Oh, I just pressed continue. Yep. Yeah, that's the shadows going. That's the shadows going. Okay. Sure. Okay. And you can go ahead. Perfect.
Ready. Thanks so much, everyone. Good morning. Today, I'll be presenting on our workshop paper, Feature Matching in the Dark, a homography-based RGB-IR feature transformation for low-light vision. So first, the challenge is reliable scene understanding across lighting conditions. As lighting decreases in a room, in a scenario, RGB images can degrade due to just the physical constraints of camera sensors detecting the visible spectra of light. However, infrared cameras, they capture thermal radiation in the IR spectrum, and that is consistent even when visual lighting degrades. So for some real-world applications, this autonomous navigation in nighttime is one of how difficult it is for RGB applications, where you may have an operator going from an indoor environment to an outdoor environment, where you may have significant light in one environment and low light going from like an indoors to a nighttime or a sunny day to a dark room. Anything like surveillance systems where the entire diurnal cycle is mapped. And search and rescue operations where you may have a whole lot of, really anything can happen and change the operating environment. So for some limitations of each approach, RGB has great detail, high resolution, good color information. It maps very well to what we see with our human visual system. And because of all the development of this technology, it is relatively inexpensive. For some cons, poor low light performance, it can be blocked by visual obstructions, and it's limited to only that visible spectrum. For IR, it is unaffected by the visual spectrum. It can detect temperature differences between objects, and it can reveal hidden heat source. And so for some cons, usually it's of limited detail, low resolution. It can fail to capture certain reflective surfaces, like in IR, a whiteboard, for example, can act as a mirror, whereas glass or a mirror itself might be seen differently. Generally, they are significantly more expensive as well. And if you have a room in a steady state scenario where all the objects in the room may be of the same or similar temperature, they can really struggle to differentiate those objects. So for our approach, I'll first go over a RGB IR feature transformation, and then I'll move into a down task of a surface normal estimation. So a little bit about the data we used. We collected a multimodal data set for benchmarking that has a synchronized RGB and IR cameras in a stereo setup. And then that's captured alongside LiDAR scans. The LiDAR isn't used for this project, but it will be important as we move forward to future work. We captured 3 scenes, 2 indoor and 1 outdoor scene. A billiards table and a computer lab are the 2 indoor scenes, and those were captured with full and low illumination, meaning all lights on and then either most or all of the lights off. And then the outdoor scene, to get kind of the full range of what might be visually seen, we captured it at noon, afternoon, evening, and night. And you can see that there's a massive lighting difference as measured by a calibrated luximeter, where we took an average over the scene. So there's been a lot of work in feature matching, starting with SIFT, SURF, ORB, and moving on to more recent deep learning-based approaches like LOFTR and then XOFTR. Up until this point, these approaches really struggled with cross-modal feature matching because IR images and RGB images don't share the same features. When you run feature matching algorithms, they're not going to detect the exact same edges necessarily. So until these more recent approaches like specifically ExoFTR, was designed specifically for cross-modal matching. So really what I'm getting to is that deep learning kind of bridges that modality gap. We're for this project utilizing some models trained through the Minima data engine. There's another paper that's being presented here this year. But so they take source data and generate a bunch of pseudo modalities to get better feature matching, and then they fine tune existing algorithms with that synthetic data. So just going along with that, we evaluated a couple of the different feature matchers available through the Minima engine and found that for matching precision, the ExoFTR achieved the best results on our data. So some of the others were good in other areas, but for our purposes, we chose to go with the ExoFTR model. And so I'll go a bit into the transformation process that we're using. So first, we start out with our RGB and IR image pairs. We'll do the feature extraction to find all of the feature matches, and they're ranked off of their epipolar error, where green being low epipolar error, red being high. From there, we do some ransack filtering. And after that, we are able to map so we do a homography calculation and we're able to map IR features into the RGB domain. So what we get is this combined feature set where all of the features are mapped into a single domain. You can see like along the edge, this trampoline here, the IR picks up a lot more features than the RGB does in this low light scenario. So that's useful for downstream tasks. And just a note on the feature stability. So as expected, RGB features are much more difficult to detect in low light. In these scenarios, we saw, at least in these two rooms, like almost 75% drop in detectable RGB features, which makes it very difficult for any applications that depend on feature matching like SLAM or et cetera. So next, I'll get a bit into the surface normal estimation model. Just as a brief overview, surface normals are unit vectors that are perpendicular to surfaces. They represent local 3D orientation, and it's essential for scene understanding, 3D reconstruction, and realistic rendering problems. So deep learning and machine learning has been used pretty extensively for surface normal estimation, starting with geometric primitives, moving on to CNN-based approaches, more complex architectures, and the one we'll be using is this tilted image surface normal network. So the key challenge is that these methods can struggle in low light conditions, which limits their applications. So as an example, here's a surface normal map generated by the TASN model for the billiards table under full illumination. And here it is. Here's that same image on a slightly different view angle, but what you can see is that here in the full illumination, you get very good, distinct boundaries of objects, walls, etc. Here in the low illumination, we see that the model gets confused, which makes sense. You're losing information in low light. So we decided we have a somewhat limited data set, but we have a model that is an expert in these full illumination scenarios. So we could use a teacher-student type model. We take the RGB image and pass it through the TASN network to generate what we're calling a pseudo ground truth here. And then we take that same RGB image and its paired IR image, pass it into this network that we've created, and then to our output, we map them as close as possible using our loss function. So we do get good expertise from the original model in full lighting scenario and are able to transfer that to a more general. Today I'll be presenting on our we're getting playback on the device. So first,
I don't know.
as lighting decreases in a room, in a scenario, RGB can be great due to just physical constraints of camera sensors detecting the visible spectrum of light. However, infrared cameras, they have thermal radiation in the IR spectrum, and that is consistent even when visual lighting degrades. Okay. So still going. Autonomous navigation at nighttime.
Yeah, we know.
There's an outdoor environment where you may have significant light in one environment and light going like in indoors to a nighttime or a sunny day to a dark room. Anything like surveillance systems where the entire
I think we're on the menu here. Maybe we can just mute it.
Yeah, I don't know. How do you? Maybe we can do that.
Yeah.
And that is for IR, it's unaffected by the spectrum and temperature.
There we go. The last one. All right. Sorry about that. As technical difficulties. But yeah, so we are able to transfer expertise from this expert model to our new model using the pseudo ground truth. So we use a multi-component loss function built into 3 parts. We have an angular loss, which is identical to the one used in the tilted image surface normal paper, and that will measure our angular differences directly. We then also use structural similarity index for, excuse me, better local geometric details. And finally, we also implemented an L2 loss because there was it adds a little bit of gradient signal, and we noticed a little stability issues when we were training without it, so we added that in. And then for our results, with our limited training data, the student model doesn't quite reach the expert model's performance in the ideal scenario at the best conditions. However, as we move towards this lower light level, our RGB model maintains very similar performance to as it does in the highest lighting conditions. So, and this is what we can, improve this low light surface normal detection with the combination of modalities. So just as a visualization, here in the top, we see the ideal lighting scenario. At the bottom, we see the low lighting scenario. Here's our RGB and IR image pairs for both high and low lighting, and the surface normals for our model are almost identical at both the ideal lighting scenario and the lowest lighting scenario. While our traditional expert model is unable to really predict any surface at the lowest lighting scenario. So with that, here are some references, and I'd like to open the door to any questions, and thank you all for coming.
Any questions?
Yes.
Thank you for the presentation. I missed the beginning, so maybe I misunderstood, but I'm wondering, it seems that you were matching between RGB and IR.
Yes.
But why wouldn't you add them together as a 4th channel and then match between those 2 modalities, or have separate sets of features per modality?
That's a great question. So part of this effort is we'd like to be able to use the IR information with existing frameworks. And that if you're adding an extra channel, you may have to like retrain a network. With this, you may be able to just pass the additional features in for for example, like SLAM.
So you have a feature pipeline and just transform it to some common set, maybe to speak of it.
Exactly.
That makes sense. Thank you.
Thanks.
Any other questions?
Hi, thank you. How did you get the surface normals to start with? How was the ground truth for that?
So the ground truth was created using that expert model. So it's not real ground truth. But it uses that surface normal estimation network to predict a ground truth and try to map to that same output.
Thank you.
Thanks.
I want to know about some of the execution performance and how do you handle the frame rate or sampling rate that comes.
Oh, so for this particular scenario, the cameras are organized. They're at a 0.5 hertz, so we get two images per second, but they're synchronized through software. So it's not running live.
Okay, good. Yeah, thank you very much.
Thanks so much.
Let's see, let's start with our next speaker. Next oral talk that is given by Eric Sandel and from ETH Zurich. The title is Flight SLAM and Global RGB Only SLAM with 3D Gaussians. Eric, can you try to share your screen?
Hello, everyone. Can you hear me?
We couldn't hear you.
What about
Now we can hear you. Yeah.
Okay.
Great. 1 second. The screen is not shared.
Already?
With the in-person audience. In Zoom we can see your screen and we need to try to. Oops.
So you do it for me, or do I need to do anything?
I do that for you.
Oh,
All right. Okay, you can go ahead. Yeah.
Excellent. 1 second. Just need to. Okay, great. Well, thanks a lot for having me online, despite that I'm not there. And I see we're running a bit behind time, so I'll try to keep this efficient. But let me get started. So this paper is about globally optimized RGB only SLAM with 3D Gaussians, and this is joint work with these people listed here. So we're all familiar with what SLAM is and why it's useful. So can just
1 second. Can you pause us 1 second? It seems like stop sharing.
Okay.
In on-site. So
I see.
yeah. Share the screen. Okay. You can go ahead now.
Okay, I can try go just, do you see the change here now?
Yeah, we can see the change.
Okay, then I'll continue. So we're all familiar why SLAM is useful, but just let's remind ourselves, why do we need dense SLAM? So dense SLAM is where we reconstruct every pixel in our input. Well, to just name a few applications, it's useful for collision detection in robot navigation and planning, also for scene understanding when we want to infer semantics from pure geometry, and of course for realistic AR. And at the time when we did this research, 3DGS had just been introduced to SLAM, and one of the first works in this domain was MonoGS, which builds this 3D Gaussian map incrementally It's gives great rendering, is reasonably fast, but it lacks pose robustness, so the tracking is not great. And in RGB only mode, the geometry is also not great. We also saw around the same time LoopySlam, which is a similar system, but it uses a neural point cloud instead of the 3D Gaussians. This is, on the other hand, quite good in terms of geometry, but requires depth input, and the tracking is globally consistent. So the obvious question sort of we asked ourselves in this project, can we combine the best of these two approaches? And that is sort of the essence of SplatSlam. And so in principle, we tried to answer the question, how can we make RGB only SLAM more robust? And what I mean by robustness here is specifically in terms of pose accuracy and the geometry that we estimate. And we developed two improvements to achieve this. One, a so-called DSPO module, which helps us improve dense depth estimation. And also we deform the 3D Gaussians online to adapt to loop closure and such. So let me run you through how this works by putting out the framework in front of you. So the input is a video from which we extract keyframes, and these are simply stored in memory. And each keyframe we estimate its pose and per pixel depth. And we feed these keyframes as input to the DSPO module to refine the pose and depth estimates. But we also have some additional inputs to the system. One being a binary filter for each predicted depth map. And this binary filter predicts where we have outliers and where we have inliers in the depth. And this is simply done by projective warping and thresholding, so there's no learning there. And we also have a mono depth estimator, which outputs relative depth maps, which are also fed as input. So now we can go ahead and look at this in more detail. So in principle, it consists of just two loss functions that are optimized alternatively. The first one is typically called dense bundle adjustment in the literature from DroidSlam. And the goal of this loss function is to estimate omega, which is the camera pose, as well as the disparity D of the keyframes. And we do this simply by using an optical flow network, in this case Raft, as a proxy ground truth. We formulate a reprojection error in pixel space to explain the optical flow. In terms of the DSPO layer then, or the DSPO loss, I should say, it borrows, for the first term, it borrows the one from DBA, but with the difference that here we don't optimize all pixels in the image. Rather, we only optimize those that are classified as outliers in the filtering step. The inliers we just keep fixed here. We also optimize the scale and shift of the mono depth. And in the remaining two terms in this loss, the first one, here we assume that if the mono depth is scaled appropriately, it's better than the outlier depth. So we try to optimize the outlier depth to fit to the mono depth here. And in the last term, we are simply optimizing the scale and shift of the mono depth. So that's all well and good, but let's see how this works out in practice. So if we only were to use the DBA layer, or the DBA loss, we get depth looking something like this. So here in dark blue, we have outliers. They are not accurate, those depth estimates. And for example, this happens in repetitive pattern regions where typically optical flow methods struggle. And if we use the mono depth information from the DSPO, we can actually resolve this ambiguity and produce overall more accurate depth maps. So that's the idea behind it. And to tie this together with a full SLAM pipeline, we run this DSPO module over different factor graphs to realize local BA and loop closure and such. And finally, to do the dense mapping, we combine the mono depth and the estimated partial depth to produce complete depth maps, which we use to do incremental 3D GS mapping. And this follows quite a standard protocol in terms of applying an appearance and a geometric loss. And finally, at the beginning, since we're doing this in an incremental way, the Gaussians that we add initially may not be, let's say, initialized at a very good location. And afterwards, as we evolve the system, when drift is corrected, we may need to account for this. So we do this simply by deforming the Gaussians with first a rigid transformation as a result of the post update. And then there may be changes in the depth as well. And we shift the Gaussian along the optical axis and also account for the change in scale as a result of this. So looking at some of the results here on ScanNet in terms of re-rendering, we can see that we achieve around high 20s in terms of PSNR, and for the depth rendering, we get around 10 to 20 centimeters in terms of depth L1 error. We can also have a look at the metrics for this evaluation. So at the time, compared to the methods that were available, GlorySlam is one that uses a neural point cloud compared to the 3DGS method. And MonoGS produces worse rendering because of the frame to model tracking system. So they don't apply global consistency to their process. So this affects their rendering quality. And if we look at the meshes that we get as output compared to those two approaches, now we're able to resolve, for example, the legs of this table, which was not possible before. We can also verify this by looking at some mesh metrics and by looking at the rendering error of the depth. So we get around 2.5 centimeters here. In terms of tracking accuracy, on ScanNet, we are on par with GlorySlam, which is also using the same type of tracking backend. And to finalize, in terms of runtime and memory footprint, we use comparably to the other methods available around 17 gigabytes peak GPU usage. And regarding runtime, we're slightly faster, still not fast enough, but around 1 to 2 FPS. So in short, what this work aimed to do was to combine for the first time a frame-to-frame monocular tracker with global consistency with a deformable 3D Gaussian map, along with proxy depth, which makes use of essentially multi-view information and a monocular depth estimator to improve the robustness. And this leads to improved map sizes and a slight improvement in runtime compared to the approaches we saw at the time. So the key results is that we achieved state-of-the-art RGB-only reconstruction for indoor environments, I should point out, as well as re-rendering and on-par tracking here with GlorySlam, and also on par or smaller map sizes in terms of the footprint of the final map and competitive runtime. And our source code for this is open source, and you're more than welcome to try it. And with that, I thank you for listening, and if you have any questions, I'm happy to take those.
Maybe we can take 1 or 2 questions.
Yes.
The audience has one. Okay, no questions. Okay, thank you, Eric.
Perfect. Thank you very much.
Thank you.
Good luck with the rest of your workshop.
Thank you.
Bye-bye.
The third talk. Yeah, this talk is given by Rohit Dulam, and the topic is silent object detection with dynamic convolution.
Okay, thank you. Good morning, everyone. This is Rohit Venkat Saidulam from the BIMS lab at University of Delaware. And today I'll be talking about our paper, Salient Object Detection with Dynamic Convolutions. So what is salient object detection? Salient object detection is a dense prediction task where the pixels of a salient object or the object which catches the attention of humans immediately are labeled as foreground or 1 in numerical terms, and the background is labeled as 0, or the pixels that are not part of the salient objects. For example, the humans and the bike in the image. So our motivations are twofold. Firstly, current works in salient object detection tend to use ImageNet pre-trained backbones, and ImageNet pre-training is like a 2-step process where first we create an image classification network, and then that is trained on ImageNet for hundreds and hundreds of epochs, and that network with all those weights is used for downstream tasks like salient object detection. Along with some feature refinement modules added on top of that backbone. So it's a 2-step process, and research has shown that backbones built specifically for image classification are not the most optimal, because self-supervised learning-based models have shown that inferior ImageNet performance doesn't lead to inferior downstream task performance, and they in fact perform better. And also the fundamental difference between the pre-training and fine-tuning tasks is another thing that is fundamentally or intuitively different. So keeping these things in consideration, we wanted to explore alternative pre-training pipelines for SOD. And the other motivation for our work is the fact that we would like to induce some input dependency into a convolutional neural network or a convolution operation. So a traditional convolution operation is input agnostic in the sense that the same weights just go across the image, try to find patterns, and that happens for the entire data set. So input specific feature extraction is kind of difficult. And to overcome this shortcoming, prior works tried to use global average pooling based attention computation, and then use that information to influence the impact of convolutions. The drawback with such an approach is the fact that global average pooling tends to reduce or compress the spatial information into a single scalar per each channel. So we wanted to explore other ways. In fact, we wanted to explore a self-attention based method to induce such input dependency into a convolution operation. So our contributions are again twofold. Firstly, in order to create a salient object detection dataset to pre-train it, we used semantic segmentation datasets. I mean, the overlap between semantic segmentation and salient object detection is very great because the difference is the per pixel classification. In salient object detection, it's a 2-class classification, and a semantic segmentation setting, it's an n-class classification. So we leveraged the open images and the COCO datasets. We combined them. We augmented them by horizontal vertical flipping, and we create a 3.2 million image dataset. The primary advantage with this setting is the fact that the entire pre-training and fine-tuning networks will remain same. So I use the same network to pre-train, and without any modification, I can directly fine-tune it on the target task, which is salient object detection. And next, so this is what the previous methods were doing. They try to compress the information to a single pixel value or a single scalar value, and then use that to kind of compute to induce some input dependence. Whereas what we are saying is, rather than just compressing the entire spatial information, can we use attention? Can we compute attention and use that information to kind of dynamically aggregate information for each pixel? For each pixel, can we have a dynamic window? Is what we are essentially trying to do. So moving on to the network architecture itself. So this is the network built entirely from scratch for salient object detection. And it is a unit style encoder-decoder architecture, which has 2 encoding stages. And this network is made up of something called dynamic long-range units. And the subscript, that's, I don't know if it's visible, but the subscript tells the kernel sizes that we have used. So I have used 9x9, 7x7, 5x5, and 3x3 in the first encoder block. And in the second encoder block, I've used 9x9, 7x7, and 5x5. So, and also in our network, we have used both saliency supervision and contour supervision. We do that because many works have shown that pairing them together is beneficial for salient object detection. So moving on to what a dynamic long-range unit is. So the word dynamic implies that it's built using dynamic convolutions. And the long-range unit means that we have a really large receptive field achieved through this formulation. I'll show in the next slide. So what essentially this block is, we have multiple dynamic convolutions stacked on top of each other. And we do that in order to increase the receptive field. And then we have some smaller convolutions to like pre-process and post-process the input and the output. And then we have a skip connection after each of these blocks. So looking at the results, so here what we are seeing is the outputs from each of the dynamic long-range units in both the encoders. So the first 4 are in the first encoder and the second 3 are in the second encoder. So the smaller convolutions, if we look at this particular column, the smaller convolution tends to concentrate more on the edges of the salient object. Whereas as we move to larger convolutions or larger kernel sizes, the importance is more centered on the salient object itself rather than only on the boundaries. And it is quite evident in this image and in this particular image, the truck. And moving on to the second stage, the outputs or the concentration tends to remain on the boundaries, since contour supervision is also a part of the training process. And moving on to the dynamic convolution. So formally, a traditional convolution is represented like this. It's the weight matrix multiplied by the pixel at each location inside that window. And in order to modify this operation, we add an additional term that is being generated using attention. So what essentially is happening here is I use attention to create this. So that particular term is saying for each pixel, I will create a weight matrix, which will determine as to how much each of the neighboring pixels would have an impact in feature extraction of that particular central pixel. So that is being computed using attention, and that slide modification leads to performance improvements in our model. So moving on to some pre-training details. As a comparison, we have listed the pre-training regimes of various networks, state-of-the-art networks in our comparison. So these four are the most recent and the state-of-the-art models, and they tend to be pre-trained on ImageNet datasets for greater than 300 epochs. And the most recent work, MD-SAM, is a SAM-based model, which is being pre-trained for 800 epochs using the self-supervised learning regime. And on top of that, it has been fine-tuned for 2 epochs on the SAM 1 billion dataset, which is 11 million images. Whereas our works are only using 3.2 million images, and only for 20 epochs is what we are pre-trained for. So that is a significant reduction in the amount of pre-training epochs that we have. And moving on to some more implementation details. So the data set that we train on is called the DUTS. That's data set. It contains 10,500 images, and the fine-tuning phase only has 11 epochs. That is very tiny. And the image size is 384 by 384. The loss function that we use is a combination of binary cross entropy loss, intersection over union, L1, and the dice losses. And the evaluation metrics are the mean absolute error, the max F score, and then the E and the S score. So we also propose 2 model sizes. The one that I showed is the 78 million parameter model. And to get the smaller model with 62 million parameters, we replace all the post and pre-processing 3x3 convolutions with 1x1 convolution. And then also everywhere where I have 2 3x3 convolutions in series, I replace the second 3x3 convolution with a 1x1 convolution. So that led to a reduction in 16 million parameters, but as we'll see, not a lot of performance hit. So the performance of these models has been evaluated on 5 different data sets. We have 5 different test sets with the varying scenarios, and all the scores have been averaged. So the mean absolute error, the lower the better. Our model is slightly bad than the state-of-the-art models, very slightly. But on the MaxF score, the S score, and the enhanced measure, on the other 3 metrics, we are quite neck and neck. We are quite in the same ballpark. And also a thing to note is VS Code and MD-SAM both are based on transformer architectures. Ours is a purely convolutional neural network. And the state-of-the-art convolutional neural network model is Tracer 7. And we comfortably outperform, both the variants outperform Tracer 7 on all these data sets, on all metrics. Looking at some visual results, our models tend to perform better than other state-of-the-art models, especially in this row where it's very difficult to find the second animal, but our models really segmented properly, whereas the other models are not comfortable in doing that. And a small evaluation was also done on video salient object detection. The evaluation was done on 4 different data sets, Davis and Davesod. Davesod has 3 different splits, easy, normal, and difficult. As we move from easy to difficult, the scenario gets far more challenging. And our model performs the best on most metrics, barring only 2 of them. And also the visual results demonstrate the same. So concluding my talk, the contributions of our work are we curate a 3.2 million image pre-training data set for salient object detection. And this is significantly, and the pre-training pipeline is significantly smaller when compared to other state-of-the-art models. And also we use an attention-based mechanism to dynamically adjust the importance of pixels. So for each pixel, we are dynamically saying, okay, this particular pixel will have a certain weight to it, rather than having equal weight among all the pixels. And then we achieve state-of-the-art performance on two tasks, the 2D RGB and video salient object detection tasks. Some references and yeah, thank you. Questions?
We may only have one question, okay, and any questions for the time? Okay, thank you. Yeah, okay. Yes. Okay, then that goes to the keynote speaker. So let me introduce Dr. Hao Zhang and from UMass. So Dr. Hao Zhang, can you at the same time try to share a screen?
Yeah, can you see my screen?
Not yet.
How about now?
Let's see.
Let's do it one more time.
It seems like I couldn't see that. Right? Yeah, it's not sharing the screen.
How about now?
Now it's sharing. Yeah.
Okay.
Okay. Let me introduce Dr. Hao Zhang, and he's an associate professor in computer science and robotics in the UMass and IMAST. And he's leading the human-centered robotics lab, and his research focuses on lifelong collaborative autonomy. And he has received an NSF Career Award, DARPA Young Faculty Award, and the DARPA Directors Fellowship. And Professor Zhang has authored over 50 papers in top robotics, vision, AI conferences, and like ICRA, AROS, CORA, and CVPR, and has received multiple paper awards. Yeah, Dr. Hao Zhang, you can go ahead.
All right. Thank you, Dr. Lu, for the introduction. Good morning, everyone. It's a great pleasure to meet you all online. I'm not able to join in person this year, unfortunately, but I do hope you are having a wonderful time at CVPR and enjoying your stay in Tennessee. All right, so for today, I'll be talking about collaborative perception in multi-robot systems. Multi-robot systems are rapidly becoming vital to both industry and the society, and the images shown here highlight some of the most exciting and forward-looking visions in today's multi-robot systems. So for example, the COVID pandemic exposed critical vulnerabilities in many industries, such as manufacturing, which continue to face labor shortages and the rising workforce costs. And multi-robot systems are widely viewed as one of the most promising solutions in robotics to potentially help.
And then we take that same RGB image, it's paired IRM.
Okay, all right. So may help both society and the industry to address these challenges. And robot perception is a fundamental robot capability that has been actively developed and studied over the past many decades. And however, relying solely on individual perception limits the potential of multi-robot systems, for example, in applications like connected autonomous driving. So this is because even with advanced sensors, robots in the field still have limited fields of view. The presence of obstacles and the dynamic objects often cause occlusions that may restrict what the robot can observe. And also, robots often need to operate in challenging conditions when operating in the field, such as poor lighting condition and like bad weather. And sensors themselves are noisy and they may fail over time. So these challenges highlight the benefits of collaborative perception in multi-robot systems. So by connecting multiple teaming robots, each robot gains access not only to its own sensor data, but also to diverse perspectives and the granular information shared by others. So this image shows an example, and in this example, a pedestrian is jaywalking across the street and is not visible to vehicle A. And this blind spot could lead to an accident, posing some severe safety risks to the pedestrian. However, if a partner vehicle B detects the pedestrian and shares the information with vehicle A, the accident can be prevented. So as a result, this collaborative perception enables multi-robot systems to see together and build a shared understanding of both the environment and also each other. So in this talk, I will present our research on developing collaborative perception in multi-robot systems. I'll begin by introducing our work on correspondence application, which ensures consistent object references across teammates. Then I'll discuss collaborative localization through multi-robot sensor fusion, which enables robots to jointly estimate both their surroundings and the poses of teammates. So before robots can collaboratively recognize, track, and manipulate an object, they must first correctly identify and refer to the same object within their own field of view. So in this example, a UAV and a UGV observe the same environment from different perspectives. To exchange information about an object, they must consistently refer to the same one. So this problem is generally called correspondence identification in multi-robot perception. And this is a challenging problem because each robot typically observes non-overlapping parts of the environment. So the same object can appear very differently from different perspectives, while different objects may look nearly identical, which is called perceptual aliasing in this situation. So if you consider all the robots in the field, they actually all look similar when other teams of robots try to track them. And moreover, correspondence must be identified under the constraints of communication bandwidth and the computing power for multi-robot systems situations. So as a result, at a very high level, this classic computer vision methods that rely on pixel-wise association often perform poorly, as they typically require a large amount of data to be shared over the network between robots. That's sometimes impractical. And similarly, object re-identification methods can also struggle a bit in the presence of perceptual aliasing, where different objects may appear visually similar. So our early solution mathematically formulate correspondence identification as a regularized multi-order graph matching problem. We represent the objects within a robot's field of view using a graph that encodes both object attributes and their multi-order spatial relationships. To explicitly address perception uncertainty and account for non-cohesive objects, we introduce regularization terms into this graph matching approach. So in our formulation, the objective is to optimize the correspondence matrix, that is X, the variable X. And the constraints here enforce each row and the column in X at most have one element equal to 1. So these constraints generally guarantee that each object can at most have one correspondence. The objective function here generally encodes the overall multi-order similarity given the correspondence X. So the first term models the attribute similarity between a pair of objects. The attributes are used to encode semantic or some appearance features of the objects. The second term models the pairwise distance similarity between two robots, and the third term models the angular similarity. So we use the angular relationship among three objects because it is invariant to scale variations and usually more robust to spatial deformation. So given this multi-order graph matching formulation, then the question is how to explicitly address the difficulties caused by perceptual uncertainty and also non-cohesibility. So in robotics, uncertainty always exists in object attributes and positions that are obtained from sensors or computed using some methods. So we first it should be right. Can you hear me now?
Yeah, you had something else going there.
Can you hear me? Test, test, test.
Can you pause a little bit? And we are having some technical issues right now.
Can you hear me now?
Yeah. We can hear you.
And they're sharing presentation.
Oh,
Yeah,
can you hear me now? Okay, let me share my screen. Is it working? Hello. Test, test, test.
yeah, we can hear you. We are still trying to figure out right now.
All right. Yeah, I'm sharing my screen. I don't know whether I can see it or not.
Ta-da. See his screen. I wouldn't see his screen.
Yeah, can you share your screen? Are you sharing screen right now?
Yeah, just share my screen. Can you hear me and see my shared screen?
Yes.
Well, you need to come with the slides right now.
So we see your desktop background.
Oh yeah, yes, yes. That should be correct. How about now?
Okay, it works. It didn't work. Okay, finally. I don't know.
It works now? All right, problem solved. It's more like a robotics problem. All right, anyway, so where we are. So we first, well, to address the uncertainty, what we do is we first compute the three-weight matrices that encodes the effects of uncertainty on the three similarity terms in the objective function. And this weight matrix enforces an uncertain similarity term to contribute less to the value of the objective function. So then we introduce a new regularization term over X, and it computes the sum of the uncertainty and uses it to penalize the correspondence between a pair of objects that have large attribute and position uncertainties. So intuitively, if two objects have large uncertainties, it is not appropriate to decide or identify a correspondence between them, even when the pair of objects have a high similarity score. So for non-covisible objects, they do not have a correspondence because non-covisible objects are not observed by both robots. So, but on the other hand, because similarity scores always have a positive value, adding any correspondence can always increase the value of the object function, even when the correspondence is incorrectly computed from non-covisible objects. So to address this problem, we introduce a non-covisibility penalty as the second regularization term. And in this case, for every newly added correspondence, only if the overall similarity score it introduces is greater than the penalty it causes, the correspondence can be identified by our approach. So this regularization term generally addresses incorrect correspondences that are constructed by non-covisible objects. So this video demonstrates the real-time execution of our approach in a connected autonomous driving simulation. So vehicle 1 is on the north of the intersection and vehicle 2 is on the east driving under the tree. Both vehicles are red. As you can see here, so this street scenario is relatively complicated. So it includes multiple vehicles and pedestrians. It has many non-covisible objects, and the several vehicles also look similar. And our approach is able to correctly identify most of the correspondences. So this generally will allow connected vehicles to correctly refer to the specific street objects when they share and fuse data on that specific object. So we quantitatively evaluate our method and compare with some previous methods as well. So our ReID is a learning-based object identification method, and the MOS is a graph matching approach. And we use precision recall as our metrics to evaluate the approach. So precision is defined as the percentage of the detected correspondences that are correct. And the recall is defined as the percentage of the true correspondences that are correctly detected. So since the street object, such as vehicles, have similar appearance, we observe that real ID generally does not perform that well. And although this mouse can identify correspondences for almost all objects, but they may have the detected many of the detected correspondences are actually not correct. So the table shows that our full approach works the best at that time. And we can also observe that both regression terms are important to improve the performance as they address perceptual uncertainty and also non-covisability respectively. All right, so that's the first approach. That is one of our first methods based on the classic graph matching theory. And recently we developed a bandwidth adaptive spatial temporal graph learning method. And this approach integrates spatial temporal graph learning with graph matching for correspondence identification. And it explicitly addresses the challenge of communication bandwidth constraints that frequently change over time. So specifically, we develop a spatial temporal graph representation that encodes both spatial and temporal information of the objects observed by each robot. We treated the spatial temporal graph as a heterogeneous graph that encode the node level embeddings to capture spatial and temporal clues. We further generate a graph level embedding using a pooling layer designed for heterogeneous graphs. And each robot computes a set of node embeddings along with one graph level embedding. However, due to the bandwidth constraints, connected robots actually cannot share all the node embeddings. So to address this to address this challenge, we only share bandwidth permissible node candidates that are likely to be observed by the collaborating robots. So here we present the quantitative results for two traffic scenarios, the normal traffic in the top row and the crowded traffic in the bottom row. And each sequence of the points here represents the observation history over the past 5 time steps. And red points indicate the non-covisible objects observed by only one vehicle, while green points represent the covisible objects observed by both vehicles. And all the results are based on a setup where vehicle 1 receives information from vehicle 2, which aims to selectively share covisible objects with vehicle 1. So to quantitatively evaluate the performance, we still use precision and recall along with a new metric called the bandwidth improving score, which quantifies how effectively a method reduces communication bandwidth requirements while maintaining or enhancing performance. So basically, based on this BIS and comparing to DGMC, which is the second best method used in our experiments, our approach achieves a significant improvements ranging from 8% to around 56% in selecting useful information and making better use of the bandwidth. So when applied these kind of approaches to street object localization in connected autonomous driving under communication bandwidth constraints, so our approach also improves driving safety by around 30%. This video generally shows 3 examples of common driving maneuvers, including overtaking, turning, and the crossing intersection. All right, so once robots can identify consistent object references across teammates, they can begin to jointly localize both their environment and also each other. So next, we'll explore how multi-robot systems use sensor fusion to collaboratively localize surrounding objects and also team members. So collaborative localization enables multi-robots to jointly estimate the locations of their surroundings, which enhances situation awareness of both the environment and also the team. And to enable this teaming capability, we need to address several main challenges. So first, how to model the complex relationships among the observed objects. And second, how to quantify the uncertainties in localization. And these 2 problems we've discussed in the previous slides. And third, how to handle asynchronous observations resulting from communication delays between robots. And finally, how to effectively fuse observations from an arbitrary number of collaborating robots. So to address these challenges, we developed a method called asynchronized collaborative localization that combines spatial temporal graph learning with this model-based state estimation. For the first challenge, we introduced a spatial temporal like graph network to encode complex relationships of the object of the observed objects. And also it is used to predict objects' moving trajectories based on their historical motions. So specifically, we create a representation using this graph, and each node denotes an object, and there exist two types of edges in this graph. The spatial edges encode the distance between the spatial distance between the objects, and the temporal edges capture the motion of each object over time. So our approach learns these temporal motion patterns of the objects using LSTM layers, and model spatial relationships and the interactions among the objects using a graph attention network. And given these spatial temporal embeddings, our approach estimates the object locations using another layer of LSTM. And given the spatial this graph network, we develop a deep like ensemble technique to quantify the uncertainty in localization results. And we create K models with the same architecture, each initialized differently. And these models, they run in parallel on the same input, and they produce K location estimates for each object. And the variance among these estimates reflects the location uncertainty, while the mean generally provide the final predicted object locations. So to address asynchronous observations caused by communication delays in multi-robot systems, we use our spatial temporal graph network to compensate for these delays. So for example, consider a system with 3 robots where the third robot's estimates arrive asynchronously due to communication lags. And since these delayed estimates do not reflect the current true locations of the robots, they cannot be directly fused with other observations without adjustment. So in this case, we compensate for the asynchronous observations by using the spatial temporal network to predict their current states based on the history. So by doing so, we transform these delayed estimates into synchronized, up-to-date predictions that can be treated just as normal estimations during the fusion time. So after that, the last challenge is to integrate an arbitrary number of estimations from arbitrary number of robots. So to solve this, they design a multi-robot fusion game that computes optimal estimates by calculating the joint distribution of all the incoming observations. So we evaluate our approach in connected autonomous driving scenarios and also using real robots, as you can see here, and we manually introduce communication latency between robots sharing observations ranging from 0.1 to 1 second. And we compare our methods against 2 baselines, and in these figures, the red lines represent the predicted object trajectories, while the yellow lines show the ground truths. And from the result, it's clear that our approach outperforms the others and providing more accurate trajectory predictions despite the communication delays. And we use this displacement error to evaluate our approach, which is defined as distance between the estimated and the ground truth locations. And we also use this relative displacement error. That's a normalized version of this displacement error. So without introducing too many details, both metrics consistently support the same conclusion that our approach achieves better performance in this specific application. So what is interesting is we further analyze the key characteristics of our approach. So the first figure here shows the increasing latency, how increasing latency affects performance. And we observe that a gradual incline in error as latency grows. And beyond 600 microseconds, performance stabilized with minor fluctuations, as robots rely mainly on their own observations without collaboration. So this generally demonstrates that our method effectively fuses asynchronous multi-robot state estimation even under large communication delays. So the second figure illustrates the error decreases steadily as more robots join the collaboration. So when there are more than 5 collaborators, the improvements actually plateau and with smaller fluctuations only, and we did not see significant improvements on the performance. So the third figure shows robustness to noise, and we observe that our approach generally achieves the smallest area under the curve. It demonstrates that a hybrid method like ours that combines model-based estimation and the learning-based estimation generally can enhance noise robustness. So We have further extended this idea by integrating cross-robot multi-sensor observations to estimate relative poses for multi-robot formation control. And in these results, 3 robots form a wedge formation and estimate their relative poses by comparing their observations of the environment. And in this scenario, no robots actually has a global map of the environment. And a separate, a separate formation control methods is then used, and that uses this estimated relative poses to maintain the wedge formation as the team follows the trajectory, while each robot actually independently avoids obstacles at the low level control. All right. Now we have covered the correspondence identification and the correspondence and the collaborative localization. And now let's look ahead to the open problems on collaborative perception in multi-robot systems very briefly. So I generally identify 4 major open problems. The first one is the complexity of the problem that we need this collaborative perception to be real-time, distributed, asynchronized, and also they must be performed under computation and bandwidth constraints. So in real world, the multi-robot application, especially in the field, all these challenges must be addressed at the same time. And second open problem is this perception action coupling in collaborative multi-robot systems that we not only consider about perception, but we also need to consider how actions can affect the perception. And the third one is to explore the role of generative AI with large models in enhancing multi-robot systems. Although this generative AI has becoming very popular, but their applications to multi-robot systems is relatively limited and underexplored at the moment. And last one, when we have humans in the team, then this privacy, trust, and the security in this shared perception is definitely an open problem. So at last, I'd like to thank the students in my Human Centered Robotics group, as well as my generous sponsors. Thank you all for being here, and I'm happy to take any questions that you may have.
Okay, thank you very much, Dr. Hao Zhang. Any questions? So I might have one question, and in the first of all, for the autonomous driving scenarios, that is the simulated data or real data?
The autonomous driving, most of the evaluations are done in simulation. So the simulation is Carla, and we use Sumo for a traffic controller as a traffic controller. So all the quantitative evaluations are pretty much done in simulation. But that project is a collaboration with Toyota. We do have some real data from Toyota, but that information cannot be published. So we generally, after performing this quantitative evaluation in simulation, we show the demonstration on real robots using the robots that are in my lab.
Okay. So in your observation, based on the evaluation of the real data and the simulated data, and do you see a big difference for the collaborative localization?
There are some differences, right? So there's this sim to real gap is always a problem. And well, we do have some considered and developed some method to minimize this problem. So basically, instead of directly using these raw images, we generally need some good like a CV-based methods that can convert either the simulation and the real data into some latent representation space. And then we use the features in that space as the input to our approach. That generally modularize the approach and separate our algorithms on this graph matching from the representations of the raw data. So that actually can minimize or reduce the gap between simulation and the real robot applications a bit.
Okay. So to summarize, the bottleneck between the simulation and the real data is some kind of also from the perception perspective, or there's some other major obstacles that is for this kind of gap between simulation and real data.
Well, I think even just from the perception perspective only, the gap is actually smaller. And the bigger gap is mainly on the embodiment. So when we deploy these methods on the real robots, all these computing constraints, all the network constraints, they come into play. That actually affect the models, the fact that our options to select different models a lot. So that's why, you see like all the approaches that I present, that they are relatively simple, even we call it the deep learning, the network is pretty shallow with a relatively smaller number of parameters. So this embodiment generally introduce a lot of constraints on the algorithms. And actions, that's another issue. So when robot moves, we see a lot, like for example blurries in the images. That phenomenon is actually also not that well simulated in simulations. And the other thing is this long-term changes. I'm also working on lifelong autonomy. So all these variations in terms of lighting, in terms of different weather conditions like a fog, smoke, strong wind, they are all going to affect the perception and also the actions of the autonomous vehicles. And those effects are not actually very well simulated in the existing simulations for now. Yeah.
Okay, gotcha. Okay, thank you very much. Any other questions? Okay, if no questions, thank you very much, Dr. Zhang, and then we will move to the next speaker.
All right, thank you. I'll see you all later.
See you later.
Okay, this is a more specific structure for the you know, for the task prompt decoding. As you know, we can learn the multitask you know, affinity maps from the spatial and channel dimension. So we can utilize this task-specific affinity maps. We can query the image patch tokens to generate the corresponding messages for the different tasks. And we can pass the messages among the different task feature maps, and we can generate the corresponding task-specific feature maps. And in the end, we just need one simple ML layer for us to decode the corresponding multitask prediction. So this can simplify the design for the different task decoders. As we can see, we also show some visualization of the learned spatial and channel-wise affinity maps. As we can see from this visualization figure, basically we can decoder for different tasks, such as semantic segmentation, parsing, salience detection, surface normal estimation, and the boundary detection. As we can see, for each specific task, we can learn very discriminative affinity map. And this is a very important observation, because based on this affinity map, we can decode the corresponding task-specific features. And this is demo to show the results we verified on the Cityscape 3D dataset. So basically, we perform simultaneously 3 different tasks: the 3D object detection, the segmentation, and the depth estimation. As we can see, basically we can perform one single forward inference, then we can directly predict for these 3 different tasks, and with good performance. And this is very convenient for the deployment, because we just need to perform one-time inference, then we can directly obtain all these predictions for the different tasks. Also, we did a generalization experiment to show the performance of these different tasks. Basically, we train the model on other data sets, and we transfer the model to directly perform the prediction on the Davis data set. As you know, for the Davis data set, we have only the segmentation annotations. But for this model, we can directly infer all the predictions for these 5 different tasks. As you can see from the first row, basically we have the results from the PatternNet, which is the foundation model for the multitask perception. And then for the second row, basically we show the results produced from ATRC, which is a model from ETHZ computer vision group. And also the last row shows the results produced from our model. Okay, so these are some research progress in terms of the multitask scene perception. So I would mainly talk about some research projects in terms of the larger scale scene modeling. So basically, I will talk about the self-supervised scene decomposition approach based on mixture of experts to see how we can utilize this mixture of enough experts for us to automatically decompose a very large scale scene into different scene parts. And then we can model a very large scale scene in the end-to-end manner. And then I'll talk about Gaussian splatting techniques for high-resolution or real-time modeling based on a pyramid architecture for us to model very diverse multi-scale representations for a very large scale scene. So as you know, NERF is a very effective scene representation. We just need a multi-view post images, and then we can directly model this large scale scene. And this has shown very successful results on relatively small scale objects and things. But if we directly transfer the NERF model for us to deal with a very large scale scene, for example, a scene shown in this video demo, and this problem will become very challenging because we have to deal with very large amount of images captured from this scene, and this physical size of this scene is also very huge. So a very practical approach for us to deal with this problem is the scene decomposition. So scene decomposition is critical for us to maintain the efficiency and the flexibility for large scale scene modeling. Basically, there are 2 representative approaches for the scene decomposition for large scale scene modeling. The first one is the MegaNERF, which was proposed by Argo AI and the CMU. So the basic idea of MegaNERF is to have the distance-based decomposition. So basically, we have the uniform sampled 3D point in a 3D space, and based on distance 3 throws, and we can partition the 3D thing into different parts. And for each part, we can utilize a nerve model to model this in parts. And then we have a post-processing step for us to fuse all the results produced from the different nerve models. But this is a post-processing step. The second one is actually block nerve, which was proposed by Waymo. The basic idea of block nerve is to have the physical distribution-based decomposition. The idea is actually very, very simple because we collect the image data from different 3D blocks. And for each 3D blocks, we can cluster the image data. And based on this data, we can model with a specific nerve model. The fusion strategy is very similar to the MegaNerve. They basically fuse all the results produced from the different nerve models. So this is also a post-processing step. It's a handcrafted strategy for the fusion of the different nerve models. So basically, we have some critical issues based on this existing scene decomposition strategies. So first of all, they are doing handcrafted splitting. That means they need some handcrafted strategies for us to perform scene decomposition first. And this would require priors. For example, we need to know the structure, geometry structure of the very large scale scene. This may pose very significant challenges because we are dealing with a very large scale thing. Sometimes we don't know the specific structure of this thing. Another thing is the fusion. As you know that we have the post-processing for us to fuse all the results produced from the different nerve models. So this post-processing is not learnable. So basically, if we just directly fuse the results based on some, handcrafted strategies, so we may create some artifacts for the regions that connect different parts. So this is a very, severe problem for these two decomposition strategies. So in our approach, basically we propose end-to-end learnable framework. And the key idea of our framework is to introduce the trainable gating network. This is a very critical design in our framework. So basically for each 3D point, so we can dispatch this 3D point into different nerve experts. By this 3D point dispatching strategy, we can utilize different nerve expert structures to produce the corresponding radiance properties. And we also have a learnable head for us to directly fuse the results produced from the different nerve models. So basically for all the parameters in this framework, they are learnable. So it's actually an end-to-end learnable framework. We just need to feed the 3D points in this architecture. We can directly produce the modeling results of a very, very large scale scene. So let me introduce some details of our framework. So basically, as you can see, we have this sampled array. So for each array, we can sample a point from this array, and we can dispatch this point. So first of all, we have a position encoding for this 3D point, and then we can feed this point into a dispatching gating network. This is very important, and this network will produce a distribution of probabilities. Based on this distribution of probabilities, so we can decide which experts we will dispatch this point into. We can consider top 1 dispatching or top K dispatching based on the efficiency consideration. So finally, we can have this prediction head. Basically, we can have the point features from the nerve experts. Then we can have the prediction head to directly predict the attributes for each 3D point. And then we can render the corresponding properties such as RGB colors and densities for us to produce a rendered pixel color, and we have the ground truth pixel color as a ground truth. So basically, we can learn all these parameters in an end-to-end way without any post-processing step. Okay, here I would like to show you some visualization results for the scene decomposition. As we can see that basically in a self-supervised way, so we can directly decompose a very large scene into different parts. And we can decompose the different points that have similar appearance and geometry, as we can see from these visualization results. And here I also compare with the results produced by MegaNerve quantitatively. As we can see from all these quantitative metrics, we produce significantly better results compared to MegaNerve on these larger scale benchmarks. And our code is also publicly available. So here I would like to show you some demos for the visualization of the null view sensors and also the geometry rendering. So the geometry is represented by the corresponding depths. So basically, we can sample a trajectory in the 3D space, and we can render the corresponding null views for these camera poses. And we can also render the corresponding geometry structure represented by the depth maps. As we can see, our method can produce very high quality null view rendering results. And also we can produce very fine-grained geometry structures. And we don't require any 3D information as supervision during the optimization of this model. So this is another thing, it's an open world thing, as we can see from this video demo. So basically, as you can see from the right side, a model can produce very fine-grained geometry recovery for those structures at the corner. This is a very challenging problem. Yeah. Okay, as we discussed, basically we are dealing with a very large scale scene modeling problem, so the efficiency is critical. So based on the MOE structure, we can already achieve very good efficiency. But now, if you want to further boost the efficiency of this model, so we have some insights on this direction. So as you know that we are dealing with the 3D space. For the 3D space, we have a lot of points belonging to the free space, right? So we also have a lot of points belonging to the occupied space. So basically, we can utilize a very small MOB structure for us to directly predict for those points belonging to the free space. So this can help us to largely improve the efficiency of the model. So the basic idea is to design heterogeneous mixture of nerve experts. We have a very small MOB structure for us to process for the points that belong to the free space. So this can largely improve the efficiency of the model. From our practice, we can achieve a speed up of training about 60 times compared to the original homogeneous mixture of nerve expert model we just introduced. To demonstrate the efficiency of our model, we did a evaluation on a city modeling benchmark. Basically, we have a 30K high quality images, which covers urban region of around 6.5 square kilometers. As we can see, this is a modeled 3D digital twin model based on our heterogeneous mixture of experts. And we did a comparison with another very efficient model, which is Instant GP. As we can see, we can achieve even higher efficiency compared to Instant GP on this larger scale scene modeling problem. And we can also achieve higher rendering quality compared to Instant GP from the qualitative results and the quantitative results. If we consider using NERF model for us to handle large scale scene modeling problem, there are some critical issues. So the first issue is that for the NERF models, basically they tend to capture low frequency details. This is because of the original structure of the NERF model, because they consider MLP structures for us to directly predict the attributes for the 3D points. So this will miss high frequency details. But for large scale scene modeling, we have to recover those high frequency details. This is very important to guarantee the quality of large scale scene modeling. So this is one of the very significant problems for NERF, for utilizing NERF for large scale scene modeling. The second one is the ray-based rendering. As you know that for NERF models, we consider ray-based rendering with sample rays, and we have to sample the points on each ray, and each point has to be passed through the MLP to predict the radiance attributes. So this is very computationally expensive. So these are two very significant problems for us to utilize NERF for large scale scene modeling. And also, if we consider rendering speed, and if we compare it with the rendering speed of Gaussian splatting, so basically the NERF model is 10 times lower in terms of the rendering speed compared to the Gaussian splatting techniques. There is another very critical problem, which is, if you consider the utilizing vanilla Gaussian splatting for large scale scene modeling, so we have to consider the initialization problem. As you know, For the vanilla Gaussian splatting, we utilize the CoMap for us to optimize the camera poses for different views. And also we obtain the initial points for us to initialize the Gaussian mean positions. So if you consider a very large scale modeling, we may have more than 10,000 images. So this is a very large amount of data. If you consider CoMap to optimize the camera poses and also the 3D points, this is a very expensive procedure. It may take more than 2 days for us to just obtain the initial positions and the camera poses for the different views. So this is a very challenging problem for the initialization. Another problem is that because we are performing heterogeneous modeling, and for this larger scale scene, we have objects with diverse scales, and this is a very challenging problem because we need to render very detailed structures and very detailed appearance. But if we have very diverse distribution of sizes and scales, so if we consider original Gaussian splatting, this would pose a challenge. Another problem is that we consider the same set of Gaussian blobs for us to model a very large scale scene. This is a very challenging problem, especially for the null view synthesis. Because if we consider null viewpoint, so we consider the same set of Gaussian blobs for the rendering. This would downgrade the rendering quality in the inference stage. So in our proposal, we proposed the pyramid Gaussian splatting technique. Basically, we have 3 key contributions in this framework. The first contribution is to replace the CoMap initialization with instant NGP. Because we just need around several minutes for us to obtain a good initialization for the Gaussian splatting optimization. We can already obtain very good initialization points from the instant NGP by taking only several minutes. So this is very important for larger scale modeling because we need a very fast initialization because we have to deal with a very large amount of images, which is quite different from small scale objects or scene optimization problems. The second one is because we have to handle the scene with diverse object sizes and the levels of details. So as we just discussed. So here we construct for the first time a pyramid representation based on Gaussian splatting for us to model a multi-scale underlying 3D scene representation. So based on this pyramid Gaussian splatting representation, we also proposed the adaptive rendering strategy for us to directly perform automatic scale fusion based on the viewpoints, and this can produce highly improved results. So here I would like to show a demonstration to have a comparison between our PYGS, which is a pyramid Gaussian splatting technique, with one of the state-of-the-art results based on nerve representation, which is the bungee nerve. As you can see from these 2 approaches, for the bungee nerve approach, basically you can see we can observe very blurry results because for the nerve modeling, they miss high frequency details. But if we consider the Gaussian splatting with the multi-scale representations, we can render the scene from different viewpoints, and we can also have a very high quality rendering for the different scaled objects in the scene. Okay, let's skip the next. So another very important question is that, so based on the previous projects, we have to capture multiple views for the modeling, right? But sometimes we may have only one single view. But still, we want to recover the 3D representation of the scene that is captured by this image, and we can perform null view synthesis, right? This is a very important direction. So in this project, basically we propose a feed-forward 3D Gaussian modeling framework, as we can see from this framework. So the basic idea is we have one single image as input, and then we can have a prediction of its corresponding depth map. We may have depth estimation from some foundation models to provide us some initial molecular depth estimation results. So then we have a transformer architecture. So we can feed this image into this transformer architecture. And we can directly predict the Gaussian attributes for each pixel location, including the mean position for each Gaussian blob, the opacity, the color attributes, and also the shape of each Gaussian blob. So basically, there are some basic attributes for the Gaussian blobs we can directly predict from the features of the image. And then we can have initial 3D scene representation based on Gaussian flattening. But this is not enough because we have only one single view. But our goal is actually to model entire 3D scene. So in our approach, basically we consider a cycle aggregation approach. The basic idea is if we have already an initial 3D Gaussian representation, we can render a null view. The null view is very close to the ground truth view. So if I have the null view rendering, so we can feed the null view through the transform architecture again. So we can generate another set of Gaussian blobs. And in the unified Gaussian splitting representation space, we can aggregate these Gaussian blobs. So this is a basic idea. So we have the cycle consistency for us to perform the aggregation for these Gaussian blobs. So here I would like to show you some results for single view 3D modeling based on feed-forward transform architecture. As we can see here, we have some images directly from the ImageNet dataset. So for each view, so basically we can directly render the corresponding geometry and also the null view sensors. So we also have some generalization evaluations, as we can see. So we can also perform the testing on some human faces and also artist images. So we have only single view as input into the transform architecture, and then we can perform the non-view sensors, and we can also generate the corresponding geometry outputs. So another very important thing is that if 3D scene is already lifted, sometimes we want to perform some manipulation, right? For example, we want to remove some objects in the 3D scene. So this is a very important task. So for the setup, so basically we have the input RGB image, and also we have a mask. So this mask can indicate which object would be removed from this 3D scene. So we can directly remove this 3D objects from the 3D scene indicated by this mask, and we can regenerate a new 3D scene representation. Based on this new generated 3D scene, we can perform null view synthesis. And this is very different from the 2D editing task. For the 2D editing task, basically we can generate the editing results for the ground truth camera pose. But for our proposal, basically we can generate null views after the editing operation. So this is a basic framework for our method. As we can see, we have the pose image and a corresponding mask for us to indicate which object would be removed from the 3D scene. And then we can actually model the 3D scene based on the 3D Gaussian representation. And then we can have the corresponding depth map. So we have indication of where we should remove this object from the 3D scene. After the removal of the 3D object from the 3D scene, key problem is that we have to deal with occlusion problem. Because if you remove the object from the 3D scene, so there are some occluded regions that should be painted. So in this case, we proposed a strategy, which is a bidirectional attention mechanism for us to directly pass messages for the 3D Gaussian blobs in the 3D space. So then we can utilize the context information from the Gaussian blobs that are around the occluded region to pass messages to perform the inpainting. Also, from the 2D view, we can also do inpainting for the 2D images, and this also propagates supervision for us to finish the inpainting task. So based on these two designs, we can achieve the results of the object removal, as we can see from the right side shown in this figure. So here we have some qualitative results to show the editing results. As we can see from the left side, we have the input image, and we have the mask to indicate which object to be removed. And on the right side, as you can see, we have the model of the 3D scene. In this 3D scene, we don't have these objects existing. And we can also perform very consistent rendering from the different views. This is very important, and this is very different from the traditional 2D editing task. So we can also perform another important manipulation task, which is the object replacement. For example, we can utilize the text information, the text prompt, for us to generate description of the foreground object. So we can insert this object into the 3D scene. And the key idea here is still the in-painting, because if we insert a 3D object into the 3D scene, so we also have to finish the in-painting in order to maintain the consistency between the foreground objects and the background. This is very similar to the in-painting for occlusion region. So based on our technique, we can achieve very successful object replacement task, as we can see from this video demo. We can generate different objects, and we'll also put these different objects into the 3D scene. So we're also interested in the editable object level generation based on Gaussian slotting technique. So as you know, the 3D generation is very important, because sometimes, for example, for open world visual understanding, we may need augmented data. So we can generate this data based on the generation pipelines. But sometimes the generated results may not be as you're expected. So this is a very challenging problem. So our motivation is that we want to have some interaction during the generation procedure. So if we can directly perform the interaction during the optimization of the generation, then we can generate some objects or things that can satisfy our expectation. So let me show you a demo for this object level generation based on the interaction operations. For example, we can use the text prompt for us to generate initial 3D objects. And also we can actually have some explicit operations, because 3D Gaussian is an explicit representation. So we can directly operate those Gaussian blobs in the 3D space. Then we can change the shape of the initial 3D object. And then we can also utilize different text prompts to generate different objects. And we combine these objects in a unified 3D object with different object components. And we can also focus on one specific region by refining the semantics by providing new text descriptions. We can refine the appearance and the structure for each specific region of the 3D object. Yeah. Okay, so this is all I would like to share for today's workshop. If you have any question, I would like to take any questions from here. Yeah. Thank you very much. Yeah. Any questions? Hello.
Thanks for lots of interesting talks. And then I'm particularly interested about the pyramidal representation of the Gaussian spreading. So
Yeah.
I'm talking about the large scene rendering thing.
Mm-hmm.
And then in there, like, what do we mean by the pyramid Gaussian splitting? So do we have a different size of the Gaussians and different number of Gaussians in different levels?
So basically, we have to model, a distribution of different object sizes, right? So basically, in our initial representation, we can define different ranges for the Gaussian blocks, because we have the Gaussian attributes for us to decide the shapes of the different Gaussian blobs. So we can decide different ranges for the initial Gaussian representations. And then during the optimization, we can further optimize for each level of the Gaussian representation.
So it's more like we initialize the kind of larger and the sparse Gaussians first, and then by the time of the optimization, we further refine those Gaussians.
Yes, so we have an initial definition of the scales in a pyramid level, and then during the optimization, we can further optimize the Gaussian blob scales. Yeah.
So it's happening by the time. So initially we have like larger and kind of like more blurry, and then by the time of optimization we get more refined.
Yes, exactly, yes. So because we have, multi-scale representations, all the attributes can be optimized together during the optimization. So finally, we can have pyramid structures for the Gaussian representations. And this is very important for us to render views from different angles. Yeah.
Any other questions? Actually, I have a question. In painting and for the 3D in painting, have you ever tried with that? And if there are some obstacles and you want to run the 3D scene and 3D in painting, I saw the 2D images. Yes, and
yeah. So the in painting is done in 3D space.
okay.
So we are not doing a 2D editing task.
Okay.
So basically, we still optimize a 3D scene representation based on Gaussian splatting. So we have explicit 3D Gaussian blobs in the 3D space.
Okay.
So when we remove one object, so we remove the Gaussian blobs that belong to that specific object. So in the in-painting, basically we want to recover the occluded region, the background region. In that case, basically we have to incorporate information from the local context. We pass messages, pass information from the local Gaussian blobs for the in-painting. This is directly done in 3D. And for the 2D level, we can also do in-painting for the 2D images because we can mask out one specific object region. Then we can use, for example, a 2D in-painting model to obtain an in-painted 2D image. This would also back-propagate supervision for us to supervise the bidirectional 3D attention mechanism for us to incorporate information from the local context to finish the 3D in-painting directly. Yeah.
Okay. And for the time performance, and what about 3D in painting? Will that slow down the splatting process?
Yes. Basically, for the optimization, it's a bit time consuming. It's a common issue for for the 3D Gaussian for the optimization stage. But if the optimization is finished, so basically the rendering speed is very fast.
Sure.
It's very fast. We can achieve a real time rendering speed, which can satisfy any real applications, I think. Yeah.
Okay. Yeah. Any other questions? Okay.
Yeah. Yeah.
Hi, very impressive work. I'm wondering, how are you handling estimating depth of very distant objects, especially when you have those aerial views? Do you have something that is a few kilometers away?
So which project you're mentioning?
That I was studying on the
The straightforward one,
yeah,
from single view to 3D sim modeling.
Right. Some
Yeah.
of the kind of urban scenes reconstruction from aerial views.
Yeah.
If you have objects that are very distant, how are you estimating the depth out of it?
Oh yeah, that's a very good question. Yeah. So that's why we want to replace the code map initialization. If we just directly utilize the code map initialization, it's very challenging for us to obtain, the points far away from the camera viewpoint. But if you consider the incident GP as our initialization strategy, so we can actually recover the points that are far away from the camera viewpoint. This can improve this perspective. Yeah.
Right.
Yeah.
So my question is, how is that estimating the 3D depth out of it with very little, I guess, baseline?
So for the large scale sim modeling, currently we don't quantitatively evaluate the geometry structures because we don't have a benchmark that provide us, the quantitative, evaluation metrics and also ground truth data for us to perform such an evaluation. So we are not able to provide, exact, quantitative evaluation for the points that are very far away from the camera point. But from our qualitative results, we can still observe that the model can still render, the points that are very far away from the camera point. That means we can still generate reasonably good results for the points that are far away from the camera. Yeah. Yeah. Yeah.
Okay. If no further questions, thank you very much, Dr. Xu. Then let hi Ankit. Can you try to share your screen? You are muted.
Are you able to see the screen?
Yes, we are able to see the screen. Let me first introduce you and then get started with talk. So it's really our great pleasure to have Dr. Ankit Bera to give us the talk, and he is currently an associate professor in the computer science department in Purdue University, and he's also a John professor at University of Maryland at College Park. And he was also a research assistant professor at University of Carolina at Chapman Hill, and he received his PhD from North Carolina at Chapman Hill, and he's also the founder of a company called Project Dust. And he's currently serving as senior editor of IEEE robotics and automation letters, and in the area of planning and simulation. And he's also conference chair for ACM CGRAPH conference on motion, interaction, and games, and in 2022. Okay, Dr. Barrett, you can go ahead with your talk.
Thank you so much for the introduction. I just want to verify if you guys can hear me.
Yeah, we can hear you very well.
Okay, perfect. Thank you. I first thank the organizers for inviting me to this talk. I also apologize that we have a medical issue at home, and actually in literally 30 minutes we have to leave for our doctor's appointment. But I figured that at least I can spend some time discussing some of the research we have been doing in this space. So good morning, or almost good afternoon, I guess, to whosoever is listening wherever they are. I'm honored to speak today at the CVPR workshop on visual odometry and location-based visual applications. As was introduced, I am Aniket Bera. I primarily work in the intersection of robotics and vision with some graphics application, particularly looking at visual odometry from a more extended SLAM and semantic understanding sort of space, so where robots and the real world interact with each other. So let's start with visual odometry, sort of the theme of this workshop. So the core capability of extending or estimating ego motion from camera inputs. And this expands across layers in real-time SLAM, semantic understanding, and even some recent works on neural generative modeling. Through several of recent systems that we have developed in our lab, I'll show how this space is just the beginning of sort of the broader story about spatial intelligence, understanding where we are, what's around us, what the environment looks like, and even what is partially observed or ambiguous. This talk is meant to be sort of a broad spectrum talk of some of the papers, and the papers are mentioned in the talks, in the slides themselves. I highly encourage you guys to read some of those papers. I will be available to chat maybe sometime later during the conference over emails or video calls. I may not be able to stay a lot longer after the talk for questions. But each system in this talk builds on visual odometry as a foundation, and then it sort of introduces new directions of semantic grounding, physics-derived understanding, physical structure, and eventually some 3D generative understanding. So let's begin by grounding the discussion with real-world examples of where these visual odometry and location cues are critical for intelligent systems. And I'm pretty sure most this workshop has been happening for quite some time, and most of you are aware. But just to sort of cover all blocks, think of an autonomous car weaving through traffic in downtown setting. It needs to understand or estimate its motion precisely and continuously, even though it encounters things like reflections, occlusion, sensor noise. In applications like augmented reality, virtual reality, visual odometry ensures that your digital version overlays stay fixed to your real world position. Even a slight drift can destroy that experience. For drones, especially in, let's say, GPS denied or cluttered environments like forest or disaster zones, these visual odometry or VOs is often the only way to estimate motion. And in indoor collaborative spaces like warehouses, hospitals, homes, robots rely on visual motion cues to understand their position relative to people and objects. So these are not toy problems. These are high stakes, real world challenges that motivate all systems, which we'll see in this talk. So to address this challenge, let's break down the problem into some of the very recent work we have been doing. So a lot of our previous work has focused on building high precision SLAM-based models or understanding the visual odometry of space. In more of the recent work we have done, we are trying to bridge things like large language models, trying to bridge visual intelligent, visual language models in the space, and try to define problems that make up for robust spatial perception, but also go beyond perception into understanding. So to make sense of complex environments, intelligent systems need to solve several core subproblems. So it starts with visual odometry, which is estimating the motion from raw RGB or RGBD streams. VO alone enables short-term navigation, but we also want consistency and memory, and that's where SLAM comes in. So building and updated 3D maps. Next, we need to go beyond the geometry. Semantic mapping integrates object and scene understanding, localizing known objects in space. This is key for interaction, grounding, and reasoning. But often, we only see a part of the world. Reconstruction systems often aim to complete this picture, filling in geometry and refining structure, especially noisy or partial data sets. Finally, with some of the more modern generative 3D understanding, allows us to predict missing parts of the picture, missing parts of the scene, learning priors over geometry to generate plausible completions just from a very sparse views. So today's talk will be touching on these in each of these levels through a lens of recently developed systems in the Ideas Lab. Let's start with our first layer, which is the real-time SLAM in dense and scalable representations. So one of our recent work, which we call Flash SLAM, where we developed an approach to tackle two of the hardest problems in SLAM. So tracking under sparse or fast-changing conditions, and robustness to sensor and noisy sensors. So conventional SLAM approaches or systems typically assume slow motion, or they rely on dense photometric cues, or they heavily are dependent on expensive optimization. These assumptions break down in real-world use. Imagine that your robot takes sharp turns, or the lighting changes, or when low-quality sensors are available. So we built, which we call Flash SLAM, which is designed to be fast, efficient, and precise. In some degrees, obviously. So it does this by combining learning-based matching systems with novel scene representations, which you guys are aware, called 3D Gaussian splatting. We already have seen some interesting research in that space just in the talk before me. So now in this work, instead of optimizing poses by comparing raw pixel intensities, we match features across frames and track the motion based on geometric correspondences. This changes things in terms of speed and robustness. Again, I don't want to go too much into the depth of these papers. We have the paper mentioned in the slide itself. I highly recommend people to read this. So with this approach, with FlashLAM, we achieve real-time performance with even tough conditions, especially suited for edge devices like drones, AR headsets, and mobile robots. So let's look at how the pose tracking actually works. So the core idea of the pose tracking is we use SuperPoint to extract 2D key points from each RGB image, robust to lighting, viewpoint, and texture variation. Then we use something which is called light glow. Some of you may be aware of this work, a high precision transformer-based matcher to find a correspondent between frames. And using the RGBD input, we back project these 2D matches into 3D space, creating 2-point clouds, one for the current frame and one for the previous. Now, to estimate the motion between them, we use a fast rigid transformation method by solving a Procutus alignment problem. This gives us a high quality pose without requiring iterative rendering or photometric losses. Importantly, this whole process runs under 80 milliseconds with on-edge hardware. Compared to traditional LUF-based LAM systems that can typically take upwards of 1 second per frame. So let's look at how we represent this environment using GS in an efficient and flexible alternatives to meshes and voxels. So instead of storing maps as voxel grids or meshes, as you heard, we use 3D GS. Probabilistic primitives that represent both geometry as well as appearance. So each splat is parameterized by a 3D center, covariance matrix, color and opacity that naturally blend into each other. At the same time, they are differentiable and can be updated online. This makes them a perfect resource for streaming a SLAM pipeline. As new data comes in, we add and refine these splats, incrementally improving the map. We also use adaptive sampling strategies to focus computational effort on visually important regions like object boundaries or thin structures, which improves rendering fidelity without wasting resources. So let's look at some of the quick results of FlashLAM. So again, we have videos on our website. I highly encourage you guys to see them. We evaluated this across multiple data sets. On Replica, which is a very popular data set in the space, we achieved sub-centimeter tracking accuracy, even under large camera displacement and sparse inputs. In terms of visual quality, we outperformed prior methods like SplatAm and GS-SPLAM in both reconstruction sharpness as well as perceptual similarity. More importantly, our system maintains this accuracy while running significantly faster. With fewer tracking iterations and efficient splat updates, we hit about 10 to 15 frames per second, even on fairly modest hardware. So this goes beyond our use case in field robotics to even applications in AR and VR. So this sort of space kind of covers geometry and tracking. But what if we want a system to recognize and query objects in the space? So this brings us to our next system, which we call GoSlam. Now that you have seen a system that where we can trap and reconstruct a scene geometrically, let's go one step further. Let's try to build these SLAM models by understanding what is actually in that scene. So most SLAM scenes, in most of these SLAM systems, the world is just a cloud of points, or in our case, splats. But humans and robots in real-world environments need a lot more. We look at objects. We need semantics. So GoSlam is our system designed to solve this aspect. So it augments the SLAM pipeline with rich object-centric representations and semantic priors. Instead of just building maps, GoSlam identifies and grounds and tracks objects, allowing interaction and question answering. So we start by, so our approach GoSlam starts by running 2D instant segmentation on RGB frames, something like mask-to-former or SAM. From these detections, we lift object instances into 3D using associated depth and estimated camera poses. This gives us 3D bounding boxes and centroids, effectively grounding the objects in the SLAM world model. Each object is stored with its label, shape, and position, and crucially becomes part of the SLAM graph. This means that we can now reason things like where is the chair or how far is the bookshelf directly from the scene representation. This persistent object tracking is especially useful in long-term operation or multi-agent settings. Now, how do we use these grounded objects for reasoning and interaction? With grounded object anchors, our approach GoSlam allows interactive queries both from users as well as high-level task modules. So you can ask questions like, where is the backpack? And our system will identify the backpack, estimates its position, and resolves ambiguities across different frames. So this type of multimodal understanding, fusing vision, geometry, and language is critical for embodied agents. We have integrated this into manipulation pipelines as well. So we have built a bunch of these different robots which can not only navigate, but also have the ability to manipulate the environment and find and resolve these discrepancies between different frames. The ability to reason about occluded or even previously seen objects enables things like replanning, goal setting, and a more natural communication. So let's kind of look into how GoSlam's performance works and how does it work across different real-world scenes and objects. So we benchmark GoSlam across multiple standard data sets. We have the ScanNet++, Replica, and the Habitat Matterport 3D. We measured both the geometric accuracy, such as tracking drift over long sequences, semantic accuracy, things like object recall, precision, and we'll look into that in the next slide. So GoSlam consistently maintains a very low geometric drift while correctly recognizing and tracking 3D objects with high fidelity. So it performs semantic mapping baselines like semantic fusion and even outpaces some of the offline reconstructed methods in object association. So here are some of the examples, some of the results of our approach. So when we look at the comparison metrics based on PSNR, SSIM, and LPRPS metrics across different scenes, we see that our approaches are either the best across all of these metrics, especially in the PSNR and the IPS metrics, but at least if not the second best in most of these cases. We also have a tracking accuracy on the big replica data set, which I'm sure many of you are aware. We are trying to measure the absolute trajectory error in centimeters. And again, our method is either the top performing method or second in line in these approaches. Similarly, and this basic, so I forgot to mention this combines the two approaches you've seen, the FlashSlam and the GoSlam, and the approach is a combination of these. So we also do some, and I've been talking about how our method is very useful for sparse data sets. So we also did a lot of ablation studies, a lot of testing in particularly sparse settings. And we found out that in different data sets, specifically in the sparse setting, our method outperforms almost all other approaches out there in two different data sets, and two different relevant data sets in this space, always being invariantly number one in that space. So sort of to summarize, and I want to leave you with these four key takeaways. When we first introduced FlashSlam, a real world, so we first sort of designed this first FlashSlam, a real-time feature matching SLAM-based approaches with Gaussian splatting, ideal for fast motion and sparse views. To sort of complement that, we also built GoSlam, which extends the SLAM pipeline into semantic reasoning and as well as object-centric understanding of the space. Again, beyond the scope of this talk, but these systems, we combine and we show some results, combine into a unified framework that supports both high-quality mapping and interactive and embodied intelligence. And fourth, the overall system has been deployed and is deployable across many other real-world uses, from drones to augmented reality and even multi-agent robotics. So our approaches have been used in quadrupeds in an indoor setting, but obviously we can go in different outdoor settings, but our results would not be as good as they are in specifically indoor settings, where light changes are somewhat constrained and your environment representation is somewhat more structured than doing it outdoors. So now we've seen what SplashSlam and GoSlam can do in terms of solving some of these real-time geometry and object level SLAM challenges. These systems are fast, reactive, able to track and understand scenes semantically. However, when we move to more larger environments, entire buildings, as I was talking about, outdoor campuses, city blocks, purely visual SLAM begins to show its limitation. The range is limited, details are missing, and surfaces are incomplete or noisy. In this kind of space, we look at LiDAR as one of the more essential aspects of it. But raw LiDAR is also can be sparse and irregular, and traditional reconstruction methods often miss structural continuity. In this space, we introduce something which we call Hessian Forge, a system that uses output from SLAM to bootstrap a physics-informed neural reconstruction pipeline using LiDAR data. This creates globally smooth, complete, and accurate 3D environments. So in effect, this slide sort of marks the transition from what you've seen before in the SLAM-based method to structure level modeling using LiDAR and neural fields. So let's turn to a complementary challenge in visual localization. Reconstructing large environments from sparse and noisy LiDAR scans. As many applications like autonomous driving, drone navigation, infrastructure inspection, we rely on LiDAR data for its robustness to lighting and long-range accuracy. But at the same time, LiDAR also comes with significant trade-offs. It's sparse, unevenly sampled, and often very noisy. Traditional reconstruction pipelines either over-smooth the data or fail to generalize across, with varying density. And moreover, most are not aware of the physical plausibility of the surfaces, so leading to jagged or inconsistent surfaces. So Hessian Forge is our approach to address this challenge, which combines physics-informed neural representations with LiDAR input and a new smoothness energy that penalizes implausible curvature of surfaces. This allows us to reconstruct large scenes with high fidelity while still maintaining scalability and generalizability. So we have a separate talk on Hessian Forge at CVPR. I highly encourage you guys to look for this particular talk. My student is presenting at one of the other workshops, and with more details on the math and the background on the physics approached. So at the heart of, and I'll try to implicitly simplify this whole pipeline, at the heart of Hessian Forge is a neural implicit model, specifically an SDF network, like a signed distance function network. This network learns to map any 3D point in space to a scalar. It's signed distance from its closest surface, again, indicating what the point is inside or outside. So this representation is expressive and continuous and allows for differentiable rendering and reconstruction. But simply fitting an SDF to noisy LiDAR data is not enough. It could be irregular and fragmented. For our approach, this physics-inspired smoothness prior, we introduced a curvature-based regularizer derived from the Hessian of the SDF. So it penalizes the surface roughness and enforces curvature continuity across the surface. This encourages physically realistic surface. Flat surfaces remain flat. Corners remain sharp. Smooth remains smooth, and noise is suppressed without over smoothing, which is very common in many of past approaches. Again, the paper is mentioned on the slide. I highly encourage you to guys look it up online and get more details. To make this practical for citywide reconstruction, as you can know, these things can be fairly compute intensive. We need scalability. So dense voxel grids are very memory intensive and slow down to optimize, very slow to optimize. Instead, we discretize the domain by using adaptive tetrahedral meshes, which naturally conform to the geometry of the environment. During training, this SDF is queried at the tetrahedral nodes and gradient flow efficiently through the entire volume. The adaptive sampling ensures that we focus more resolution in high curvature regions like object boundaries and edges while keeping things sparse elsewhere. So this helps us train models which are much larger without exploding in memory or runtime. In fact, our optimization converges 3x faster than prior neural field based approaches like NGLOD or ISDF, while also producing better surface quality. So we benchmarked Hessian Forge across standard autonomous driving datasets like Kitty and semantic Kitty, as well as our in-house urban scene 3D. Across the board, we see up to 2x improvements in the chamfer distance and F-score compared to the NGLOD and the ISDF baselines. But I guess what is more interesting is the qualitative fidelity. Curved edges, corners, thin signposts, they are all retained in our reconstruction. This matters for HD map generation, path planning, and inspection. Robots navigating in these maps can trust the geometry, and downstream modules can use them for semantic understanding or surface interaction. So to sort of end this particular segment, while FlashSlam and GhostSlam and all these methods are designed for real-time tracking and semantic scene understanding, Hessian Forge complements them as a powerful offline refinement step. Imagine running SLAM across campus and a city block, collecting sparse LiDAR maps, and then using our Hessian Forge to convert these sparse maps into globally consistent watertight meshes with high geometric fidelity and physical plausibility. Again, this kind of workflow, I believe, is ideal for creating things like digital twins, validating environments before deployment, or running long horizon planning. It sort of completes the loop from online SLAM to detailed reconstruction, which is, I believe, the backbone of spatial intelligence. I have 5 minutes to end, so I promise I won't take too much time. Also, I have a medical appointment, so I promise to be on time. So let's look at our last segment, where again, this is an ongoing work, so I don't have a lot of results to show in the space. We have seen what SLAM systems can do based on dense point cloud representations, tracking geometry in real time. We looked at semantic understanding, object awareness with GhostSlam. With Hessian Forge, we looked at neural implicit representations, modeling large-scale scenes from LiDAR and physics-inspired losses. But there's a natural next step. Instead of modeling surfaces directly from sensor data, can we go one step further? And this is where it gets tricky. Can we synthesize plausible 3D geometry from very sparse views, or even just a few camera angles, perhaps using some very powerful generative approaches? This is where our next work, Part Diffuse 3D, comes in. It is a bridge between geometric modeling to generative reconstruction. So let's take a look. So with this general motivation in mind, let me introduce you to the challenge where we are trying to do sparse reconstruction in the wild. So a recurring challenge in 3D world, real world 3D perception is working with incomplete or very sparse visual coverage, whether it's a drone flying over a building, a mobile robot with limited field of view, or surveillance system with partial occlusions. The reality is that dense, uniform multi-view capture is rarely available. Most learning-based approaches for 3D reconstruction or generation assumed you have 8 or 16 well-aligned views at the bare minimum. What if you have just 2 or 3? Or if your views come from unknown or non-uniform trajectories? That is the motivation behind this ongoing work, where we aim to enable efficient, scalable, and high-fidelity understanding even with limited disjoint views when they're available. So the core idea of this space is to break down the input space into smaller view partitions. Each partition is treated as a potentially independent and incomplete observation of the object or scene. We then use a novel diffusion model that learns to condition generation based on these parts, creating plausible completions from each partition's viewpoint. Once we have these part-based samples, we fuse them together into a learned latent space to produce coherent, high-resolution 3D geometry. So again, this is an ongoing work, and because this is a very interesting workshop, and I'm hoping people are interested in the space, I just wanted to introduce this to you. If you're interested in working in this space, please reach out to me, and I'll be more than happy to collaborate in this space. So we tested, our ongoing initial tests are on some standard sparse view data sets, like the most standard ones like ShapeNet or OmniObject 3D. With only 2 or 3 views, our method outperforms strong baselines like Vision Nerf or Sparse Fusion and many 3D Gaussian or the latest 3D Gaussian based methods. The reconstructions are smoother, semantically meaningful, better coverage. This has major implications, again, where cameras are limited, warehouse settings, AR, VR, not just for images, but for unifying views in 3D structures. So I just want to conclude to take a step back and reflect what we have seen. We looked at a lot of different applications in the SLAM-based world, in limited setting, in a household setting, in a constrained setting. We looked at when we go outdoors, when we use LiDAR-like inputs, how do we use physics-informed neural methods to do scalable real-time mapping using Hessian Ford. And we wanted to push the boundary even further and go where things are not even visible, or the input we have are disjoint, to look into generative approaches to fill in the gaps, to have a somewhat reasonable approach. So where do we all go from this? So let's close with some open questions and some forward-looking thoughts in this space. The community as a whole, I feel, has made a lot of real progress in this space, but many questions remain. Can we build a single system that performs visual odometry, maintains semantic maps, understands semantic geometry, and somewhat hallucinates in a like the word hallucinate has a lot of negative connotation, but I feel if we can hallucinate to the point that it is low stakes enough for some robotics applications, some vision applications, but do all of that in real time, what does even evaluation for long horizon uncertain perception tasks look like? As you can see, more and more of these foundation models begin to dominate vision and language. What might vision and spatial foundation models sort of look like? And perhaps something which is more exciting to me is that can SLAM itself evolve into a generative, context-aware process that synthesizes plausible worlds in real time? So these are the questions which we keep on asking I would say, at the frontiers of spatial intelligence. And I would really look forward to working with many of you. I really apologize that I could not be there in person. I would love to have discuss many of these. To conclude, many of our work in the space has won awards at top graphics, VR, and AR and robotics conferences. One of our work was recently nominated at ICRA 2025, which was just a couple of weeks ago, as one of the best papers in planning using some of these approaches. And I want to thank all my collaborators and my students, without whom none of these work would have been possible. And last but not least, I would like to thank my funding agencies for believing in our research and paying the bills. So thank you so much. This is my email. I would love to take questions over email. I know I have to leave right now for my appointment, but thank you so much for inviting. And I apologize again. But thank you, Chris.
Okay, thank you very much, Dr. Farrell. And I know you need to leave. And feel free to leave questions on YouTube channel and as well as the email and provided here. Okay. Yeah, thank you. And I hope your web can get better.
Thank you so much. Thank you so much. I hope so too. I hope so too. Thank you. Bye.
The next speaker, I see he's here already.
How about now? I think I'm muted myself.
Maybe also use can you turn on your camera as well?
Oh, sure. Well, I would need to restart the Zoom, so let me just keep it going. So this is the city, and actually, like there are we have basically we built entire city, and like we have a little bit of different phases and areas of these like plans. But the point here is because we build city, for example, like we have entire like a digital twin of the city. And the aim for the city is like we support innovators, inventors, researchers like you or developers to collaborate and try your new ideas. And also we try new ideas. Some recent works, not even camera things, but also this one is like we co-host the workshops this year's ICCV or last year's CVPR. This work is about like a data set, traffic safety data set. So as you can see, we collect data set of near accident scenarios. And we host a competition of analyze these videos. Understanding like video understanding analysis. Another work that we do and we present this Friday, the main conference is 3D gaze estimation. So for this one, we analyze, we set up the outside in camera, like third-person view cameras, and analyze the 3D gaze estimation. So if you are interested in, please reach out or check the posters. Moving on to the event camera stuff, I know you may know already, but let me start from this one. So imagine that we have HD resolution camera, so like this resolution and 60 FPS. Then the data volume, data bandwidth will be like 1.3 gigabit per second. But if we actually estimate the rough bandwidth of human retinal ganglion cells, then it's going to be like 8.7 megabit per second. So how do we humans or how do animals achieve this like low data bandwidth or data efficiency? Is actually sensing only changes. And this is where the event camera idea or event camera's idea came in actually basically. So this is a scene like capturing me like playing a football. And on the left side, like I'm showing like frame-based cameras. Of course, this is like 30 frames per second or something like that. Basically still images, like sequence of images. And this is synchronous frames. And event cameras, in contrast, just respond to changes. And what is changing in this scene? It's like bulb or the person. So this is asynchronous, and due to this asynchronicity, it achieves like 100 times or 1,000 times higher temporal resolution. And like a lower power consumption. It actually depends on the scene, but when the scene is not moving, then it's very like a high power efficient. And also like data efficiency is also very high. And because this also just detect changes, so dynamic range is quite big. A little bit summary of industrial academia evolution of this field. On the left side, I'm just plotting the pixel pitch and comparing with CMOS frame-based sensors. Then as you see, of course, frame-based cameras has a very small pixel pitch and high field factors. But event cameras manufacturing also like following this trend more or less. And we are getting more and more higher resolution cameras. And in conferences, we have like more and more number of papers. And actually, we have dedicated workshop tomorrow, which I also will talk there. But if you are interested, please visit tomorrow. And my supervisor, PhD, is organizing it. A little bit, let me give you a little bit of example motion estimation, because this is a workshop of VR and so on, SLAM and so on. So actual event data is like this one, and event data is like input tuples consisting of x, y, tp. X, y is like image coordinates in the image plane, and t is timestamp, and p is polarity, plus or minus negative positive of the changes. How can we estimate, for example, optical flow from there? Optical flow is actually a little bit like what we propose in this work is a little bit like different from optical flow in traditional frame-based concept. So when looking at the frame-based optical flow, then basically we have frames at t timestamp t1 and frames at t timestamp t2. And the optical flow is a function of x, like optical flow is a function of pixel coordinate. And this is like pixel displacement between two timestamps. But event data, when we look at event data, then like the timestamps is more kind of continuous because it's asynchronous and 1,000 times faster. So what we propose in this work is basically like optical flow can be characterized as a pixel trajectories, which is a function of space-time. So not just like a pixel coordinate, but also timestamp. And this is going to be a trajectories in this 3 space-time volume. Then how do we estimate it? Like when look at like very 2 instantaneous moments in this like space-time volume, then we see kind of like a edge-like features like a car here. So if I define like reference time at the beginning, the first timestamp, and like some target timestamp event like here, then the edges coming from the edge events from coming from the car moves along the space-time trajectory. So it's kind of like a matching problem between the 2 timestamps. So when I estimate like an optical flow, then I should be able to warp these event coordinates, like XY coordinates of events into the reference time. Then I should be able to like get like a goodness of matching via blurriness or sharpness of image of the events. So this is like an example of wrong flow estimation. Like this is like a toy example. When the wrong flow estimation is going to the right, then like this flow is wrong. But when I get the correct flow estimation, then to the left in this case, then I should be able to match these like 2 kind of edgy structures to each other. As a result, I should be able to get sharp image of buff events. So this is like a brief idea explanation of how we cast the problem of optical flow estimation into the optimization based on the contrast of the image. So here, this is like no ML here. Of course, like we have ML works based on these kind of ideas, but I'm trying to communicate the basic idea because maybe this is not familiar. But on the left side, like we have candidate flow, and like I run just optimization based on Newton conjugate gradient, based on patch of images. And then like this, while I'm seeing the convergence of optical flow, then I should be able to get the sharp warped events, like converging to sharper and sharper edges. So actually, this is called contrast maximization method, which focuses on image contrast as an objective function to estimate motion. Of course, when I estimate optical flow, then I should be able to recover ego motion and depth if the scene is static. So this is like an example data of the camera moving on the drone data set. Then I should be more or less like estimate the correct like ego motion. Or even for the stereo setup. So this is like a car mounted on, camera mounted on car and stereo camera, and on the left and right cameras. And I can estimate the depth and optical flow for each cameras. Okay, so this is like a general, more like general optical flow, ego motion, depth estimation, this kind of a method based on the one like a contrast maximization. But let me move on to another topic which we are currently working on. This is marker-based real-world localization applications. And let me clear a little bit like the topic here. So local communication using QR code AR markers. Like, of course, we use payment barcode or robot localization like QR code. And if you have a Roomba, iRobot Roomba, then you see like this barcode is like put it on the home dock of the Roomba to localize, to help localize the robot. So actually, this kind of like QR code marker-based localizing communication happens a lot. Even like we have this widespread internet, but like localization based on location clues or like based on physical entities happens a lot. Looking to the other like opposite of the idea, there is this idea of visible light communication. And what is this? VLC is a wireless communication based on modulation of visible lights like LEDs at high frequency. So looking at this is the night scene of the Tokyo. But like you can imagine, if every light is sending some sort of signals or information, then I should be able to get like some touristic information, like Tokyo Towers, today's vacancy of the tickets, 10. Or of course, I should be able to localize the camera based on the relative location of like different IDs, different light signals. And this kind of idea has been around like for more than 20 years or something. And there have been several protocols, proposals and so on, like for data, such as like using just blink or like intervals of the blink to encode binary data. And of course, needless to say, but let me just emphasize, we have lots of data in our daily lives, like street light on the road or traffic light. Maybe we can send some signals based on the traffic light or help detection on the traffic light. Or exit sign, emergency exit sign, then we should be able to use it as a rectangle. So it should be able to use to localize camera. Or factories, so to monitor the factory lanes. Or cars or ships to do this like a peer-to-peer communication, even under like no internet signals. So I want to mention that VOC has huge potentials of wireless communication and localization without affecting RF-based like Wi-Fi is congested or like that. But I mentioned like 20 years before, like there has been existing these ideas, but why it is not popular? So there has been a challenge in the VOC receiver side, sensor side actually. So when thinking about the receiver of the light communication, then two factors are very important. The first one is temporal resolution. And this affects the data bandwidth, how much data you can send per second. And the spatial resolution, the second one, which is important to avoid signal contamination and also, of course, localization. And normal photodiodes have a high temporal resolution, but very low spatial resolution. So this doesn't satisfy. Frame cameras, the opposite, like a high spatial resolution up to like 10 million megapixel, 10 million megapixel, but low temporal resolution, like 30 to 60 FPS. Actually, event cameras can be a very good fit because it can provide like both high temporal and spatial resolutions. And that's why we focus on investigating communication localized performance with event cameras and VLC. So for this VLC with event cameras, let me introduce three key components here recently that we published. The first one is we propose a dataset with mobile mounted event cameras. And the second one is we propose an encoding method with car-mounted event cameras. And the third one is our validation in outdoor real-world environment with actual illumination products. The first one is dataset. Research program here, I'm not going to very detail, but like let me briefly cover. The research statement here is like there's no actually public dataset focusing on event-based VLC that is necessary for benchmarking, improving algorithms of detection and localization. So we actually released the first public dataset EVLC consisting of synchronized frames, events, and motion captures on various recording scenes. So actually I have transmitted a toy example here today. And this is an LED board that I'm using in this paper. And this is just like a light, just lighting to human eyes. But this LED is flickering at 5 kHz and sending the signal, in this case, 7. So like binary data is sending the 7. We prepare like a bunch of these LEDs and like put these LEDs on the daily objects and also like AR markers printed on like A1 size, like this size. Entire signal can be sent within like a few milliseconds. So this is very fast and like low latency. And as a protocol, this is like tiny details, but we use like interval based to encode like 0 and 1 differently. As a receiver, we built this custom-made like a mobile receiver, and this consists of a tablet and frame camera and event camera on top of it. And both these cameras are connected, synchronized from this trigger box on the behind. And actually this synchronization trigger box synchronizes these two cameras, but not just two cameras, but sends signal to the motion capture in this case, like OptiTrack, and so that we can get the ground truth poses. On the right, I'm showing the example data captured in outdoor scene, the event camera data and frame camera data on top. And we also annotate LED in this data set. So it's you can see like 21, 37, these like numbers are different LEDs that we annotate. And GT pose is also from the external motion capture. And we record a diverse data set actually on different motion patterns, like a translational motion or rotational motion, like a ranging distance, scene brightness, and camera sensitivity. This is a detail, but you can check in the paper. And also, not at least, but we propose to improve localization accuracy using the motion estimation method that I explained in the first part of my presentation actually. So when looking at LEDs and the camera is moving, LEDs is always static and the camera is moving, then there should be always like some small displacement in the pixels of this LED in the camera plane. So we estimate the motion and compensate this like a displacement to get the sub-pixel accuracy of the LED pixel location to improve the decoding and localization accuracies. Just very brief introduction of the result, but basically this figure shows the comparison between frame and event, and under different luminance of the scene. And of course, frame camera cannot detect markers under dark scenes, but event cameras are high dynamic range, and LED doesn't suffer from the scene luminance. So based on this LED-based, event camera-based localization, event camera can detect at larger distances, more than 10 meters distance than frames, regardless of scene brightness. And even I compared just like for this, like just a very close 4 meters distant, then event cameras offer better detection rate, like 4 times better detection rate and comparable localization accuracy. Like this is like a few centimeter worse than frames, but this is actually for room for improvement using our data set and benchmark in the future. This was using a mobile mounted event cameras, but another work that we have done recently and published is exploring new protocols. And actually, so what is robust protocol when the camera receiver moves quickly, such as on vehicles? Like vehicles, of course, move much faster than the mobile phones. So for this work, we propose a new protocol using Walsh-Adama encoding, and like we tested until like 50 kilometers per hour. And this is a collaboration with Toyota Motor Corporation. Not going to the detail, but just a brief idea of this, how this works is like we use the Walsh-Adama matrix, which is like a orthogonal metric, which has like a very high autocorrelation. So this makes a decoding algorithm or detection algorithm to make it very easy and robust to recover the original signal of binaries, 1 and -1s. And as a result, like for static scene and dynamic scenes, we confirm like error-free communication, like up to like 50 meters and 40 meters. This is more like a communication field research, I would say. And the last not least, the interesting point is we validate the entire system in outdoor environment in the real world settings with illumination. So on this photo, I showed the illumination product that we can purchase with the exact same microcontroller that I showed you, this one. And illumination spec is something like that. And we installed this illumination in the outdoor environment so that I can test like more signals in the real world, real city settings. And actually, of course, this depends on the luminance of the illumination, but communication more than like 100 meters are confirmed. Paper information related to these things are here, just to recap. And the summary of the presentation today. So I introduced the company and like some ongoing research, like a data set, like a traffic safety data set and 3D gaze estimation at the beginning. And also I introduced the event cameras and some motion estimation methods. And finally, localization based on visible light communication. So like dataset and encoding method and large-scale real-world experiments. We look for collaboration if you are find this one interesting. So please let us know or please reach out to us. Thank you very much.
Okay. Any questions? So for the I may have a question. And for the indoor and outdoor UV, you coupled with LED and as well as event camera. And what about the room is totally dark? In that case, does this work?
Room?
Totally dark for the room in the room or outdoor environment, and there's no lighting.
That should work because the LED itself is like sending the
light result.
Yes.
Okay.
So actually it should work.
So have you verified with that?
I verified until like a 10 lux or something.
Okay.
So not like super precise dark, but
Okay.
it's very dark.
Yeah, I know sometimes if for event camera, sometimes if that is very, very dark or no light and it doesn't really work well. But LED, and I was thinking maybe that can solve this problem, right?
It is known that even the camera is a little bit like prone to noise under dark conditions. But for this our setting, we focus on the light signals, which is very like distinctive from the normal noisy events. So it's very easy to recover and like robustly communicate sending signals.
Okay, cool.
Sure. Hi, I'm working with event cameras as well, and I was interested in the application that you showed with the localization of the active markers. So you said you use PMP, calculating the pose. Do you encode some IDs into the markers that you read and use?
Yes. So like for example, like when I have 4 LEDs encoding different IDs, then I should be able to like recover the pose.
So these IDs are encoded and the camera is using these.
Yes, I'm currently just encoding IDs, but it should be extensible to encode further information, like just more dynamic or like just like coordinate itself of the LEDs.
Let's think about this. So
Yes, that's definitely the way, like an interesting way to go.
Okay, thank you.
Thank you.
So thanks for the interesting talk. And then I have a question about the application of the event camera. So you show some example of the VCL, but I'm wondering, like what is the kind of future direction for the event? For example, like autonomous driving or those kind of things. Do you think there's a large potential of the event camera?
The short answer is actually in the tomorrow's workshop, probably there's kind of discussion, lots of to be happened. Different companies, different research groups are working on different applications, like including mobile phone or AR, VR glasses, cars, or like that. For this project, we are focusing on this like VLC part. Yeah.
There are many visible you're focusing.
Yeah.
Okay. Thank you.
Thank you.
Okay. Any other questions? Okay, if no further questions, let's have the speaker. So yes. Okay. So Dr. Ango, are you here? Okay. Okay, I can see.
Yeah.
Can you try to share your screen and see whether it works?
Sure. First, are you able to hear me at all? This is as loud as I can speak.
Okay. Okay. The sound is a little bit weak and can you,
I'll turn off my, I've turned up my microphone. Does that help?
now it's better. Now it's a little bit better.
It's
When
better?
the closer to your mouth, it's a little bit better.
Okay. It's, let me know if it's too, it's their lunch break, so it should be quieter, but, I'm not the only person in this space.
Okay, sure. Okay, let me introduce Dr. Brina Ago, and she is the professor in mechanical engineering and computer science at Northwestern University. And she's the founder and the director of CCIV and Rehabilitation Robotics Lab, and as well as the Shirley Run Ability Lab, and formerly the Rehabilitation Institute of Chicago, the #1 ranked hospital and for rehabilitation in the United States. And she has received many awards, and currently she's a fellow of American Institute for Medical and Biomedical Engineering, and she has received NSF Career, and in 2016, one of the 40 under 40 by Green in Chicago Business. And she has received her PhD in robotics from CMU and as well as mathematics. And she was a visiting fellow at EPFL as well. And one thing I want to especially mention is Dr. Agong is very sick today, and actually, and her throat is very has quite a lot of pain right now, and I'm really very grateful that you could still take your time and to speak and under your sickness. Hopefully you can get better, and the shock will be a little bit short because of the sickness, but we can learn the big picture at least, and for this research. Okay, Dr. Agong, you can go ahead and to introduce. Maybe you can share a screen. Okay.
Thank you. I'm trying to get the screen share to work properly. It's not. When I go to full screen, I'm not able to actually get rid of the small screen. So let me try one more time.
It seems like it doesn't. The current screen. We can see your screen, and it's not in the promotion mode right now.
Yeah. Yes. It is not interacting. Huh. Okay. How's that?
Yeah.
That looks okay? Yes?
Yes.
Okay, great. Okay, thank you for the invitation, and I'm sorry that I can't quite give the talk that was planned. I've got laryngitis. But as was mentioned, oh shoot. I'm sorry, I'm not sure what's going on with my machine. Okay, here we go. So as was mentioned, my lab is located inside of the Shirley Ryan Ability Lab, which is a rehabilitation hospital in Chicago. It's an open plan research space, which means that we are integrated within a clinical environment. So my students program robots literally steps away from people who are receiving inpatient physical rehabilitation. I'm going to go through the motivation for my lab's work a bit more quickly than I was planning, just to try to hopefully get through one line of research before my voice gives out. But within the world of functionally assisted machines, so we use functionally assisted machines within the field of rehabilitation in order to bridge gaps in function. And across the field, there is a challenge in how you capture control signals from human bodies with motor impairments in order to operate these machines. This gets more pronounced both the more severe someone's motor impairment gets, as well as the more complex the machine itself gets. So you can see here on the right, these are interfaces that are available at increasingly high levels of spinal cord injury. And the two big characteristics to take away from what happens to these interfaces as we go from the bottom to the top is that their dimensionality decreases, And also they go from issuing continuous control signals to discrete control signals. So if you now go from issuing a continuous 3D signal to issuing a one-dimensional discrete signal, it is much more difficult to operate these machines. It is also the case that for higher dimensional machines to control, like a robotic arm, you now need to partition the control space of the machine in order to fully cover the machine's control space with the interfaces that are available. And I'm going to skip over these interfaces. But just to overview the challenges of operating assistive machines, we have the human's motor impairment that is actually masking and filtering information that they would like to send to the machine. We also have limitations on the control interface. We have limitations in the continuity and the dimensionality of a control interface. And we have this machine complexity, this catch-22 of machine complexity, where often more severe motor impairments require more complex and higher dimensional control signals from that body in order to operate the machine. So an approach that's been addressed with, an approach that has been pursued by the field within my lab as well as the field more broadly is to add robotics intelligence to these machines in order to offload some of the control burden. So to do this, you need to add sensors that are able to observe the external world, and you need to add compute and intelligence to interpret both the information coming from those sensors as well as the information that is coming from the control signals that are issued by the human in order to operate the machine. Because for most application domains, the human still wishes to remain in control as much as they are able. So I'm now going to take you through one line of research in my lab within this space. I had intended to walk you through 2 lines of research. I don't think my voice will make it that far, unfortunately. But within my lab, we started out with implementing shared control paradigms on these sorts of machines. So here we see 4 different shared control paradigms that were published within the robotic wheelchair literature. So we have it that we are just inferring an immediate goal, like for example, by forward projecting the control command that's issued by the human, forward projecting it like a half a second into the future. And then we can do things like linearly blend that with an autonomous planner that is able to drive to that position safely without colliding with any obstacles. Or we could perhaps filter the control command and say that the human's control signal in each control dimension should never exceed that of the planner that is presumed to be safe. But we can also find different ways of finding goals. And this is where things start to link somewhat to perhaps vision-based approaches. So certainly to know what safety is, you are paying attention to external sensors, but also to figure out where the person's trying to go, you could also be paying attention to those external sensors. So it could be that you have a perception goal, for example, that there are physically constrained tasks within the environment, like traversing doorways or docking under tables, that we know are issues for patients and for wheelchair operators. And so we can develop perception algorithms that are able to identify these locations autonomously and then use that as the goal for our autonomous path planner. So my lab did some early work in this area. We had algorithms for perceiving doorways as well as algorithms for perceiving ramps and safe docking locations. These all were geometric-based algorithms, so they were not based on training data. They were not based on images. They were based on depth data, and it was strictly based on known structure in the environment. So you look for walls, you look for gaps within walls, and so it is a geometric-based perception algorithms. So what we had seen in the field at the time that my lab was developing our first robotic wheelchair about a decade ago, what we had seen within the field was that these different shared control paradigms existed, but what we hadn't seen was a side-by-side comparison of them. So we had seen comparisons between shared control and full autonomy, or full autonomy and no autonomy, but we hadn't seen a side-by-side comparison of these different ways to do shared autonomy. So my lab did this study. We implemented these 4 shared control paradigms. 2 of them were using this higher level perception goal that used the algorithm from our prior work. We implemented them and we ran a study with wheelchair operators, people with spinal cord injury. And what you might notice in looking at these videos is that they don't appear to perform that differently from each other. And it is true that when we use the sort of typical metrics that we use to evaluate robot autonomy paradigms, like task completion time and number of collisions, none were statistically different from each other. What we did see, however, was that they were different in terms of user preference. And in fact, each of them was chosen at least once as the most preferred, some participants' most preferred paradigm, and at least once as someone's least preferred paradigm. What we also saw, we executed this study as nominally a 2-session study where people operated 2 different interfaces, so one on each session day. We had a joystick interface and we had a head array, where the head array, it was a one-dimensional control interface that was a discrete signal, so you basically tap your headrest to send a switch, it operates as a switch to go forward or turn left, right. And what we also saw was that, and we did do some work on trying to predict these preferences, but I won't get into that now. What we saw was also that about 50% of the time, people's preferred paradigms changed when the interface changed. I will note, however, what we don't quite know is how much of this was related to the interface versus familiarity with the autonomy over time. And that is something that as a field, I'd say we are still working on. The fact that most of our studies evaluate novel interaction with these devices, and that's an issue we're going to need to address going forward. Okay, so a lot of my lab's early work was along these sorts of veins, and time again, we saw that it was important to customize our solutions to people, that a one-size-fits-all solution was not going to be the right solution. So fast forward to 2 years ago, and my lab is now a part of the National Science Foundation's Convergence Accelerator Program, and we are specifically trying to address barriers to independent mobility with robotic wheelchairs. We're addressing 2 barriers in particular. One is a lack of safety control paradigms that are available commercially on powered wheelchairs. So things that we see in our cars, like driver assist that we see in our cars, like emergency braking and parking assist and lane assist, these don't exist in powered wheelchairs, commercial products. And we also wanted to address the inability to issue continuous control signals from parts of the body that can't operate a joystick. We have a lot of partners on this project, which is a part of the Convergence Accelerator mandate. This is supposed to be convergent research that involves all stakeholders, whether those are end users, it might be government, it might be policymakers, it could be industry, whoever it makes sense for your particular application domain. And in particular, our big partner on this is Lucy. So while none of the major wheelchair manufacturers offer any kind of driving assistance, Lucy came on the market in 2021 as the very first in the United States and still the only aftermarket sensor-based safety system for powered wheelchairs. So you can see here in this image, we have each of these colors represents a different sensing technology on the chair. And so you can see that we have full 360-degree coverage, and then we have redundancy where we have overlap between sensor systems. And what the Lucy system will do is it will detect obstacles and it will detect drop-offs like chairs and curbs, and it'll stop you or slow you down. What we are working on in this project is now providing more accelerated and active forms of assistance. So our team is called Project Drive. We have 3 thrusts that we are addressing, but first I want to go overview the team a little bit. So Jared Dean, who's the CTO of Lucy, is my co-PI on this project. But we also have clinical collaborators who are our team members. So for example, Daniel Vance is an OT who's been with our project from day one, and we have other clinicians as well. And then very critically, we have end users. So Kevin Rowland is an engineer and a computer scientist, and he's living with ALS. His primary mechanism of communicating with the world now is through his eyes, through an eye-gaze interface. And he uses his eyes to talk to us, to participate in meetings, and he uses his eyes to write code for our project, which is pretty remarkable. And what people like Kevin afford us is they live in this sweet spot that is very sparsely populated, where he both understands the technology deeply enough to know what it is capable of, and really critically what it isn't capable of as well. And he also has lived experience. And so having his insights and insights of people like him is really, really critical for our team. Okay, so just overviewing these 3 thrusts really quickly. So this first, driver assistance, as I mentioned, we're working on more active forms of driver assistance than the Lucy product provides. And so in particular, our React assistance will now actively drive you around an obstacle. It is not trying to do any higher level perception besides just perceiving. We just perceive obstacles and drop-offs and come up with an occupancy grid safety map. That is what the Lucy product already does, but there's no form of higher level perception than that. But what we are doing is actively driving people around obstacles. Now with route assistance, we are building up maps of a known environment, and we are providing 100% autonomous assistance to known locations that a user will be able to tag within these maps that are built of, for example, their home. So you'll be able to tag, like, this is where I like to watch TV, this is where the bathroom is, this is where the kitchen, and then be driven there with full autonomy. Which we have found that there are users like our team members with advanced ALS who would like a 100% autonomous solution. And so route assistance is using higher level perception in order to perform the sort of assistance that it is doing. And so our project goal is that we want to roll this out to all 400 plus Lucy users who are out in the world. They can have their Lucy units updated just with an over-the-air software push. And we are on track for React assistance to be sent out to Lucy beta testers this summer and to all Lucy users by the end of this calendar year. We are also innovating on how communication happens between wheelchairs and any input device. So the current standard is actually that the current standard used within the field is that communication happens over a serial DB9 9-pin cable. So it's a printer cable. So it's serial, it's not digital, it's not bidirectional, and it can't be brought into the digital age. And so what we have developed is what we call the wheelchair digital interface. It is an open API, it's already released open, and it is a communication protocol between any digital input and a wheelchair. So here you can see Jeanette, she has CP and she's a Lucy beta tester, and she's driving her wheelchair with an Xbox controller, which is made possible because of the WDI. And our project goal is that we'd actually like this to be an ISO standard for wheelchair communication, digital wheelchair communication. Our third thrust has to do with how control signals are relayed or captured from the human in order to be relayed to the machine. And what we identified as a missing, a gap within the field, and we identified this in part through our partners with the Able Gamers charity, is the absence of very usable and low profile twitch switches. So these are switches that are able to detect sub-millimeter movements. So here you can see our prototype based on optical sensing. It is not yet low profile, but it could be when it's not a prototype. And our project goal is that we want to capture both discrete and continuous wheelchair, and we want this to be able to be used for wheelchair and computer control, both discrete and continuous signals. And we want it to complement and expand current interfaces. So it's not that you need to use this instead of whatever interface you're using. It's that this would open up additional control channels also from additional parts of the body. We have a pitch video for that we created as a part of this project, and the QR code for that video is here. And so I think that's about it for my voice. So I apologize for that, but I'd like to thank the current members of my lab on the left and alumni on the right, and then I'm happy to take some questions.
Any questions from the audience? I received some questions, and one thing is, how many sensors have you put on the wheelchairs, and how to coordinate those sensors?
So the sensors are sub-millimeter wave radar, ultrasonic sensors, and depth cameras, RGBD cameras. There are 2 depth cameras. I'm not actually sure exactly how many radar and ultrasonic are on the platform, but they have 360-degree coverage. The 2 depth cameras are forward-facing. And exactly how they get coordinated is a great question, and that's a proprietary Lucy question. So I don't quite know. We get on the other side a point cloud that has already integrated all of these technologies, and a safety map that has already integrated all these technologies. But in terms of whether or not there is different priority given to the different sensing technologies when populating that map, or how conflicts between them are managed, I'm not quite sure.
Okay, and also, are those sensors computed on the wheelchair? Are there any computing unit in the wheelchair as well?
Yes, there is a computing. There's a computer in the wheelchair. It also has a GPU. Everything that Lucy does is computed on the chair. For the moment, what we do in terms of our active intelligence to drive around the chair is being computed externally on a laptop because that's the easiest for our development. But once it's released to the Lucy product, it will all be on the chair.
Okay. Also, another question is for the gait estimation, and will that be something like some errors and in the gait estimation that we may have the miscontrol of the wheelchair?
Sorry, for which estimation?
The gait, the eye tracking.
Oh, so the eye tracking, so this is a system that, it's not our system that we've built, it's a commercial system. It certainly can have errors, but it actually, the way that most gaze trackers work is that it's actually big buttons on a screen. It might be a keyboard, or if it's for wheelchair driving, for example, it's big buttons on a screen, and then a button is clicked based on dwell time. So I think it's less that it's prone to errors and more that it is very slow to use because it waits for this dwell time. Because of that dwell time, it's less prone to errors, but it's also extremely slow to use because you have to wait for that dwell time.
Okay. And another question is, and for the wheelchairs, will they communicate with each other, or they communicate with the environment?
Yeah, so certainly they could in the future. At this point, it's not being actively pursued because there just are not that many of these out there to necessitate it. But certainly, they're communicating with the cloud. Like they can send data up to the cloud if the user okays that. They can send data to Lucy. So there's nothing to say that they couldn't, but it's not being actively developed.
Okay. Any other questions from the audience? If no questions, thank you very much, Dr. Adam, and I really appreciate your efforts to make it happen for the talk.
Yes, it's my pleasure, and I'm sorry that I wasn't able to give the complete talk that I promised.
Okay. Okay. Thank you very much. Okay. Bye.
Thank you. Bye.
Keep up loving for your talk. Okay. Let's end up our morning session, and our afternoon session will start at 1:10.
Localization. So we want to localize that canvas in maps. That's like it. And then okay. This is something that is not done with yeah. I didn't talk, so this is interesting. Yeah. We're gonna have any innovation for sure. This tomorrow. I need to find out if it's technical, but I don't have it on my list. I need to check out. Yeah, I do.
我暂停了，我就是暂停 Zoom 暂停了一下 recording。我没有断。
Hey, do you want to go up for lunch?
Actually, it's 1:10 that will.
Okay. Well, I need to be for the poster at 1.
Sure.
But actually, this is why I wanted to ask if you want to go up there for lunch. No, so lunch is in the exhibit hall.
Sorry.
In the exhibit hall, there's the lunch.
Is it far away from here? No.
It is. It's on the third floor.
It's in the third floor.
I mean, of course, you will be back, but you might need to grab your lunch.
Oh, we can go. We bring a bread and then we come back.
If you find the clinic short the right way, then it shouldn't be too hard.
你听了我的啊，你知道我不记，我这还在 streaming。外面有热水。为什么我的这个是这么迷你的？我就是挑了两个不一样的。这个说他那里排的好长好长的队，我就不想插队了，我就这排了至少有这么个100米长的队，有排。然后你就排，我没排。我们就想我们自己直接走到前面去看一看能不能直接从那些排队的人老老实实在那排着队，一个一个，我们就直接到饭店去拿走。你几点开始的班？1点10分，半小时以后。1点10分了。还有半个钟头。关键是我这个 Zoom 它怎么是？哦，这儿呢，我先把我的信息。
Hello, can you hear me?
Yeah, we can hear you. We can actually get started, and finally it works. It's great. Okay, can you try to share your screen? And so while you are sharing your screen, and I can introduce you, and then we can get started. And first, let me begin to record. Yeah. Okay. Okay. So let's get started with our afternoon session. And doctors Sylvia and Valerie is the speaker and the first speaker in the afternoon session, and she is currently John Brancaccio Professor of Mechanical and Aerospace Engineering, the Associate Dean for Cross-Campus Engineering Research at Cornell University and Cornell Tech. And prior to that, she was a professor in engineering and computer science at Duke University, and the founder and director of NSF Integrative Graduate Education and Research Traineeship and Fellowship Program. And she is currently director of the lab for the Intelligent System and Controls at Cornell University and the co-director of the Institute for Vehicle Intelligence at Cornell Tech. She has given quite a lot of talks and books, and especially she has given the tech talk on the topic "Do Robotics Dreams of Electronic Ships?" And she is a fellow of IEEE. She is a senior member of IEEE, member of SPIE, ASME, AIAA, and she has received ONR Young Investigator Award, NSF Career Award, and the Presidential Early Career Award for Scientists and Engineering, and which also we call that PKS Award, and the highest award in the from the government agencies. Okay, Dr. Valerie's talk will be on active localization, identification, and mapping. Okay, we can get started.
Thank you, Oyu, and thank you also for inviting me here today. So today I'm going to talk about a new area of research in our laboratory where we have been focusing in the past on active perception. And I will provide a lot of also background on the topic, which for us is more or less a new direction. So we have been working for a while in underwater vehicles, and in this particular project, we are interested in developing autonomy algorithms for long duration underwater missions. So in autonomous underwater vehicles, one of the key goals is to develop intelligent path planning strategies that allow the vehicles to observe and understand more details on previously detected or prior information on targets. The targets may be distributed throughout a region of interest, and in many cases, the goal is also to perform target reconstruction. So as an example, I'm showing here two representations of the same bunny, one in voxels and one as a point cloud. Many of the underwater sensors these days also provide 3D information in these forms, and the idea is to perform both active and passive reconstruction tasks, but in particular we want to enable long duration autonomy in vehicles that need to perform multiple views in terms of performing their sensing objectives. So one problem we have been working on is the next best view planning for active target reconstruction. And in this problem, we developed generative models that allow the sensor to do so in a near optimal fashion. And today I'm going to be focusing on the other problem, which is that of actively planning the vehicle position and orientation over time in order to simultaneously reconstructing the target geometry, for example, improving target ID, as well as improving localization using imaging sonar. This is particularly important because in underwater exploration, we have the underwater robots or underwater autonomous vehicles, even though they are equipped with very advanced and proper sensors still struggle to perform correct localization. Therefore, over time, biases build up, often causing the vehicle and therefore the onboard sensors to not have accurate localization in terms of inertial coordinates or georeferencing, and as a result, causing errors in the target reconstruction or other perception tasks that they must perform underwater. This is particularly exacerbated if the vehicles operate in a remote environment for long durations of time and if they collaborate with other vehicles. So in these long-term or long-duration underwater searches, we're trying to cope with various complexities. One is sensing modalities. As you can see here, we are interested also in modalities that are not affected by some of the issues we encounter underwater. Also, we may be dealing with complex terrains that have lack of features typically utilized by algorithms such as SLAM, and also lack of navigation landmarks as the vehicles navigate environments that are largely unknown a priori and change over time. Therefore, even if the same vehicle or other sensors have previously visited the area of interest, we may still lack the relevant information to properly navigate. Finally, the inertial navigation can be obtained underwater, but often there are significant significant errors that take place in real-time navigation, and therefore we would like to develop algorithms that correct for these inertial navigation errors. And this type of scenarios are what motivate our research that attempts to not only perform simultaneous localization and mapping, but also to do so in combination with target perception, such as target reconstruction and recognition tasks. So we decided to employ our common active perception paradigm, in which we have that an autonomous robot collects measurements from interesting targets by means of onboard sensors, but then we don't stop there. Subsequently, we want to use this collected information to estimate measures of information value and not only update the target representation, but also what is the utility of potentially obtaining new information about those targets. And then this is where then we plan the control action, which will provide the most useful information in the future. So in this paradigm, we often need to cycle between the different stages. And in particular, if we look at some background on SLAM and target reconstruction, typically the active perception paradigm is not utilized, but rather the robot or sensor are navigating passively or in many cases randomly on the unknown environment, and then using an inverse projection of these measurements are able to reconstruct target information as well as estimating the sensor pose, which amounts to localization. So our goal is to at once perform these traditional localization and mapping tasks while also reconstructing 3D geometries of potentially multiple targets. So we would like to modify the typical dense visual SLAM pipeline shown here in order to account for these new problems by which the robot also has to take multiple looks at one or potentially more targets in a distributed environment. In the traditional SLAM pipeline that we see here, we have various tasks that the sensor must perform, including visual odometry. And by this approach, the sensor measurements obtained online are combined with IMU measurements, which may or may not be available accurately underwater, in order to estimate the sensor pose. This is then provided to an incremental optimization block, which produces both pose estimates and sparse geometry updates. In this process, we would like to introduce the reconstruction block so as to produce a dense geometry for the interesting targets that we are deployed to perceive. I would also like to give a bit more background on this topic, in particular visual odometry, which consists of the problem in which we have a sensor motion XC that brings our sensors, such as a camera or a sonar, from one position and orientation to another, the first being considered as viewpoint V1, and the second being considered here as denoted by viewpoint V2. At each one of these viewpoints, the sensor obtains two images. Now, if we are dealing with cameras, these might be RGB images. If we're dealing with sonar, these might be sonar images with different intensity matrices, and these also provide range measurements typically. So we hope that that is the case. That is not always the situation that we have. In some cases, we have that depth, as in RGBD cameras. In some cases, that information may be missing. Assuming that the same point on the target surface shown here, denoted by P, is characterized by the same brightness in the respective images I1 and I2, then we can perform this transformation using this equality, whereby the camera motion is bringing the sensor to the second viewpoint. And in the process, we have a warping function that maps a pixel coordinate X in the first image to a coordinate in the second image. And this is using a projection denoted by pi that maps the Euclidean space, points in Euclidean space R3, 2 points in Euclidean space R2. And this is what most imaging sensors perform. There are two types of residuals that we can use for loss functions. Of course, there are also many others, but in particular, we are focusing on photometric residuals and depth residuals that are denoted here by RIP and RID respectively. Going back to the previous notation that we see here, those correspond to the formulas shown here on the right-hand side of the table, where we essentially look at the difference in the intensity matrices and potentially in the depth measurements Z1 and Z2 when those measurements are available. Then we can define an energy function that is defined as the minimum of the sum with respect to xc, the motion of the sensor, and it can be weighted by weights wi for every one of the residuals. Obviously, if we have multiple viewpoints, for example, more than 2 viewpoints, we can take the sum over all of those points. This leads us to a probabilistic formulation by which we can distribute the residuals according to a probabilistic sensor model, where Ri, the probability of Ri, given the sensor motion, is denoted by P, the conditional probability of R given C. Now, if we can assume that the noise of all the pixels is independent and IID, then we can factorize this conditional probability, let's say, into the product of the conditional probabilities for each one of those viewpoints. Then, using Bayes' rule, we can rewrite the conditional probability of xc given R now. So we're, as you can see, we're inverting the arguments by Bayes' rule, and using Bayes' rule, that can be written as the original conditional probability P of R given C times the prior of xc divided by the prior of R. Now, clearly, the prior of R is independent of the camera motion, which is what we want to optimize, and the prior of the camera motion can be estimated using the IMU information. This then allows us to compute the energy function that I mentioned before, and in particular, using a maximum a posterior estimate, we can show that that is equal to the weighted least squares formulation of direct energy minimization, and therefore we perform the maximum a posteriori estimate as shown by this equation. In this probabilistic formulation, we can also assume that the motion prior probability is a constant, and then we can write this map estimate of the energy function as the argmin with respect to xi minus the sum over the viewpoints of log of the conditional probability of Ri given xi minus the log of the prior of xi. Again, where xi is the camera motion. Therefore, when we assume that the motion prior probability is constant, we can then calculate the minima by differentiating the logarithm with respect to xi and setting that equal to 0. Using the chain rule of differentiation, we can write the partial derivative of the log shown here with respect to xi as the partial derivative of the prior of Ri or with respect to Ri times the partial derivative of Ri with respect to xi. Afterwards, we set this quantity here equal to the weights and rewrite the sum as this relationship right here. This leads to recursive relationships shown in this box, which allow us to solve the problem using Cholesky decomposition. Now, in this problem, we typically want to fuse both the visual information from the camera field of view with inertial measurements that give us information about the inertial position and orientation of the sensor at the time the images were obtained. So this is what is also known as visual inertial odometry, where the two problems can be either tightly coupled or loosely coupled. So in the literature, these two approaches have been utilized as follows. In the tightly coupled visual inertial odometry problems, the information from the visual and inertial sensors is combined in one optimization problem. This allows to solve mathematically the correlations amongst the sensors. And although it is computationally expensive, it also provides obviously higher accuracy. Because of the computational expense and the assumptions underlying these techniques, there are also techniques known as loosely coupled, where the pose is predicted by solving for the visual sensor information only using the IMU measurements and then fused in separate estimation steps. This does not account for correlation amongst different sensors. And in some recent approaches by our collaborator Scher and his co-authors, there have also been attempts to combine the two ideas, both the tightly coupled and loosely coupled methods, to create hybrid approaches that leverage the advantages of both. In the tightly coupled problem formulation, the xi map is given by this relationship here, which is a version of the relationship we saw formerly. And assuming that the camera motion xi is distributed normally, the average or the expectation of xi can be predicted using IMU measurements with a covariance sigma, using the relationship shown here. So in this case, a large covariance matrix, of course, will decrease the influence of the motion prior to the MOU and vice versa. So the covariance matrix obviously is chosen based on the given application. In the SLAM paradigm, we also know of the well-known methods known as incremental smoothing and mapping. So again, in this original work by many authors, we have that robots typically navigate the workspace, typically using a random algorithm or maybe some other objective for navigation, and at the same time passively collect information that allows them to perform simultaneously localization and mapping. And the incremental smoothing and mapping approach allows to use factor graph factorization and the maximum posteriori estimate in order to improve the estimates of the state, which comprises both the robot position orientation as well as the position of the landmarks in inertial space improving these estimates over time incrementally, in an incremental fashion, because we have that the robot, as it navigates, of course, is collecting information about potentially some of the same landmarks. So in this schematic, we have that the robot is represented by a yellow triangle, which represents the robot geometry. The field of view of the onboard sensor is shown by a blue sector. The landmark is represented by a red dot, and the measured, corresponding measured object is represented by a magenta or purple square. So assuming that there is a nonlinear mapping H, known as the measurement model, which essentially maps the actual state we're trying to estimate onto the measurement vector, then we can write the factors of this X-map relationship in this form here, where they are proportional to the exponential raised to the power of -1/2 H, which is this is the measurement model minus the actual measurement, and then we take the norm of that. Now, this particular problem can be recast into the following non-least squares problem, which is much more efficient to solve using the corresponding factor graphs. So the factor graphs, which also exploit the separation properties or conditional independence relationships, allow to compute these updates more efficiently, incrementally over time as new measurements become available. Here, the nodes representing the pose of the robot are shown by the yellow circle and are denoted by x1, x2, x3, and these are essentially the estimates of the robot pose as they're being updated over time, and the landmarks, the landmark information, obviously, or landmark state, are shown by the pink nodes denoted by L1, L2, and so forth. So these are different landmarks that are entering the field of view of the sensor, essentially in a random fashion, not with any purpose or planning or active sensing, but simply happen to be in the scene and can provide help in localizing and mapping at the same time. So this is the well-known incremental smoothing and mapping performed in traditional SLAM algorithms, and ultimately the numerical solutions can be obtained using the well-known nonlinear solvers, as we now have a nonlinear equation that can be solved by Levenberg-Marquardt or Gaussian-Newton method on gradient descent. So before I go into the new directions of research that we are exploring in terms of like active localization and mapping, we would like to also review some of the sonar modalities for underwater mapping, since this is ultimately our desired application. And here we see some differences between sonar that are either forward-looking, side sonar, or synthetic aperture sonar. In each of these cases, we have that the sonar is installed on an underwater vehicle, and the characteristics of the sonar also affect the type of maneuvers we wish to perform. Now, the main difference between, well, I would say one of the main differences between these types of sonar is in the field of view, not only its geometry, but also its orientation. So, for example, in side scan sonar, the swath refers to the field of view that is scanned as the vehicle swims over a region. Therefore, the region is typically that is imaged by the sensor is typically below the vehicle. In forward-looking sonar, the sensor is forward-looking, and therefore the image that is built is comprised of vertical cross sections of the images that come across the vehicle and typically are in front of the vehicle. And then we also have synthetic aperture sonar that resembles synthetic aperture radar and therefore is highly reconfigurable. Now, In all of these problems, obviously, we can use different applications and also different sonar-based SLAM. So this is an overview of the different algorithms that have been proposed over time to perform SLAM in forward-looking sonar, side-scan sonar, synthetic aperture sonar, as well as sonar with optical sensors. This is a review of the algorithms, and DVL and IMU are also used for that reckoning odometry estimates. So in light of all of this research, our goal is to focus on the possibility of tracking features across different sensor images, and also on how to actively pursue important targets and use information collected by from those targets to improve simultaneously the classic localization and mapping problem, but also the target reconstruction and possibly classification. Since typically we're obtaining multiple views from the same target, we can leverage the sensor geometry and the measurement model to essentially extract out or in a way nullify errors that are due to errors in localization as well as in mapping. So focusing on imaging forward-looking sonar as well as side-scan sonar, we have that images may resemble what you see here. And from knowing the sonar, we can develop a geometry of the measurement as they map information from the 3D world onto a 2D image. So this is an important reference that shows an illustration of 2D forward-looking sonar and how the geometric information about the target is translated into a 2D image that is typically on a grayscale, but is very different from traditional images because it also consists of shadows and is constructed from processing acoustic measurements. Therefore, it does not have the typical characteristics of natural images. The sensor measurement model, as I said before, is essential to performing incremental smoothing and mapping because it is what gives us the nonlinear function H, mapping the information about landmarks and poses from information from the image obtained by the sensor. So if we have, for example, a landmark that in the 3D world is positioned at the X, Y, and Z coordinates in the global frame, once it is observed from a sensor with pose XI, so this is the first look, which is obtained by a sensor with position and orientation represented by XI, that vector L sub j in this case is mapped onto a sensor reference frame. For example, this could be a reference frame embedded in the image plane for cameras, or in the sensor frame relative to the sonar for the different sonars that we considered before. And obviously this mapping depends highly on the type of sensor. So here's an example of the nonlinear measurement model that allows us to obtain the range R, the orientation theta, and also the intensity I from this information, where you can see that the transformation is definitely nonlinear and this function gives the intensity and is pose dependent. So many times the results obviously are pose dependent, which is why we need to simultaneously estimate the pose as well as the landmark information. Example applications of this type of sonar consist of path planning, shown here. This is for autonomous underwater vehicles, mosaicing, shown here, localization, where we have that vehicles perform many passes in order to localize themselves as well as important targets. And finally, the one application we're considering the most, which is 3D reconstruction, as you see here, and this may be in fact performed in the form of a point cloud. Some important considerations before we move forward are elevation ambiguity and sensor pose-dependent intensity, as typically we are assuming that at different viewpoints, the intensity of the same point on the target surface is the same. In reality, that is not true because this brightness consistency assumption is often violated in FLS images, as I mentioned before, because the reality is that the images are obtained by processing acoustic measurements that are obtained using wave propagation models, and these are also the propagation models that describe the propagation of acoustic waves and underlie the acoustic measurement phenomenon. Therefore, in the case of this type of images, traditional SLAM algorithms are much more error prone because the brightness of the points is pose dependent. Here's an example of images captured in Lake Osceola. And as you can see, also we have the phenomenon known as shadowing, which is not the shadow as intended in natural images, but rather shadows that are created by the acoustic wave propagation and the characteristics of the sea bottom. So because of these issues, it then becomes very difficult to localize landmarks, and as a result, to perform simultaneous localization and mapping, whereby both the pose and the landmarks are subject to errors due to the violation of this assumption, as well as other issues of sonar images. So we propose to use neural surface reconstruction techniques. This is a technique that has been used for volumetric rendering to infer 3D target geometry, as well as for simultaneous target tracking and reconstruction, as shown in this video. So here we can see also how this can be utilized with underwater cameras, and the methods we are developing are more or less sensor agnostic. While they do apply to sensors with the characteristics that I mentioned so far, we are implementing them on both vision sensors such as cameras, whether underwater or above water, as well as in forward-looking and side-scan sonar. So we want to develop an approach by which we can perform 3D target reconstruction, even for problems where we have the elevation ambiguity and pose dependency problems. And in this case, we are proposing using neural surface reconstruction because these are differentiable volumetric rendering that allow us to model the actual physics behind sonar, such as as I mentioned before, the acoustic wave propagation phenomenon, and using that to model the geometry as a neural implicit function. The advantages of this approach, so here is a summary of results obtained by different methods as well as our own. Our own being that of color. In this case, the pros and the cons are listed here. So we have that the advantages is that we can, as I said, we can rely on physics-based rendering that takes into account the underlying physics of acoustic wave propagation, and also that this is generalizable for arbitrary target geometries, since in many cases we do not know what target we're going to be considering a priori. And also this technique is robust to speckle noise. The cons are that it is currently difficult to perform large-scale reconstruction, and again, like many other methods, assumes error-free localization, which is the problem we're trying to solve, since that is typically not the case for underwater vehicles. There are also some other cons, such as that this technique does not leverage the priors and does not typically allow for the same type of updates. So what we're proposing to do is to develop a neural implicit surface-based new SLAM framework where we leverage some of the strengths of the original smoothing and mapping incremental approach, such as for the backend state estimation and also for 3D mapping. And at the same time, we want to combine the sparse feature base layer with the neural dense reconstruction and inference layer that is used using the neural implicit surface representation. The dense representation, known as an NSFDF, is denoted by N and is a function of the sensor pose, the landmark position, and also the orientation. The dense reconstruction is obtained by considering the geometry of the sensor, in particular assuming that we are looking at measurements represented as point clouds that may be sparse, that is then fed to the NSDF so as to obtain a geometric evaluation from a reconstructed dense representation. Here is a comparison of sparse and dense feature reconstruction. Here are existing sparse feature-based sonar SLAM. So this is the state-of-the-art as far as we know of underwater SLAM. The current limitations that still prohibit underwater vehicles to accurately perform simultaneous localization and mapping, especially in long-duration autonomy missions, are that there are insufficient amounts of features, as I mentioned before, and this is due to the nature of sonar images as well as to the nature of the environments that we explore underwater, and how these affect state estimation and mapping results. In our approach, we propose to consider 3D dense geometrical features and to use new evaluation metrics that we have developed using generative models for 3D point cloud reconstruction and for rejecting outliers so that we can denoise the sparse feature. So our goal is to provide a more accurate approach for estimating not only the vehicle pose and the landmark position and also identification, as well as simultaneously performing better target reconstruction in 3D. And so this is our proposed approach and how it compares to the traditional SLAM for sonar. In conclusion, in the past, we have developed new robust multi-view planning, control, and autonomy algorithms that are applicable to underwater vehicles conducting long-duration autonomy missions in environments where they are deployed to conduct multi-target classification. One of the algorithms we have developed and published in the IEEE transactions of oceanic engineering is the so-called IMVP, which is an information-driven approach for multi-view planning in underwater settings. And we've demonstrated this approach in at sea testing, as well as extensively in numerical simulations. And what we want to do now is use some of the learned lessons from this previous work in active perception in underwater environments for complex target reconstructions, where we're actually using continuous normalizing flow for shape completion and for planning the next best view or NBV problem. In this regard, we have developed also new performance metrics that allow us to quantify the quality and completeness of the NBV problem using continuous normalizing flow. And we have developed a new approach based on generative models for active reconstruction, known as GAR, where we use the generative model to estimate the information value of future views in relation to views of the targets that have already been obtained. And this is without knowing the target geometry a priori. Again, we want to use the results here to develop a new approach for simultaneous multi-target localization, reconstruction, and mapping in decentralized target detection and classification problems where we may have one or more underwater robots working collaboratively to not only localize, but also reconstruct and classify accurately multiple targets distributed in an underwater environment where we may or may not have accurate georeferencing and inertial localization. This hopefully will allow us to provide better underwater SLAM, as well as simultaneously providing accurate capabilities for active target recognition, localization, and mapping, even when the localization and mapping performance standalone is not satisfactory and is not accurate enough to be utilized for multi-target localization. So in other words, we want to take 3 problems that are performed poorly and combine them so as to perform them all in a better sense. So like with a better performance, excuse me. So I would like to acknowledge the people who worked on this problem, not only my collaborators, Matt Bays, Joshua Weaver, Tom Weddergren at the Navy, but also my former PhD student, Shi Chan, who has already graduated, as well as my current postdoc, Evan Chuan Lee, and my current PhD student, Sushruth Sir, both of whom have performed the work shown today. This work also was funded by the ONR Code 321, the MCM Autonomy Program. So I would like to acknowledge the sponsor. I would also like to address the audience in terms of where you can find more information about this research and other projects. In particular, our book, Information-Driven Planning and Control, provides a lot of the background and techniques that can be used to solve the problems talked about today, as well as other problems in active perception. And last but not least is my TED Talk, that was also mentioned in the introduction, The Robot Dreams of Electric Sheep, which is an approachable introduction to active perception. And with this, I would like to thank you for your attention, and please let me know if you have any questions.
Any questions? I got several questions from the channels, and first thing, there are some lighting, providing lightings in the underwater and for robotics, and compare with regular RGB images, and which has the lighting conditions, active lighting conditions, I would say, and how to why you choose sonar instead of RGB images, and what are their advantages over each other?
Oh yeah, that is an excellent question. So basically, if we have good lighting conditions underwater, definitely RGB images can be highly effective, as shown in the video on neural surfaces, where you saw an underwater camera obtaining imagery from underwater environments. However, the sonar provides 2 important advantages over RGB cameras. The first is that it can provide information at much longer distances, and the second is that it can provide information even when there is no visibility. So aside from the light conditions, so say we're looking at very deep environments or environments during darkness conditions, for example, at night, or inside caves and other enclosed environments, such as inside a rack, then sonar provides the same quality images regardless of the presence of light, of natural light.
Okay, thank you. Another question is, so in sonar images, there could be quite a lot of noise and in underwater conditions, and how do you do the optimization and for those kind of noise in the underwater?
Yes, that's another excellent question. So sonar images are characterized by noise, but primarily they are characterized by features that are difficult to interpret because they're not natural images. They're produced by processing through many different steps the acoustic wave propagation results. So when the acoustic wave is propagated in the environment, there are many phenomena, most of which are also described in summary in my textbook, that affect the propagation of sound in the underwater environment. And in active sonar, the images are obtained by processing the return signal, which is the amount of acoustic energy that is received after the wave has propagated through the environment and reflected back from the target back to the sensor. Knowing the underwater propagation properties, one can essentially develop filtering and processing algorithms that turn those measurements, typically in decibels, into images that are in fact not an actual image, but simply a processing of the sonar data reflected onto a 2D surface. So people who are accustomed to interpreting sonar imagery understand how to extricate information from the image, despite the fact that it doesn't resemble natural images. And so similarly, when we use automatic target recognition algorithms in sonar imagery, what we do is we simply train them with sonar images instead of natural images, so that the algorithm will learn to recognize, for example, a cylinder from a sonar image, even though the cylinder looks very different from what it would look like in a natural image. Now there are many other types of sonar such as circular SAS, that provide point clouds and extract geometry from targets in the same way as you would with a natural image, for example, an RGBD camera. However, those sonar are not always available. Therefore, we want to develop techniques that also apply to more traditional acoustic sensors.
Okay, thank you. And another question is, compared with IMU and sonar, and in underwater conditions, which one provides better pose estimation?
Underwater odometry and IMU is available, but again, it is subject to many limitations. For example, it may not be available in contested environments, and also it may not be available when the underwater conditions are very harsh, as well as when long-range communications are required. So for example, you are definitely able to find underwater modems and IMU-like systems. However, they rely on techniques that may not always be applicable in underwater settings for a number of reasons. And therefore, the type of sensor that is by far the most relied upon and the most broadly applicable underwater remains to this day sonar. And because it is also utilized for target recognition and classification, then it is intrinsically available on the vehicle. With that said, if you are able to obtain to operate the vehicle with an IMU or with inertial navigation, which is also available sometimes using the either underwater odometry or also other techniques utilized underwater with inertial positioning systems that are devised specifically for underwater environments. If you're able to use both, then of course that's the ideal situation. That's what I would say.
Okay. Yeah, thank you very much. Any other questions? Okay, if no further questions, thank you very much, Dr. Ferrari, and I really appreciate your time to give us the talk.
Thank you for having me, and enjoy the rest of the conference. Bye-bye.
Yeah, thank you. Bye. And let's have the next speaker, and he's here as well, and Paul Torrance. And Dr. Paul Torrance is a professor in the Department of Computer Science and Engineering at New York University, and he's currently also a faculty in the Center of Urban Science and Progress. And prior to join NYU, Dr. Torrance was a founding director of the Center for Geospatial Information Science at the University of Maryland. And before returning to NYU, he was a program director for engineering research centers at NSF. And he also received Presidential Early Career Award for Science and Engineering PKs, the highest award from the US government agencies. And for his work in modeling human behaviors, he received his PhD from University of College London in 2004. Dr. Paul Torrance, you're here, right?
Yeah, I'm here. Can you hear me okay?
Yeah, we can hear you. We just couldn't see you. Do you want to turn on your camera, or you want to?
It'll eat up my internet connection. I think it's better that I leave it off.
Okay, sounds good. Yeah, you can go ahead.
All right. Well, thanks very much, Guayu, for the very kind invitation. And hello, everybody. It's a fantastic event, and I'm delighted to be part of it. So I'm going to talk to you today about the topic of embodied pedestrians, if my computer will work. So briefly, I'm going to talk about what embodiment is. I'm going to discuss why pedestrians are a good case study for exploring it. I'm then going to move on and discuss what it has to do with artificial intelligence and query whether we can build AI pedestrians, and then state that yes, of course we can, and I'll show you how. I want to acknowledge 3 of my fantastic graduate students whose fingerprints are all over the work that I'm going to show here: Ryan Kim, Kai Shinazaki Konofre, and Damien Chen. So first of all, embodiment. Embodiment is many things, but at its core, we can reasonably think of it as the notion that cognition is physically grounded. So this is a topic of huge debate in philosophy and philosophy of the mind, whether thoughts and action are separated or whether they are intertwined and so on. So there's a couple of different flavors of embodiment. The first is social embodiment. So the techniques by which we developed a shared social meaning, and in particular, how we do so when our experiences, our minds are singular. So this gets into Schutz's ideas of intersubjectivity. The second is computational. It's embodied interaction. So the notion that we can extend computer-human interaction away from devices and perhaps have it drift into users' natural context. So for computer scientists in the audience, this is context-aware computing, and this is Paul Dorsch's idea for the future of computer-human interaction. The next topic is situational embodiment, and this goes back to the philosopher Merleau-Ponty's idea of phenomenology. So the idea that the body and the mind are intertwined, and that they are often intertwined through context. That could be social context, but traditionally it's environmental context. And then, of course, embodied AI. So the notion that artificial agency can become so sophisticated that it can be designed to enact tangibly in the physical world. It can drive robotics and agentic AI assistants and so on. And this actually dates back to the end of the 20th century and Franklin's work on autonomous agents. And then new ideas, probably Rodney Brooks' ideas for Cambrian intelligence are part of this, but the idea of embodied cognition. So the idea that we can close the gap between perception and action. So effectively, there is no gap, so that AI becomes dynamic. It becomes an intelligent interaction with the world. Instead of sensing, we just have constant attention and reaction. Okay, so these ideas of embodiment represent a shift away from sense, model, plan, act AI and toward automated machine intelligence, or AMI. So this is the concept being advanced by my colleague at NYU, Jan LeCun. So this is really a push toward a form of an active AI. So a move towards a new form of AI that comes from a substrate of autonomy and adaptability. So novelty, change, shifting context, things that AI doesn't necessarily have an existing plan for, that it doesn't have an existing knowledge base for, and so on. So pedestrians present a good case study for all of these forms of embodiment. So the first reason is that being a pedestrian evokes questions of habit and quotidian behavior. There's lots of things that we do by kind of rote memorization and do habitually. But we also do a lot of things that are extraordinary. So we do things that are ordinary, we do things that are extraordinary. We engage in evacuations, we engage in pedestrian surges, we line up for sales, and so on. There are a lot of unresolved society-facing value propositions in exploring pedestrian embodiment, everything from accessibility through to public health, safety, security, recreation, and so on. And some of these are what we could refer to as wicked problems. So wicked problems are things that we try and solve, and our solutions usually just tend to create new problems. So one of the main wicked problems for pedestrians, of course, is pedestrian injury. There are also several commercial value-facing propositions. economic development, retail and marketing, location-based services, wearable user interfaces, advanced driver awareness systems, wireless networking that needs to guess where pedestrians are and what they're doing to avail of high bandwidth and low latency communications, and so on. And pedestrian embodiment is very thorny to tackle in practice. So it's an interesting academic subject to study. So it quite easily tends toward infinite uniqueness, non-generalizability, and pedestrian behavior and pedestrian phenomena quickly become nonlinear and turn into complex adaptive systems. So what would it take to incorporate all of these functions into an agent AI? Well, first of all, it requires agents, not libraries, that automatically do the right things in the right locations at the right times, in the right company, and in the right ways. So in other words, agents should demonstrate a sort of common sense. They should engage in common sense actions, reactions, interactions, transactions, and proactions. And that common sense should persist and should survive and should be resilient and robust relative to novelty, so relative to novel situations and shifting dynamic context. So how do we get started on this track? Well, one thing is to engage in real-world field work, so to do real-world examination of embodied encounters. This exposes us to questions of dynamics and relevance. Until something better comes along, one common framework, or the best common framework we have, is probably geography, and geography can provide common sense world models, whether they're maps, HD maps, conceptual maps, mental maps, whatever they might be. Computation, of course, can produce what-if scenarios that allow us to scale beyond the original evidence. And immersive technologies can open up new cyberspaces or cyber infrastructures that provide exchange pathways between computing and the real world. Newly incoming brain-computer interfaces can close open reality gaps that exist between models and our lived experience of the real world. So what I want to do here now is go through one example approach of an end-to-end kind of research pipeline. So this is a system that we have been developing at NYU. We call it Sidewalk to Synth. So the idea is that we go directly from field observations of sidewalks and streetscapes to synthetic representations of those things and hopefully back again. So we go from naturalistic observations into models and simulations and then into user-based experiments. So the first thing that we do is that we spend a lot of time sampling behavioral data through naturalistic observation. And we do this by hand through ethnography, but we also do it with devices and with software, particularly deep learning, that adds value to the data that we can collect by natural means. So this is just going to be a movie that plays here. We do coded observations. We spend a lot of time coding up pedestrian behavior. We do fixed observations at the streetscape side with LiDAR and other forms of geomatics. We have mobile versions of these that we put on human subjects. So we get first-person views, either with LiDAR or cameras or combinations of the two. Again, we use a full stack of deep learning techniques to add value. We do gaze and fixation tracking. Try and see what people are looking at, what's holding their gaze, where there's mutual social gaze, and so on. Next thing that we do is that we build synthetic one-to-one virtual geographic environments. So these are essentially 3D GIS that have one-to-one mapping between the real world and its synthetic representation in the GIS. So we do this with commercial products. This is AirSim. This is open source platform Carla. We have our own version that we run, that we fork, but ultimately we're interested in building our own models. So this is one of our own home-brewed models of an area that's near our lab in Brooklyn. We then perform studio recreations of behavior and phenomena. And the idea here is that we want to develop accurate, realistically sourced, quantitative, empirically founded state descriptors that will allow us to fine-tune our understanding of behavior and context. So for this, we have a motion capture lab. Started out with a bunch of marker-based cameras and has grown over the years to include a lot of different location-aware technologies and sensing technologies. And we can have a lot of people in the lab. We can record for about 20 people simultaneously. So we can have them act out different behaviors. We can project things on the screen. We can have them get in VR headsets and so on. And we can collect real data. We can go out in the real world, code it up, go back into the lab, go back and forth and so on until we have a good understanding and a good collection of data that map to those behaviors. So this is an example here. This is actually me in our lab. So the prior image was marker-based motion capture. This is LiDAR. And then just showing a couple of different modalities, all working at once. This is me directing traffic or pretending to direct traffic in our lab. We can have people come in with different locomotive behaviors, people that maybe have difficulty walking, people that have different stride patterns, different nonverbal communications for their body language and so on. And we can develop graphs of their body language. And all of this data is collated in real time. And we have a data fusion system that streams this all up to about 800 hertz when it works really well, but certainly somewhere between 100 hertz and 800 hertz. So it's about sub-millimeter in some instances in spatial resolution as well. Okay, so the next thing we do then with all of those data on hand, we have our observations in the real world. We've come into the lab and we've tried to fine tune and calculate all the parameters of what we've observed. We then put this information into an agent AI that is designed to replicate the behaviors as computation. So we do this a couple of different ways. We're using geography as the main unifying substrate for this. So at city scale, we have path planning. At neighborhood scale, we have navigation by wayfinding. At street scale, we have movement by steering. At people scale, we have reaction and interaction through collision dynamics and vision. And then at body scale, we deal with locomotion. And what we're interested in then is what's kind of below that scale. Below body scale, below locomotion, we get into issues of what's going on in one's mind. Okay, so for the agent AI, we have path planning. Probably familiar to most people in the audience here. Low path planning, we have a combination of navigation, wayfinding, and steering. Again, probably familiar to most in the audience. And some of what we do here is we do machine learning. So for some of our observations, we have a lot of trajectory samples. So we can do combinations of data mining and machine learning to learn different patterns of motion. We then get into locomotion, and then combinations of locomotion with vernaculars of hyper-localized social behavior. In this case, it's within a crowd. Getting into some of the social agency, some of the affordances, bids for interaction, affect, and so on between people and crowds. We can do this for extraordinary scenarios. In this case, this is a mass egress model after an evacuation event. We layer in physics models. So we have a ragdoll model. coupled with a rigid body dynamics model. And then we have some IKFK models built into those too. We can put these together in some instances. Okay, so these simulations, or our simulations at least, focus on fidelity and verisimilitude. So fidelity is the idea that what we represent in the model should have a basis in what we see in the real world. We're not interested in making things be proxies of the real world or having them simply look like things in the real world. We wish them to act in the same way that they act in the real world and unfold with the same dynamics that we see in the real world. We also focus on verisimilitude. So when users interact with the model, it should evoke realistic behaviors from those users. So we focus on fidelity and verisimilitude for interactions amongst pedestrians, drivers, crowds, and traffic interactions. We develop immersive interfaces. So these are wearable, neural, VR, AR interfaces to the simulations that allow real people to interact directly with them with behavioral parity. So here you see a road crossing model. We have cars, we have pedestrians, and we have in the upper right, we have a user who's in the simulation trying to cross the road. Again, one-to-one mapping between our studio and the model. And while they're in the simulation, we can, of course, collect lots of data about them. Everything that they look at. We find that they're staring at the back of the head of other pedestrians, which is what they should do psychologically. We know that people do that. And we have a version of it that we can take outside our lab. This is outside our front door in Brooklyn, and that works on AR. So this is running in just running in an iOS ecosystem. In this case, it's running on an iPhone using Unity. Okay. So we then study how people perceive and sense the phenomena that are represented, visualized, and pushed to user participants in the simulations. And we look at how people perceive and sense them as embodied encounters and experiences, and we try to assess reality gaps between the two. So here's an example here. What we're doing here is we have trained the gaze of the drivers onto the user, and we're looking at what the user looks at. We also have the user wearing an EEG device, which essentially measures their attention. So they're in the simulation. The agents are staring at them. They're staring at the agents. We want to know what they're gazing at. When they're gazing at it, what's going on with their attention at different wavelengths of energy that's kind of emanating from their brain through their scalp. And you can see that they actually end up looking at the drivers and not at the built environment, even though the drivers are synthetic. So a question then is, how do we trace explanatory paths from pedestrian embodiment, upscale spatially, and upstream temporally to pedestrian phenomena? So this is probably going to involve some mashup between foundation models and autonomous machine intelligence, which is not really easy. There's probably barriers between the two. So in the near term, it's probably going to be some cycling between machine learning and between AMI. I think, or I would argue, that behavioral science can ease some of the interface between the two of those things, as can sensing science. So what can we learn from these tools? What can we learn by applying this to a mundane task, for example, explaining the embodied pedestrian flow of a pedestrian along a sidewalk? Well, we can pick out sensory cues, their world model, and their motion. We can map some of our technology stack to those things. And we can have somebody use some sensing devices with deep learning on them, with localization as a unifying factor. We can go out and collect some data. We can build some pedestrian agents based on those data, and then have somebody immerse themselves in the real world and simultaneously in a VR version of the model, and we can collect their data. So we can collect their EEG data, we can collect their EMG data, whatever it might be. So what do we discover? Well, substantively, we find a statistically valid change in EEG signal as pedestrians focus their gaze and their attention from faraway pedestrians toward incoming pedestrians. And we think that this is a phase shift from things that are far away to things that are nearby. This phase shift seems to be a function of the amount of disorder in the proxemics of the pedestrians in their personal space buffer. We think that this disorder is a composite of increasing collision potential and increasing neighbor relationships. So this seems to essentially be sourced in a very hyper-personal and context-specific deviation from what the pedestrian expects. So the pedestrian is walking along, kind of on autopilot, and then something happens. Their expectations are jolted because there's disorder locally around them. We see this flash up in their EEG signal in statistically valid ways. So we think that understanding these deviations and phase shifts, alongside sourced evidence in real-world observation, simulation-based experimentation to kick the tires on what it might be and what it might not be, and sensor-based measurement, could help us better understand the building blocks of embodiment. And if we can do this, it could be done in ways that can be transferred to new forms of an actively embodied artificial intelligence. So with that, I'll say thanks very much. A very famous album cover of pedestrians, and then what generative AI interpreted of the same cover. And I'd be happy to answer any questions. Thank you so much.
Okay, thank you very much. Any questions? Okay, I got a couple of questions. And first of all, you mentioned about social and which could be the interface. Another thing is whether you are considering about social interaction into the simulation.
So the question is whether we're considering social interactions in the simulation?
Yes.
Yes, we are. So we consider at the scale of pedestrians, it falls into the realm of social psychology, which is very qualitatively rich, but is maybe wanting for quantitative supporting evidence. So it's an area that we have an interest in. So one thing that we're doing is the idea of gaze has a lot of prominence in social psychology, and the idea of nonverbal communications. So the signals that we exchange with other people through our body language, that also has a lot of currency in social psychology. So there are two empirical metrics, gaze and NVCs, because we can build NVC graphs. We can track gaze with head-mounted displays and other things. So that they are two pathways that we're looking at, the role of gaze and the role of body language. In terms of the kind of hyperlocal social phenomena that we're able to explain from that, our most immediate target is crowd phenomena.
Okay, another question is how do you estimate the gaze or incorporate with the gaze into the human behavior?
So methodologically, within the VR, it's very, very easy because you just put a camera on the representation of the human subject in the VR world and you can calculate the gaze. You can calculate the gaze intersection with the environment. You can calculate where gaze is held. You can calculate how frequently people return their gaze and so on. In the wild, it's a little bit more tricky. One has to begin with eye tracking. So two eyes, you have to map those to an interim manifold and calculate gaze from that. And then you have to strip out when people are just like looking off into the distance. That's very different than when they are focused on a particular thing. So it's a little bit trickier in the wild.
Okay, and another question is, how do you do the large-scale simulation? Can you provide more details about the methodologies and the tools you are using for the large-scale simulation?
So for large scale, are you asking about the size of the built environment, or are you asking about the size of the number of agents?
I would say not really is about more about the graph. I guess that is more about the graphics part and how do you make those simulations.
So, so the graphics, we can do them just in, I showed some in the presentation that were OpenGL. And then I showed some other ones that were in Unity. And then I showed some other ones that were rendered. So we tend to do things kind of cheap, fast, and simple. And then, you know, exquisitely detailed, beautiful, and costly. We try to work on a spectrum from cheap to expensive, both in terms of time and computing resources. You know, a happy medium, of course, is Unity. Unity or Unreal are a happy medium because it kind of sits in that nice sweet spot between the two.
Okay, and another question is, you have some human pedestrians. Have you think about other environment like the vehicles or like the other somehow the animals on the street and into the simulation?
So I heard animals. What was the other question?
Vehicles, cars.
Oh, vehicles. Yeah. We have vehicles in the models. I don't know if you saw them.
I guess they are talking about the dynamic vehicles, the driving conditions, the driving on the road.
Yeah, we do. Yeah, so we have pedestrians, and then we have a counterfoil, which is drivers, and it's not just an animated vehicle. There's actually a driver model in them. So we play with different ones. So that's an area where we rely on other people's expertise. So we have a Carla-based model, which I showed, and then we implement the intelligent driver model, which is Dirk Helbing's group. We've also played around with Transims, but Transims is more of a traffic model and less of a driver model.
Okay.
Animals we do. We have another project with the dog in it.
Okay. Lastly, actually, that is my question. And there are quite a lot of research on 3D generation right now and using foundation models, like using some language or using some images as the input. And have you thought about using those kind of things into the 3D generation and or merge with your simulation with those 3D generation methodologies at the moment?
Yeah. So I mean, I think the next step for anybody that's kind of working in these areas is, you know, vision dash language models. So, you know, I think for us, because we're dealing with very hyper localized things and we're dealing with context, the idea would be to come up with a large language model that describes the context and that describes it in a way that perhaps matches some of the coding that we have from our observational coding, where we're standing by the side of the street with an iPad and we're coding things. If we can get an LLM to describe something back to us in a coded way, that would be a great kind of return input into our model. Of course, it sounds very, very easy in principle, and it's probably straightforward for some convenient things, but we're trying to dabble in the realm of the extraordinary and so on. So it's a little bit more tricky.
Yeah, absolutely. Yeah. Okay. Any other questions from the audience? Okay. If no further questions, thank you very much, Dr. Paul for it. And then we can get started with the next speaker.
Okay, can people online hear me now?
Yeah, they should, yeah.
Yep, okay. Sorry about that. Okay, so yeah, as I was saying, a star tracker looks into deep space, takes a picture of the stars, figure out where the stars are, and once you figure out where the stars are, there are two different modes of operation. The first is the loss in space solver. So if you don't have any prior information about where the camera is pointed, you recognize the stars by comparing them against a catalog of known stars, and you figure out your initial right ascension, declination, and roll. That initial process with no prior information is slower, but once you do it and you capture information subsequently, you have prior information of where you were, say, a few seconds ago, and that allows this relative tracking mode, which is faster and more accurate. So you know which stars are which, you just observe how they've moved within the sensor's field of view, and then can perform tracking there. So conventional star trackers using conventional sensors have various limitations. The first is low temporal resolution. So conventional sensors have a notion of an exposure time. So you start integrating light, you integrate for a while. The exposure time is driven by the amount of light you need to capture in order to generate a signal that allows you to recognize the stars. But that, in the case of a moving sensor, can result in motion blur. So motion blur makes it hard to figure out, where exactly the star is when the star field appears as a series of dim smears, as in the upper image. And another challenge with using an active pixel sensor for star tracking is that it's a synchronous memory intensive operation. You're taking a picture of deep space. Most of the pixels are empty, there's nothing going on there, but you spend a fair amount of energy reading those pixels off and then processing them when there's nothing going on. So when you're on a size, weight, and power or swap constrained platform like a satellite, reading off a bunch of pixels representing deep space and then processing them is a waste of time and power. And the last limitation is that the dynamic range of conventional sensors is limited, as you saw in the illustration before, as you'll see in the picture in the future. Star trackers typically come with these big bulky hoods. So the star trackers themselves are fairly small. They're just a sensor and embedded processor. But in order to keep out lens flare from the sun, they put these bulky hoods on. And again, satellites, especially these nanosat type satellites that are going up in orbit these days, are very small. And so having a very large bulky hood is problematic. So we use event-based sensors for star tracking. This is the sort of canonical example or the canonical illustration of what an event sensor is. If you're interested in event sensors, there's a whole workshop on this tomorrow here at CVPR. An event sensor, in comparison to a conventional sensor, first of all, it only reports when there's change in the scene. So if you're looking from a stationary camera at a stationary scene, an event sensor will generate, to a first order, no output. But when something changes, it generates events. So that's illustrated in this video that's playing here. So imagine a conventional and event camera looking at this disk with a black spot on it that's spinning in a clockwise fashion. It's spinning fairly fast. So in the upper part of the illustration, you see a series of frames coming in regularly, let's call it 30 hertz. And each frame is motion blurred because the object is moving quickly. And again, it's capturing these sort of regular pixel values everywhere on the sensor. By comparison, the event sensor, whose output is shown in the lower right, generates a time series of positive and negative events. So the positive events indicate those pixels that are experiencing an increase in brightness, in this case due to the black spot leaving that pixel's field of view, and the red ones, the negative events, are those that are experiencing a decrease in brightness, in this case the black spot coming into their field of view. So an event-based sensor has, compared to a conventional sensor, has low latency, It has little to no motion blur, and it has higher dynamic range. It also uses low power, especially when you're looking at star fields, because you don't have to read out all these pixels that are telling you that there's nothing there. So this seems like it has the potential to improve star tracking. Again, you measure changes in the scene only when something is changing or is moving. So there's a sparse data representation. There's less data to be processed. So you have to use less power for your embedded computer to perform the star tracking operation. It has low latency and mitigates the effects of motion blur. As we'll see, conventional star trackers have a fairly low tolerance to motion blur. So if the star tracker is rotating above, say, 3 or 4 degrees per second, then the images of the stars get blurred. Then it's hard to figure out where the center of the star is and produce any output at all. And the third advantage here is high dynamic range. So this problem that I mentioned of lens flare, where if the lens is accidentally pointing in the direction of the sun, you get on a conventional sensor regions of the image that are blown out, and then the auto exposure creating troubles that make it hard to see the dim stars. There's no global exposure mechanism in an event sensor, so event sensors are more robust to lens flare. But there's a whole body of literature about how to make star trackers and how to process conventional imagery for star tracking purposes, but there's a lot less of that for star tracking, although there is some body of work. And so we need to develop a new set of star tracking algorithms for event data. What event data looks like, again, is this time stream of these tuples x, y, t, and p. So for an event is literally represented as the x and y location of the pixel that's whose brightness is changing, the time at which that brightness change crosses the threshold, and a polarity, again, increasing positive polarity when the pixel is experiencing an increase in brightness and negative polarity when it's experiencing a decrease in brightness. So we need to come up with new algorithms for star tracking, and that's what we've been doing at Kitware for the last year or so. But there is, as I've alluded to, prior work on event-based star tracking. You see some of the references here. And the way people started doing this event-based star tracking work in the way that people sort of start doing event-based work in different applications is to first take the event data and to create a pseudo frame. So one of the common visualizations, like this event frame shown on the slide here, is to take essentially a histogram of the number of events that occur at a particular pixel over some time frame, and then treat that as if it's an image frame, and then feed it into your conventional algorithms. And that's fine, but it fails to take advantage of the advantages of event-based sensing. So more recently, there have been asynchronous event-based star tracking methods, some based on Huff transforms, some based on 2D Kalman filters. You see the references here, and we'll get to comparisons of them later on. But another, in addition to the performance implications of these conventional or these previous methods, which we'll see in a little bit, another drawback of the existing work in event-based star tracking is that the evaluation methods are somewhat artificial. So existing methods that evaluate the quantitative performance of event-based star tracking use a setup like the one that's shown here. So you have an event-based sensor on the far right, and it's looking at a screen on which various star fields are rendered. The star fields are rendered with known orientations, so there's quantitative ground truth of what the star tracking should produce. And so you can get quantitative results that way. But the downside is that, looking at a monitor with some front surface reflections, the monitors typically have some sort of LED illuminator that flickers a little bit and limited dynamic range. Looking at a monitor is just not the same as looking at an actual star field. And then, outside of these quantitative comparisons, the existing literature in event-based star tracking shows some qualitative results by sort of taking a camera, pointing at the night sky, and waving it around and saying, well, look, it seems about right. So this is something that we address in our work as well. So with all that context about what star tracking is, what an event sensor is, about the previous work in event-based star tracking. The three contributions that we make in our work are first, a novel event-based star centroiding method based on a rigorous analysis of event camera timing factors. The second is an extended Kalman filter for asynchronous 3D rotation and velocity estimation. And the third is the first data set of actual events of actual stars in the night sky, synchronized with the ground truth source, specifically an active pixel sensor star tracker, to enable quantitative evaluation on real event data. So I'll go into each of these in some detail, but that was previously the text summary of these, but this is what the visual summary looks like. This is, if you're going to pay attention to exactly one slide that I present, this is the one that you should look at. So we again have these three contributions. The first is that if you have a bunch of events generated by a star moving across an event-based sensor, so that's the left panel of this image. The positive events here are shown in red. Those are, again, the pixels that are experiencing an increase in brightness. The negative events, those are experiencing a decrease in brightness, are shown in green. And some of the conventional existing techniques just assume that the star is at the location denoted by the white X, which is sort of center of mass of the positive events. But in fact, the star, the true centroid location, is below that by some distance that depends, as it turns out, by the brightness of the star. And our centroiding technique, the first contribution, is a computational method to estimate the location of the star more accurately than existing techniques. The middle panel depicts the data collection that we did. So you see this EVK4 HD event camera. So that's an event sensor that's made by a company called Prophecy and manufactured by Sony. And it's there with just a machine vision lens. And it's mounted next to this CMOS APS star tracker. What you're seeing there is not actually the star tracker. The star tracker is this tiny little thing. But as I mentioned, star trackers have these bulky hoods to keep out lens flares. So that sort of bronzy gold looking thing is just a big baffle to keep out stray light. And each of these two sensors are rigidly mounted with respect to one another on this piece of plywood that when we do our experiments sort of teeter-totters with increasing speed. And you can see in the insets, the APS pixels, the event pixels, showing what a particular star looks like as captured by these different sensors as the sensors are undergoing motion. So again, the event pixels have this blob of positive events that are getting brighter because the star is going into them, and a tail of negative events that are getting dimmer because the star is leaving there. Everybody kind of knows what a motion blurred image of a star looks like, but that's what's shown in the APS pixels box. And in the output, as a result of this Kalman filter and the centroiding approach, the output of a star tracker is, again, the pose of the camera quantified as the right ascension, the declination, and the roll. So RA, dec, and roll, these three plots on the right. And in one of our experiments, which is captured over about 40 seconds, again, this platform that they're mounted on teeter-totters with increasing speeds. You can see that most clearly in the right ascension plot. And our approach, which is shown in red, gets smooth, reasonable values for the entire time. The conventional $70,000 active pixel sensor star tracker, its output is shown as these black X's. So at best, you get an output at about 2 hertz. But as you can see, for much of the 40 seconds of this high-speed teeter-tottering, there are no black X's, which indicate that the conventional star tracker is unable to estimate its attitude because of the motion blur that I alluded to earlier. And then for completion, this purple plot here represents the output of a previous method in event-based star tracking from Heng et al. And as you can see, it kind of goes off the rails at certain points because it doesn't know anything about roll. It's a 2D filter instead of a 3D. So this is just a table comparing our approach on the bottom to the previous work in event-based star tracking. Again, the state estimation is a 3D Kalman filter versus a 2D Kalman filter or ICP. We use this centroiding event that accounts for this magnitude dependent offset between the location of the positive events and the location of the star. We do quantitative evaluation on actual night sky events, but also do some LCD experiments, which actually aren't even in this presentation. Again, we're estimating the camera state as the 3D rotation and 3D velocity. We only do this slow loss in space step on initialization, and you can see the centroiding accuracy of our approach is quite a bit higher, and the update rate is also quite high. So that's the high-level summary of what we did, and I'll talk now for the next few minutes about the individual contributions. So the first that I mentioned is that there's this intensity-dependent offset between the centroid of the positive events generated by the event sensor and the actual location of the star. So again, this depends on the brightness of the object. So the illustration here shows a dim, a medium, and a bright star as those stars are moving across the sensor. And you can see for the dim star, the displacement is fairly small. If you were to use the positive event centroid as the location of the star's location, that would be not bad. It would be off by less than a pixel. In the medium case, you can see now that in this case, the star is moving from the bottom to the top. In the medium case, you can see that the positive event centroid sort of estimates a location of the star that's ahead of where it actually is, and that separation gets even bigger as the star gets brighter. You can also see that the shape of these positive events goes from sort of an isotropic kind of blob, a defocus spot, to a more anisotropic thing, to this sort of crescent or bow shock shaped frontier. So again, this illustrates that there is this intensity dependent offset between the centroid of the star and the centroid of the positive events, but it doesn't tell you where that comes from. So it comes from, as shown in this illustration here, the fact that an event sensor generates an output when something is changing. But for stars, which are unresolved objects, they appear as Gaussian blobs of brightness on the sensor due to diffraction of the lens, and at the actual location of the star, which is the middle of that centroid, the Gaussian has zero derivative, right? So at the peak of a Gaussian distribution, the derivative is zero, so there is no change, and so there are no events that are being produced there. Instead, especially in the case of these bright stars in the bottom part of the illustration here, the steepest part of the intensity distribution is actually in front of the star. So the area of greatest increase in brightness is in front of the star by a distance that depends on how bright the whole thing is. So again, once you know the brightness of the star, which one does when you're doing star tracking, you can determine both analytically and empirically an offset that needs to be applied to the centroid of the positive events in order to get the true location of the star. So I won't go into it in the presentation, but we have this analytic model of what this distribution of positive events should look like. It's shown in the theory row here of this figure, and on the top you see the measured noisy actual event streams for dim, medium, and bright stars. So stars have this strange measure of brightness called apparent magnitude, which is this inverse log thing, and so bright stars have a smaller apparent magnitude, and the numbers get bigger as the star gets dimmer. But anyway, you can see that the agreement between the theoretical and the measured event distributions is quite good, as is the offset between the true star location and the observed centroid of the positive events. So, this overall theoretical model can be computationally a bit much to do in real time. And so what we have is a quick approximation that's described in the paper that tells us in real time what sort of offset to apply based on the star brightness to offset the location of the centroid of the positive events to tell us where the actual star is. So again, the key idea here is that the true centroid is offset from the positive event mean by some amount of pixels that depends on the brightness. And again, the brightness we know because we're tracking stars. Star catalogs have brightness information in them. Okay, so that's how we figure out where the stars are. I'm only going to talk very briefly about the extended Kalman filter that we use to estimate the sensor's orientation. But again, existing work uses a 2D Kalman filter that doesn't capture basically the roll axis here. So we have an extended Kalman filter for both the rotation, which is the thing that we're explicitly estimating and outputting, and that the values that a satellite's guidance navigation control system would use, but we also estimate the velocity in those three directions in order to support prediction in the case that the sensor is temporarily blinded by perhaps looking directly at the sun. So graphically, how this works is that we have this initial state, we have the camera looking out at the stars. There are these quaternions that give us a representation of the right ascension, declination, and roll, and then we have the velocities in these three directions. You can apply a prediction step where you just extrapolate based on the previously estimated velocity to figure out where it should be some period of time later. And then we get some measurements, some events come in based on stars moving across the field of view, and then we can mix the prediction and the measurement in order to update our state vector. And again, it's the right ascension, declination, and roll that are ultimately output here. So there's a bunch of derivations of this in the paper. I won't get into it in the talk here. If people have a lot of questions about this, I would encourage you to come by the poster on Friday because my colleague Dennis, who will be there, can do a better job of answering Kalman filter related questions than I can. So that's the Kalman filter and how we take the star centroids and turn those into right ascension, declination, and roll. And again, the third contribution of our method is data collection to enable quantitative evaluation of event-based star tracking on real data instead of monitor data. So there's a whole setup to do this. I showed you on the previous slide this setup here where we have the event camera over here. We have the conventional star tracker. In this view, you can really see that the sensor and the embedded processor are actually quite small, but the size of the star tracker is dominated by this big baffle here. And in the earlier illustration, I showed you these mounted on a piece of plywood, but here it is on an angle bracket instead. But both of those are attached to this pan and tilt motor. There's a whole contraption here to synchronize this data. Event-based sensors have this exterior input capability where you can inject a signal so that some sort of external reference appears with a timestamp on the same scale. So there's a lot of stuff about the synchronization, which again, my colleague Dennis, who's presenting the poster on Friday and also tomorrow at the event-based vision workshop, could tell you a lot more than I can. But we went out several nights. Our offices in Minneapolis, Minnesota. We went a little bit north of the Twin Cities to get outside of the light pollution. We did a number of experiments at a place called Ham Lake, Minnesota. So again, we pointed the thing up at the night sky, and you can see sort of the setup we had there on a dock. So, okay, we captured with that setup that I just showed you multiple tracks at the night sky. This is all part of a data set that's released in conjunction with the publication of the paper. And so the motorized stage sweeps out different motion trajectories with different velocities. We were limited, of course. There's a bunch of cables sticking out of this thing, so we couldn't, sweep out arbitrary patterns. but we captured 9 or 10 different families of different motions, a couple of which are illustrated here. So in these illustrations, the one that I showed before with this increasingly fast teeter-tottering motion is shown here. So you see the right ascension, the declination, and in this case, the roll is encoded in the color coding as a function of time. And again, these other sorts of motion profiles that we captured in the data. So now we have finally the set of quantitative results. Again, there are these 7 different captures that we had with this sort of teeter-totter with different velocities. We had this multi-pose, as we called it, which is shown here, which is sort of jags between different positions, and then a smooth sine function and this thing we call the tilt ladder. And for each of these, you can see the durations of the data capture, the right ascension, the declination, and the roll ranges, the maximum velocities, the star magnitudes, both the dimmest and the brightest that appear in the field of view during that time. And then on the bottom, what you see is for each of these data collections, the accuracy of our approach on the bottom compared to an ablation of our approach, and then these 3 previous works in event-based star tracking. And not surprisingly, since I'm here talking about it, our method outperforms the other methods actually by quite a bit. So as you saw in the qualitative example earlier, the 2D Kalman filter tends to go horrendously off the rails from time to time. So the accuracies here, which are split, there are 2 numbers. The first one is the across accuracy, so that's the accuracy and right ascension and declination. And the bottom number, which is always worse, is the about accuracy, which tells you about the roll of the camera. So anyway, you can see that our approach does quite a bit better. This velocity-dependent offset that I mentioned significantly improves things. The exception to that is when there are not particularly bright stars in the field of view, as there are in these 2 columns here. So again, we're doing quite a bit better than the existing star tracking methods. And here we're using the conventional star tracker as a source of ground truth. And as I mentioned earlier, conventional star trackers are typically limited to about 3 to 4 degrees per second of motion before they totally give up. And so all of these numbers here in this row are pretty small. But we also, as I mentioned, have these other cases where the velocities exceed 3 degrees per second, and the conventional star tracker, which again is denoted by these black X's at most at 2 hertz, will fail to give an output. So we have no ground truth for that. The motor encoders of the thing that we're using to induce motion, those are not nearly precise enough to get us arc-second accuracy. And so, at best we can show you qualitatively that this teeter-totter thing looks like we're doing the right thing, including the places where our notionally ground truth sensor gives up. So, conventional star tracker at best gives an output of 2 hertz. If it's not moving too fast, our method gives an output at 1 kilohertz. And as I mentioned, qualitatively we can show that we can generate outputs at much higher velocities than the conventional sensor. So this visualization for people who haven't looked at events is a little bit weird. So the black background is just empty parts of the sky. These white bits, these white things sort of sprinkled in here are positive events. So here we're only showing positive events. The blobs of positive events that we can correlate to a known star in the catalog are circled with these white circles, and you can see that we are outputting again the right ascension, the declination, and roll, but we're also estimating the instantaneous velocity in those 3 axes as well. So as we play this, you see that there are a bunch of stars that come in and out, especially the dimmer ones, but you only need a few different stars to maintain a track once you know where you are. You see that we've now changed direction and growing faster, and we're going to change direction and go faster again. If you look at the velocities here in Y, right now we're at about 3.5 degrees per second. That's when the conventional star tracker would give up. but here we are still tracking at 5 point something degrees per second, and now we're up at 7, and we're still able to track these stars and compute a right ascension declination. So again, that's the sort of qualitative demonstration of the improvements. Here's how this looks if we plot in red the viewing frustrum of our event-based sensor, and then in blue the viewing frustrum of the conventional star tracker. You'll see the blue one gets stuck at some points because it is moving too fast and it can't tell where it is. So we provide an output throughout, but the conventional sensor pauses and gives up. So just to summarize, again, the 3 main contributions here are a novel event-based star centroiding method based on analysis of the event camera circuit timing. This is more accurate than previous methods, allows us to get single digit or less than 20 arcsecond differences as compared to the conventional star tracker. We also developed an extended Kalman filter for asynchronous 3D rotation and 3D velocity estimation that allows accurate estimation up to 1 kilohertz output rates. And we also generate the first data set of events synchronized with ground truth attitudes from an active pixel sensor star tracker, so that people can finally do quantitative evaluation of event-based star tracking with real events. and as we showed with that data, our approach is an order of magnitude or so more accurate than existing methods. I mentioned this is a poster highlight on Friday afternoon. We're an open source software company, so the project, the code, and the data here are all available via these QR codes. We'll also have these up at the poster on Friday if people want to come by and take a snapshot of them. So that's what I've got. I'm happy to take any questions. Yeah.
Hi. Very impressive presentation. I wonder, regarding calibration, how do you go about calibrating these type of sensors, especially lens distortion and such?
Yeah, so some of the basic things that we take for granted of having tools for with conventional sensors are a little bit more complicated with event sensors. Even something as simple as focusing them is kind of a nuisance. But basically what we do is we point the event sensor at a checkerboard with a strobing light in the scene, and then we can figure out where the corners are and do the sort of, conventional lens calibration to undistort the field of view.
And another question is regarding outliers. Is there any problems about that you have to explicitly capture outliers on the space?
Well, there are different outliers in different ways. Somewhere in here we have an illustration. So as I mentioned, one of the hopes for event-based star tracking is that we can be more tolerant of lens flare. So what this illustration is, what this video is showing, albeit with a purple background instead of a black one, is panning across the night sky as the moon comes into the field of view. I should say all of our testing so far has been terrestrial. So once you get up above the atmosphere, the moon isn't as big a problem as the sun, but here on Earth, the moon produces a lot of lens flare. So what you can see here is that there are a lot of positive events generated over here, some sort of outlier events from lens flare from the moon. And what we've shown is that, computationally, these look very different than, stars that are all moving as point sources at infinity. And here's the moon proper now in the field of view. And so there's certainly noise suppression techniques that are specialized for event sensors that we haven't had to use so far, but are available for other applications. And then in this case, we can track the stars through these blobs of lens flare, which are a type of outlier.
Thanks.
Sure.
Okay, let me read a couple questions. Does it only work in the night, and what about in the daytime or the not quite lot?
Yeah, so the question was whether this can work during the daytime. Obviously, during the daytime here on Earth, there's a lot of light scattering from the atmosphere. conventional star trackers are generally intended to be used on satellites in space, and so the stars are as bright whether the sun is pointing at the satellite or not. But I should say that there's other methods in the literature and event-based sensing literature that, for instance, have demonstrated being able to track a satellite during the day. That requires a much larger telescope, a much larger lens than the one that we are using. But there are still ways to do that if that's of interest to somebody.
Also, does the weather affect the tracking result?
Yeah, certainly we did these data collections on clear nights. Again, the ultimate use case of this is to have the sensor attached to a satellite up in space where you're not worried about the clouds. But this is earlier research. There are actually multiple, I believe, event sensors up in space. One on the International Space Station that produce some actual space-based event data that we're working to get access to test our method as well.
Okay. Also another question, and you mentioned in the talk that brightness is pretty much a major factor, and compared with if there are some bright light and there are bright stars, and have you compared with RGB images just for tracking and with compare with the event camera?
Yeah, so the comparison to, well, not RGB in the sense of color, but like a conventional sensor is baked into this plot that I was showing before, where what's going on and why the conventional star tracker fails to produce an output during this part of the experiment is that it's moving too fast, and the star to the conventional sensor looks like a dim smear, and you can't tell where the star is if it appears as a dim smear rather than as a sharply focused point.
Okay. Any other questions from the audience? Okay, then I have read all the questions. Yeah, thank you very much.
Okay, thank you.
Hello, can you hear me?
Okay. It seems like it's not the correct screen. It's not the presentation mode.
Are you able to hear me?
Yeah, we can hear you.
Okay, great. So you're saying you're not seeing it in presentation mode right now?
It is correct one. Yeah.
Right now it's fine. Okay, great.
Okay. Let me introduce the next speaker, and Dr. Yevgeny Vorovay-Chik. Sorry, forgive me if my pronunciation is not accurate. And is in computer science and engineering at Washington University in St. Louis, and he was an assistant professor earlier on at Vanderbilt University. And he has won quite several awards, and including NSF Career Award, and he was invited to give a talk on each Kai in 2016 on early career spotlight talk, and he received several Best Paper Award as well, and including the 2017 Best Paper Award in Health Informatics. He was nominated for the ACM Doctoral Dissertation Award and received honor mention in 2008 on IFS a Mars Distinguished Dissertation Award. And his topic today is visual active search.
Okay.
Yep.
All right. Well, thank you for inviting me. So I'm going to dive right to it. So visual active search, what is that? So it's at the high level, it's a decision problem guided by visual information, as well as reliable feedback. So a little bit more specifically, let's say you have a two-dimensional area map that you start a priori. And I'll give you a little bit more concrete examples momentarily, but I thought I'd start with somewhat of a formal model first. So you have a broad area map of interest, which you can think of as a set of two-dimensional location coordinates, and it's divided into smaller grids. You have some prior information about it. Commonly, this could be like a satellite image, for example, of this map. And there's going to be a total exploration budget. What we can do is we can traverse this area one grid cell at a time, or potentially multiple grid cells at a time as a generalization. I'm not going to talk about that here, but it's straightforward to generalize. When a grid cell I is traversed, the key aspect of VAS is that it reveals potentially up to two things. First of all, it can reveal a high resolution visual information or features of this area. And second, and more importantly for purposes of VAS, it also gives us a ground truth, for example, class label associated with the grid cell. And so traveling from grid cell I to grid cell J has some cost. So ultimately, this is going to be a decision-making problem. And what we're going to try to do is maximize utility. So what is the utility here? It maps a class label of a location or grid yi to utility value u of yi. Commonly, what this is going to be is very simply, we're going to be looking for targets in this space. If a grid cell has a target and we explore it, we get a 1. And if it doesn't, we get a 0. So in most cases, it's going to be as simple as that, but this allows pretty straightforward generalizations. Everything I'll talk about allows an arbitrary utility definition. Okay, so our goal is nominally to maximize the total search utility over a sequence of queries, where queries are just can translate directly into moving from one grid cell to another, but they don't have to. You could be moving physically, you could be moving as in a drone flying overhead, you could be driving through it, whatever it is. You could even just be moving, let's say, a camera from one location to the other as part of the search, although the reliable feedback part would require something more than that. And I'll get into that later as well. Okay, so here in this definition, Q is a set of locations or grid cells you've visited during a search, and you're going to impose additionally a budget constraint that the total cost of doing this exploration is at most B for some predefined cost function. So making it a little bit more visually concrete, let's say here's their special area, happens to be around St. Louis, which is where I am at. And let's say you have a satellite low resolution image, which is your prior, and you're trying to find all military installations, or really anything you want, just as an example here. Right, so this would be corresponding to, let's say, yi equals 1, let's say is a military base, and equals 0, that means it's not there in the grid. So what we can do is iteratively explore small subregions, okay, in order to obtain reliable information about these. Okay, so here's the example. So what we're going to do is we're going to sequentially query. I'm going to use query to just abstractly refer to any sort of exploration. Let's say we query this region right here. Okay, so in each step when we query, we obtain new information that we can incorporate into future decisions. So for example, we can zoom in, and this gives us higher resolution information about the region itself. I'll call this XI. And additionally, we get a label. For example, this happens to be a town, and this is YI. So the key aspect of VAS is that we have online feedback. As we search an area, we get some additional information about this area, which we can use in order to decide where to search next. Okay. In particular, the key challenge in VAS is the tension between exploration and exploitation. In particular, whenever we query something, we get useful information that allows us, for example, to learn better where to search next. But in addition, and this is also a key part of visual active search and really any active search, is that what we're actually trying to find are actual objects. So whenever we explore an area, if it happens to be the case that we also find the object of interest, that contributes directly to our utility. So the first one is going to give us just informational value. So even if it doesn't contribute to utility, it can contribute to future utility or future reward. The second one actually directly contributes to immediate utility, but also it gives us some exploration value, contribute to future utility. And really what we're trying to do is design search policies or learn search policies to balance this tension. Now, just as an aside, mention a few closely related lines of research. I'm not going to spend a lot of time talking about them. but I'm guessing the folks in the audience are probably well familiar with some or all of these. Of course, this is closely related to localization and detection that I'm sure everybody knows. They'll note that that's just a prediction task. It's not exactly a search task, which is what we're solving here. Active perception and sensing has been around for decades. Here you determine where to look by changing, for example, camera positions or focus and so on. But still, it's focusing ultimately. The goal is prediction efficacy and not something else. Something that has search in the title is mechanical search, which is more of a robotic task and is closely related to where we're trying to find and retrieve a target object, typically in a cluttered environment. In all three of these, the crucial distinction is that in visual active search, we incorporate reliable feedback about the locations that it has queried so far. And in other words, we get this YI, the actual labels as we search a location, and that contributes to both information that allows us to search better in the future, as well as directly towards our utility, as I've mentioned earlier. Now, this actually builds directly on the research area that's been pretty active, no pun intended, which is called active search. In this area, fairly abstractly, you're given a set of feature vectors and a budget constraint, and the goal is to maximize the number of targets or positive labels identified based on feature vector queries. Typically, these are going to be binary classification tasks, but doesn't have to be. And so, like I said, we're building on this, but conventional approaches are not typically vision-based, and they tend to use typically predefined ex-ante heuristics as well as simple learning algorithms, and don't work particularly well in high dimensions. I'll show in the experiments some data to confirm this. The key idea in VAS is that we're actually going to use past training data, or for example, past image data, in order to learn how to search. That's the goal. All right, so I'll start with a fairly basic variation of visual active search, in which the prior is just a given overhead image, just the way I showed you earlier, of the entire area. And we only obtain just the true label information. There is no zoom in. We just get the YI whenever we explore a location or grid cell on. Okay, so one observation is that we can model this problem as a Markov decision problem as follows. Really, the key parts to it are going to be search state definition, reward function, action, and transition. So search state here is going to be, of course, where you are. It's going to also include or incorporate some summary of exploration history, which we can actually just represent as a matrix, which cells have been visited, as well as associated labels, and of course the prior information, which is our, for example, this overhead image that we have a priori. Reward is very simple. Every time we explore something, we either get a 1 if we explore, or the utility, whatever, for the current grid cell to explore, either typically a 1 whenever we actually have a target in that cell, or 0 otherwise. That's going to be the immediate reward. Action is also pretty straightforward. It's going to be decision which grid cell to visit next. What is not straightforward is transitions. Okay. The reason it's not straightforward is that, of course, it's determined by what we decide to do. But the key part of the transition is figuring out what saying something about what is in the location we explore. And that's going to be, by definition, unknown joint distribution based on unknown joint distribution over image input and inputs and labels. And so how do we deal with that? How do we deal with this unknown distribution? The answer is actually pretty simple. We're going to use deep reinforcement learning and the data set of ground truth overhead imagery, which is annotated by targets of interest in our case. So let's say if we predefine a target of interest, let's say we want to find all the bridges in a particular scene or image. And I'm going to call this a task. We're given this overhead image of a large area. We can explore small sub areas of it one at a time. And let's say we want to find as many bridges as possible. Every time we explore, we either find a bridge there or not. If we find it, we get a utility for it. If we don't, we keep exploring. Actually, we keep exploring either way. We're going to try to find as many of those as possible. So each image done corresponds to a task with the annotated target locations. This is in training data. And execution time, of course, nothing is annotated. We start with just the image and get feedback as we search. And so here, what we're going to do is we're going to train a search policy which maps search states to action for any new previously seen search task, right? So we use training data. We train this policy network using actor-critic approaches. And when we apply it to a new image, it tells us essentially over time where to search next as a function of the input image, as well as the search state and remaining query budget. Okay. So here's the experimental evaluation that shows that this idea, even at this very simple instantiation, actually works quite well. So a few baselines, I'll just go through them very quickly. Essentially, qualitatively, of course, there's a random baseline, but basically, greedy classification is just the question, can we just do prediction and nothing else? Does actually paying attention to what you've seen before, how much does that matter? Greedy selection is a bit better than just a standard greedy classification. It's based on a paper from CVPR 2020, which selects which grids to zoom in for, but it's not the same problem. Active learning is not the same problem, although it's close. In active learning, you're trying to do your best to try to make predictions better, but you're not accounting for the fact that where you query also gives you immediate utility. And of course, classical active search I've mentioned earlier. We use data sets like XU and DOTA, which are the satellite imagery data sets that are annotated for what's in there. And the metric is very simply average number of targets we've discovered within a given budget. And so here's some results. Bold indicates our approach. This is just on DOTA data set. One particular target here happens to be a large vehicle. The vertical, the columns are going to correspond to the C equals 25, 50, and 75. That's going to be just the total cost budget. And VAS is our approach on the bottom. And so we can see actually that just over the baselines, the advantage is quite dramatic. So for example, looking at C equals 50, in the bottom set of plots where we have a finer resolution of the grid cells, VAS does dramatically better, in some cases twice as well as the best baseline, which happens to be, I think in all cases, greedy selection. So what this shows is that clearly explicitly accounting for information gained during the search and in the search policy is actually extremely valuable. And none of these baselines really work particularly well. Okay, so that's the basic idea. But this has a number of limitations. First of all, the key limitation is that it works just fine in cases that are sort of in sample, which means that you have the same data set, you just sample the same tasks from the same data set that you've seen in training, and you use the same, and essentially it gives you similar types of tasks, similar types of images. But performance is going to degrade quite quickly, as we have in experiments, when this is not the case. For example, in your data set, or especially when you have trained on one set of targets or one target, and then you execution time is on a different target entirely, that degrades extremely quickly. In addition, it requires us to predefine what target object is up front, because that has to be the same for training and execution. Okay. And it does not fully adapt, really doesn't adapt at all, really, except in context, if you will, to the information obtained online during the search itself, which seems to be quite suboptimal. Okay. So to address these problems, I want to step back for a moment. So what do we have here? We have a training data set of tasks, which are really broad areas, along with associated images. And we'd like to train a policy. Okay, we're given a new search task of the same kind. Okay, in the basic approach, we just have pre-trained a search policy, and this search policy is fixed for any task at execution. Okay, so that's fine. But notice that we're getting actually new ground truth data as we search. So the fact that we're not using it fully, for example, to improve the search, to fine-tune the search policy itself, seems really weird. We should somehow figure out how to do this, but it's actually not obvious how to do this. So how do we? Okay, so I'm going to actually abstract this even further and just talk about POMDPs for a second. So POMDP is is defined as a collection of states, actions, observations, transition distribution P, initial state distribution, and which I don't indicate because it doesn't matter so much here. Rho is the observation distribution. We don't know either P or Rho, and some reward model. Okay, so an interesting idea in the literature on POMDPs is something called Einstein observability. So it means that if we observe a true state after executing the trajectory for each step of the trajectory. So let's say for our purposes that we know the true state during training. That's what's going to be important. Okay. Suppose further that the observation model is invertible, by which I mean simply like for much as a state can correspond to many different observations. Once you have an observation, whatever constitutes as relevant information for state, you can in principle identify uniquely. It might be hard to do this, but you can actually in principle do it. Okay, and this is in visual tasks that we face oftentimes is actually a fairly reasonable assumption. It doesn't always hold. It requires observability, of course, and visibility, but it will often hold. Okay, so this motivates an idea which we call partially supervised reinforcement learning, or PSRL. Okay, so what we do is train a policy f of O that predicts state from observations, really any finite history of observations, but nominally I'm going to say just observation, current observation O. In addition, we also want to have a policy, but the policy actually is going to map predicted state based on observation to the actions we'll take. And the key idea is we simply train those jointly. Okay, so we observe, in particular, the way it's going to work is we observe S and O. S is the true state, and O is the observation pairs during reinforcement learning training itself. That's using this hindsight observability assumption. And we then jointly train the state predictor F, as well as a policy where state is just going to be predicted by the state predictor F. Of course, at execution time, we don't have that. No problem. We plug in FO into the policy, and voila, we're done. Okay. So let's go back to actually just an illustration of this. In some domains, this works really well, although it's much more complicated story in practice. But that's not the substance of my discussion. Let's go back to the problem at hand. So notice that model of visual active search as a MDP, much as it's a model, it's missing something very important. Okay, what the true state is not really quite search state. The true state in this world is the true locations of the target. And image is actually just an observation thereof. And so we can apply the intuition from this PSRL, really the idea from PSRL, to VAS as follows. So what we can do is learn a model f of x to predict, this is just a computer vision test now, we want to predict whether or not the grid cell has the target given its image input. So this is just image classification problem. This induces a matrix of predictions, P, which are just predicted probabilities. And what we want to do is we actually want to learn a search policy which takes P, the predicted probabilities, as input in addition to other things like observation history and so on, this observation state. So why is this helpful? The reason it's helpful is actually now we have what to fine tune. We can train and fix a search policy, but what it now is able to adapt to is improved performance in terms of predictions of where stuff is in the particular instance of the task we're given, based on the collected ground truth, which we collect online as part of search. So that's very nice, but that's actually not enough because there's something else going on here. So if you notice that really the underlying problem is actually a meta-learning problem, right? What we're actually trying to do is not just learn to predict. What we want to do is learn a function, a model F that is able to predict and be fine-tuned really well, but not for its own sake. We don't just care about predictions. We want to be able to predict things in a way that guides the search policy very well. Okay, so this suggests, and this motivates us to design a separate meta-learning algorithm where essentially what we do is as follows. What we do is we simulate a training time parameter updates, essentially fine-tuning steps for each task that we get during training. So we sort of simulate a fine-tuning of this prediction f of O. And what we do is we update the policy and we update using gradient-based techniques initial parameters of this prediction model that optimizes search utility. Okay, so this combination with sort of joint training allows us to really optimize for not just for prediction, but actually for search, such that we fine-tune during search. So here are some experiments for this domain. The key idea here that we have a whole host of experiments. Here, the key idea is that we're actually testing with a target that we didn't see during training data. So this is really specifically testing the domain adaptation problem and also different distributions of the tasks as well. So here we have 3 different domains, a bunch of the same baselines that we had before. Also this sort of simple baseline for VAS here is one of the baselines, as well as online test time adaptation. Now, the other thing that we compare it to is the variation where we just ignore the fact that we're in a meta-learning world and simply train it the way we would train kind of VAS, except we now add this prediction as a pipeline and code train. That's PSVAS. And so there are 2 key observations from this data. First of all, just adding the predictions themselves helps, but it helps at best marginally. Sometimes it doesn't help at all. The best baseline here is online tested TTA. Actually, if you notice, comparing that to VAS, it doesn't help very much either. Okay, so really just doing test time adaptation in conventional ways doesn't help much. Doing just standard, partially supervised enhancement of VAS doesn't help very much. What makes a huge difference is combining that with meta learning. And that's the last line here, MPS VAS. There you have actually what in many cases, not all, but in many cases are pretty dramatic differences. Just one example is test with Harbor as target. It goes from 7-ish, which is the best baseline, this is PS VAS, to 9 total utility on average that you get. Now, not always do we get much bang for the buck here. Tests with a large vehicle as a target, you don't get a lot, possibly because it actually is already fairly well optimized for that task during training. Okay, so that's some basic foundational techniques. And you might be wondering now, okay, that's very nice, motivated by somewhat abstract problems. Is this real? Or does this map to a real social problem? And here's an example where it does. Tenant eviction outreach. The problem that's been faced, this has actually been acute a few years ago, particularly post-COVID, but it's really kind of a constant problem in many urban areas. Tenants often face eviction proceedings because they're just in a temporary lifetime crisis. For example, losing a job can put you into a tailspin. You're not able to pay rent temporarily until you find a new job, unless you have a ton of savings, which if you're a low-income household, you will typically not. And so you're unable to pay rent and utilities. This in turn causes all kinds of side effects, right? On the other hand, there are actually lots of different resources available to people who fall in hard times. There are special programs from utilities themselves. There are city, state, and government, federal and state government programs. For example, short-term rental support that sometimes they're available in particular jurisdictions and so on. There are sometimes free legal support, many such things. They vary in time. Practically nobody knows all of them, but specialists. And so you can't expect the renters to be aware of these opportunities. But these opportunities can be transformative. If you know, you can apply for these programs, and that can actually help you go along for a few months until you get your job back and are able to actually pay back the rent. Okay. Now, once you get evicted, it's really dramatic. It's very hard to find a new rental. It affects credit history, and so oftentimes sends households to downward spiral. It's difficult to get out. So one mitigation that have been actually deployed, people have been doing this, is you hire people or people volunteer to canvass rental units that are at high risk of eviction. Now, you don't know this a priori. And so what you're actually trying to do is you're trying to actually identify renters who are at high risk of eviction and then you provide this information. Now, canvassing is expensive. You typically don't have tons of, armies of people volunteering to do this. If you have to pay them, that gets expensive. There's not a ton of money for this sort of thing. And so the question that does arise, how do we best allocate limited canvassing resources for this task? Now, in practice, we have all kinds of data to support tasks like this. We have visual imagery, we have mapping, we have address level features, and so on, that would constitute jointly features of the particular locations or grid cells XI. We can send multiple canvassers to visit units, okay, and provide this information. The way that we get reliable ground truth here is that canvassers, when they encounter a particular tenant, they ask them to complete, say, a short survey, and that provides highly reliable information about the high eviction, whether they're at high eviction risk or not. They'll ask them whether for example, their renter has been after them and so on. So you can get that very, very reliably. But these are, of course, I've mentioned, limited in number because of the, as well as in time. So this imposes very naturally budget constraints. And cost here translates just to, for example, time traveled between different locations. So this very, very naturally corresponds to a visual active search task. There's only one small problem, which is scalability. The kinds of solutions that we've proposed so far address scalability at the level of 100 grid cells or hundreds of grid cells, let's say at the most. If you're looking at a area like St. Louis, where you're trying to send canvassers and find how to best disseminate this information, you're looking at tens of thousands of residential properties that you have to be able to reason over jointly. So the approaches that I've described so far simply will not work. So how do we deal with that? And the idea is a combination of hierarchical reinforcement learning, as well as a particular way of parameter sharing in this hierarchical RL. So here's how it works. We would train jointly two policies. One is a high-level policy that subselects a region, which would initially pre-discretize the whole map into a tractable number, let's say 100 of broader regions in this area. And then we also train a low-level policy, which, given a region which is selected by the high-level policy, is going to select the actual place to go to. Now, the key idea here is that we can actually share parameters. So we can just train a single low-level policy, even though a priori, each household is different, but we can actually distill a household into its features and just renormalize probabilities after the fact, which allows us to essentially do all of this parameter sharing, makes training very, very efficient. And so here are the results. I'm going to speed up a little bit now to just get through the rest of the talk. But here are the results, and you can see that the search budget, by the way, here it seems very large. It's 80,000, but it's at the scale of distance, not at the scale of resources. So that's why it looks very large. But in any case, so we can see that this leads to dramatic improvements over all prior art, including just like throwing kind of vanilla visual active search here. It's called AGS for active geospatial search, but it's basically the same sort of thing. Okay. Now, there are additional practical challenges with the problems I've described so far. First of all, I've assumed so far that we observe, at least at the visual, at the feature level space, everything about the area of interest. And of course, in practice, that's hardly ever going to be true. I mean, that's going to be true in certain specialized scenarios, but a lot of the times you're not going to see everything up front. Number two, information can be oftentimes is multimodal. You might actually specify targets, for example, very generically in natural language. You don't want to predefine a set of classes that correspond to targets or labels. You can also get information as well as pre-specified targets that you would just give as an image, right, or natural language. So we want to be able to do this in multiple modes at the same time. Let me address the first problem first. Suppose we don't observe the entire area the whole time. But whenever we do query, we do observe XI, the actual, let's say, a image for this area, as well as the reliable label YI. For example, you can observe an image at high resolution. You can send it to an analyst via some connection, and this analyst could tell you what's going on in this image. So it gives you reliable real-time feedback as well. Of course, this is all going to be costly, no question about that. So you'll still have this limited resource constraint. So how do we do this effectively? For this, we essentially leverage diffusion models as a way to be able to do effective reconstruction of the image of the entire area in real time in a way that also adapts as we search. Now, long story short, of course, we have to actually train everything jointly. And how do we do this? So we design a reward function that actually combines the reward that's specific to encouraging the diffusion model to predict effectively, but as well as encouraging it to also explore. So encouraging exploration where we have the most unreliable information about reconstruction. In addition to the the reward I've described earlier, which encourages just or optimizes for search efficacy itself. Okay, and again, just a quick snapshot of the results to demonstrate that indeed our approach here works quite well in leveraging the diffusion model and reconstruction to be able to do this really well compared to all the baselines that simply just directly leverage whatever information we obtained during the search and nothing else, which is MPS-FAST, for example. All right, and the final question that I'll address is this multimodality issue. So like I've mentioned, our goal here is going to be more, basic. We just want to get to a particular location. We just don't know what it is a priori. Okay, so it's kind of like a special case of finding as many targets as we want, except we only have the one target that we need to find. This location, as well as any feedback, can be actually provided in multiple modalities. For example, in natural language and in visual information from multiple, for example, aerial image as well as ground level image from multiple vantage points. So the challenge is to be able to deal with targets as well as feedback in a way that can be provided through these multiple modalities. And the approach uses a combination of LLMs, which allows us to actually kind of specifically tune the embedding that we train to the planning tasks at hand. We use CLIP, but you can use other approach is to align representations across modalities to make sure that, so to speak, the different information that we get actually speaks the same language. And we train kind of jointly a localization policy using reinforcement learning, as well as this LLM-based history conditional embeddings. Okay, this is just a visual illustration to show or to illustrate that no matter how we provide the target information, be it land-based image or text or overhead image, the policy itself that it induces gives you both sensible and pretty similar distribution over what you're going to see here. In all cases, it reaches the goal, which is what we want. But also the distribution is fairly sensible in terms of stochastic policies you sample with a different goal specified. And here are the actual quantitative results. Here, especially what's remarkable is the bottom table, which shows zero-shot generalization to a different data set and different targets that we've never seen before, have never specified before. And all baselines are really quite terrible, as you can see, whereas the proposed approach, this GOME-GO approach, is really quite effective in these domains. Okay, so just to summarize and kind of anticipate some additional applications that warrant their own study. So the spatial active search problem, I think, is a very general and quite powerful framework for identification and discovery in environments with a 2D topology, like geospatial environments. And what I showed is a host of techniques for this problem that addresses various aspects of the problem, combining reinforcement learning, multimodal embeddings, diffusion modeling, and so on, to be able to actually address numerous problems that you might encounter in practice. And I would argue this is broadly applicable. Here are some example applications that I haven't talked about. So PFAS monitoring is one. PFAS are long-lasting chemicals that may be bad for health. EPA happens to engage in geospatial monitoring for these to determine their concentration, but it's very expensive to measure. And it has limited resources. So the goal here is to find places to measure to maximize the number of high PFAS locations identified. That could be cast as a VAS-style problem. And we have a paper currently under review just on that alone. Epidemic control is a geospatial problem. If we model things in these visual terms, and we'd like to measure epidemic incidence in space to determine outbreak epicenters, for example, the identification of these epicenters defines now our utility, and we can apply VS-style techniques to this problem as well. And something like identifying lesions in medical images, where we're trying to identify all the locations of possible lesions in a medical image by asking medical professionals for small queries about small subregions. So all of those can be viewed as instantiations of visual active search. And we've shown on some of these already that adaptations of these techniques actually work quite well compared to state of the art. All right, well, thank you for inviting me again. I'll take any questions you have in the time I have remaining.
Any questions?
Thanks, that was really interesting. I was curious, you mentioned the distinction between active search and sort of active perception problems. I don't really work directly in either of those areas, so I think I'm just sort of missing some basic definitions there, but could you talk some more about the difference between those two?
Sure. I think it's active perception, active sensing. You can think broadly enough, if you like, to make VAS a special case of that. Because we assume certain structure on the search. We assume, right, the actions available here are geospatial actions. In active perception, nominally, you just define some arbitrary action space that allows you to perceive things in particular ways, right? There's going to be some mapping between actions and what you perceive. Typically, in the literature, what you don't get is reliable feedback about the ground truth, which is what you care about. So here, we define the ground truth in terms of, for example, whether target object is there or not, as an example. Okay, so typically in active perception and active sensing, all you get is kind of alternative sensing, and you try to kind of combine it together to optimize for prediction. Not necessarily this somewhat different notion of utility. This is just a reflection of the typical attention that the literature has paid on the problems. But I think it would be fair to also say that what we're addressing here is a special case of a very, very broad definition of active perception.
That makes sense. Thanks.
Yeah.
Okay. Let me read a question. When you use CLIP for multi-model search, active search, you are using the language as well as the images. And in the images, I saw you are using a cross view image. Is it true? We want to clarify that it's actually the cross view from the street view and do the active search for the geolocation on the bird view.
So we use I mean, that's clip-like, but we can use, I'm just saying, like, that's not much novelty. We can actually essentially use clip style techniques to just align the representation across any modality. So here we have sort of, we would call it two image modalities. I know they're not exactly different modalities because they're both images, but satellite images versus street view, we want to make sure that if it's showing the same thing, it gives you similar embedding vectors. And in turn, those two should be similar also to whatever the LLM embedding is.
Okay, a follow-up question is, when you use street to do the geolocalization and compare with somehow the same perspective, the same view, does the accuracy view be affected?
I'm sorry, I coughed and I missed a part of the question. Can you repeat it?
Okay. When you use street view for the localization, geolocalization on the bird view, and compared with using the bird view for bird view localization, do you see a difference in the geolocalization?
That's a good question. I actually don't remember these results. I believe we did these ablations, but my student would know better. Incidentally, I would just advertise the student who's actually led all this work is in India, Sarkar, who's potentially going to be on the job market next year. And he's really responsible for all the technical work that's been involved. As a matter of fact, let me put this up while I take questions. This is the collaborators that have been engaged. But yeah, I actually don't remember that particular ablation. So if you email me, I can answer more. I can look it up and answer that.
Okay, great. Any other questions from the audience? Okay, no further questions. Thank you very much. It's really great talk.
Thank you very much for inviting me.
Okay, our next speaker is already here, and Dr. Thomas. Okay, yeah. Okay, can you try to share a screen? Well, I introduce you.
Can you hear me?
I can hear you. Yeah. The screen is okay. The next, the next is Dr. Tobias Poller, and he's a professor in computer science in UCSB, University of California, Santa Barbara. He directs the Four Eyes Lab and conducting research in imaging, interaction, innovative interface, and he spans several areas in HCI, real-time computer vision, graphics, social and semantic computing, and visualization. And he has a PhD from Columbia in 2004, and he got NSF Career Award for his work anywhere augmentation. He has quite a lot of publications and almost over 300 publications already, and he has won the Best Paper Award and the Honor Mention Award at quite a lot of conferences, such as IEEE ISMAR conference, which is one of the best AR conferences, IEEE VR, ACM, VRST, ACM, UIST, ACM, MOBI, HCI, IEEE Software, as well as IEEE CompStima. And he was named ACM Distinguished Scientist in 2003, and he's a senior member of IEEE and IEEE Computer Society, and a member of IEEE VGTC, and which is, I believe, is in the graphic community and the visual augmented academy. And his talk today is on the topic of on-tracking, always on mobile augmented reality.
Thank you so much, Goryu, for inviting me. Thanks for everyone. Thanks to everyone for attending today. I'm sorry that I can't be with you in Nashville today. I'm talking to you from California, which of course is much more peaceful than sometimes portrayed in the media. So I'd like to talk today about augmented reality. This is where I come from. This is my lab, the Four Eyes Lab. The Four Eyes stand for Imaging, Interaction, and Innovative Interfaces. There are some other affiliated faculty in the area of visual computing. We are very interested in augmented and virtual reality. We do dabble in computer vision, especially real-time computer vision, and some other topics that are all concerned with the future of human-computer interaction, basically. And the 4Is obviously also stand for the glasses, the goggles that we still wear for much of our research. I want to start today by just recapping what has shifted our computational era in terms of milestones in computer technology adoption. I mean, you can agree with me or not on these. These are some very key milestones. There may have been some minor developments in between. This is something that I always do in my classes on HCI, and then since 2007, which basically is when the iPhone came out and the mobile revolution, where more devices were produced that were mobile than desktop, that happened about 2009, 2010. Nothing really happened for a long time. So the next thing that shifts our paradigm, I always thought would be reality computing through always-on mobile augmented reality. And by now, a lot of companies are actually investing in this area a lot. And during the 2010s, of course, we had a huge advancement of machine learning. And so what really happened in terms of technology adoption is that about 2022 onwards, in terms of adoption, right? We are now in the big revolution of generative and conversational AI, of course. So now then maybe the next thing will be reality computing through always-on AI-supported mobile AR, and that is still what a lot of companies believe and invest in. So I just want to use this as the backdrop and kind of go quickly over what my part in the story is. So this was my PhD work in the 1990s at Columbia University. I was fortunate enough to actually join Stephen Feiner's lab, and they had just started doing experiments with mobile AR outdoors on campus. So this was a situated documentaries application on campus where we kind of said what was on those grounds before Columbia moved up there. And ironically enough, it was the Bloomingdale Asylum for the Insane, which prompted many people to say that nothing really changes ever over time. So, but in order to do this, right, we looked like this. And so this guy looks weirded out by just looking at my colleague Elias Gagas here. And some people call Ghostbusters after us because really that's a movie that's also filmed on Columbia's campus. So since then, fast forward to 2020, about then, this has shrunk into a headset, right? And so this is the HoloLens 2. One of the headsets, HoloLens 1, came out 2016 or thereabouts. And now we can just walk around on UCSB's campus with just that headset as the computer that drives everything and do a virtual treasure hunt. So this is my student, Eugene Kim, who ran this study. He's now an assistant professor at Texas A&M. So how did we get there, right? So it's this miniaturization of technology, obviously lots of impressive engineering, device integration. And to the topic of our workshop, with some economies of scale, especially on CPU and GPU performance, and recent improvements in display technology, lot of developments and new benefits in real-time computer vision, visual odometry, and SLAM. And just to show that my lab over the years actually did some work in this area, dabbled in it. This was 2008, where we used an outstretched hand that we kind of recognized as an AI toolkit marker to initialize a SLAM system. And I have to admit, I mean, our SLAM system could not compete with PTAM, which came out around the same time. So that is what everyone in the AR kind of discipline based their work on, and that's kind of what influenced industry. But we had some interesting HCI like possibilities here. By using your outstretched hand, you could populate and interact. So this was before you could do full posture hand tracking. So with just real-time computer vision, like certain poses can already do a lot of interesting things. So it's 2008, which was really like there was no hand tracking out of the box at that point. So, and with this ingredient, right, real-time computer vision, which in fact, I think from my lab, we put a lot of focus on and was a big component on my NSF career agenda on anywhere augmentation. This fed and this is how we see the world and operate HCI research. So what can we do with this future system, right? And as I pointed out, I mean, we don't even right now have like widespread adoption of it yet, but we're getting a lot closer. So in order to figure out what future systems could actually afford, right? Whenever we wanted to assess the limits, limitations, opportunities of these new technologies informing the future, we resort to simulation. So here's an example. This is taking place in like a 3-story high visualization chamber, the allosphere that we have at UCSB. So you're basically on a bridge like in Cerebro from X-Men, and you're surrounded by a completely spherical display. And now here we simulate whatever is shown as this display as your real-world backdrop to be also streamed to a handheld display. And here we can simulate tracking artifacts, annotations, and anything, because this is going on in simulation. And so we can have any arbitrary computer-generated or 3D captured panoramic content. So this one is computer-generated as well. So we like act as if we're using the camera of this handheld display, but instead it's just graphics streamed to it. And then that can actually expand to doing simulation of like more difficult, like larger environments, because really, while you're standing on the bridge and there's limited mobility in this instrument, you can simulate interesting phenomena like visibility constraints with smoke from wildfire or anything like that. So, and there's another experiment here where we like basically we're interested in the question of what field of view and what tracking artifacts like you could live with in augmented reality tasks. So the backdrop here, you can't really see that because we chose a monoscopic like example for filming this video is actually stereo. You're standing in a stereo 3D reincarnation of the Luxor Temple in Egypt. And overlaid on top of that via simulated AR, which, as you can see, we simulated a little bit of latency as well, because you wouldn't have to in this instrument, right? It could be rock solid. Would affect how you can actually find information about physical statues in this temple region if you have this kind of interface in AR, right? And so we ran some user studies and also looked at exactly the combination of, so this is from the first person perspective, what field of view and what tracking artifacts actually have an impact on task performance. And so this is a simulation of head-worn optical see-through displays, right? We can also simulate video pass-through or video feed-through or video see-through VST displays, which are now much more common with the Meta Quest devices or the Apple Vision Pro. So we did this work in 2016. There weren't really any like commercial options, cheap options around, or even like widespread public adoption in this space. But you could work with like $30,000 like headsets at that time, or you could simulate. In an instrument that obviously is even more expensive than that. So again, we're tracking, we're simulating tracking artifacts. In case of video see-through, it affects the entire visual portion of the view and not the augmentations. And so you can this is the field of view, and you can draw conclusions from that. All right, so back to today. So this is from 2 years ago. I showed you we're walking around our campus in 2020 during the pandemic. It was very nice and empty, so we could do outdoor experiment here where it never rains, right? Without being disturbed by passers. And so we did a sequence of studies of wide area mobile augmented reality. So this particular study by my student Radha Kumaran, who just graduated, congratulations Radha, 2 days ago, defended her thesis on navigational aids in an outdoor environment. And so here's some footage from that. The tracking and is a little bit better than you see it here, because here it's mixed reality capture, and so that is additional load on top of the HoloLens 2, which was already taxed by all our graphics. So and then we have 3 navigational aids. Bottom right, you see the in-world arrows. The top, you see a radar, and on the bottom left, you see basically an indicator that shows on a timeline what's around you and the distance to the nearest object right in the center, right? So of these 3 things, the compass, the radar, and the arrows, I show you some results here. All navigation aids actually reduced search time. We had 24 of these visual gems, all virtual, that people had to collect. And the real differences come when you have found nearly all of them, right? So the last 6 of them, we had 4 bins of 6. And obviously they were in different order for different participants. Everything in the navigational aids was also controlled and permuted with Latin square. But you see that like no aid always took longest overall, and especially the last few. But then even the world stabilized arrows, right, that are really good in the beginning, because you just see them coming down from the sky and you just have to walk up to them. For the last few, you still have to look around and see where the last few remaining ones are. And the screen stabilized gadgets like the radar and the compass actually listed the last 2 remaining ones, and you could find them a little bit more quickly. So that's interesting. So different aids are useful at different stages of the task. And there was an overall strong user preference, which is always important in HCI research, for the world stabilized arrows, right? It's easier. It's not indirect. It's right in your field of vision. So in a follow-up study, we wanted to give users the ability to customize their use of these navigation aids. We actually just took the radar and the in-world arrows for this. And I will talk about that in a little bit. So the first question is, right, with this work, we can do these types of experiments now, right? So does that mean tracking is solved? So if I ask a question like that, the answer is no, right? But we do have these devices, HoloLens 2, Magic Leap 2, MetaQuest series. Just yesterday at AWE, I saw the latest incarnation of the Snap Spectacles. We have the Apple Vision Pro as video see-through device. And then we have what is depicted here on the right, not as a product, but as a research prototype, probably one of the currently most sophisticated small wearable AR devices, and that's Meta Orion. But with any of these, all of these, tracking is not solved yet, right? And so if you're working in visual odometry on tracking, on anything computer vision related in this area, I can assure you there's still a lot of work to do. This is actually interesting because let me go back. I attended a keynote talk about Orion at ISMAR, which is the Mixed and Augmented Reality Conference, IEEE flagship conference last year. And my friend and colleague Benko stated in that talk that tracking is comparatively to other topics solved today. And I took issue with that. I think it is not solved at all. So lots of challenges remain. I mean, not that my lab actually is doing a lot of tracking work. We're just using it, and from its use, we noticed that in no currently available platform, and even in the most sophisticated research platforms that I know, there is still lots of problems. I'm listing a few of them here. So we heard already in some talks today, lighting situations, scene situations are definitely a problem. Weather, direct glare, and this is true for autonomous driving systems. High dynamic range transitions when you walk with AR, right, and go from outdoors to indoors, bright sunlight to like a church environment, let's say, you would have tons of immediate problems. So highly dynamic environments, big problem, right? Because it's hard for computer vision, as you all know, to delineate what is like camera motion, what is motion in the scene. Low texture and repetitive environments still cause us a lot of problems. There, we had a little bit more advancement. Sensor fusion complexity, like all these devices that you can buy right now in AR, right? They have highly sophisticated integration of different sensors, inertial sensors with the computer vision, with LiDAR maybe. So lots accelerometers. So lots of different things, and if you want to add like something from your own arsenal, that's actually really hard because this happens all in firmware, all in hardware accelerated direct communications. So still a lot of complexity there, where we could actually like make stuff much more accessible to everyone if we solve some of these problems. Multi-user, multi-session, right? So you need to synchronize a lot of stuff, and there's problems both on the computer vision side, on the timing side, as well as the HCI side. And then when you want to scale this up to a global, worldwide AR cloud, you actually find a lot more problems. So on scalability, actually, I have a little plug here. So my student Noah Stier also just graduated, or graduated half a year ago, now at Tesla doing research there. I encourage you to talk to him. So this poster is at CVPR on Sunday. And in this work, we have for 3D reconstruction from posed views that could come from augmented reality observations. like figure out like, hey, how can we work with adaptive sampling so we don't have to have the same resolution everywhere, and that actually buys us a little bit more scalability. So that was just a plug on that front, scalability. And semantic understanding, right, is something that several speakers today in this workshop already alluded to. It's really a big boon for AR and for computer vision. And there's a lot to be done there.
Leaps in neural vision language understanding
I
to
don't know.
enhance environment
Maybe since there
perception
is
for
audio here,
autonomous
maybe I
tasks.
be quiet for a little
In
bit.
this work, we present a fast multimodal 3D reconstruction pipeline
This
to
was
unify the
more 2
geometric,
years ago.
semantic, and linguistic
Well,
3D
last year.
understandings for context-aware AR. We also propose in situ learning to allow users to interact with physical objects in a spatially and linguistically meaningful manner. This video demonstrates the usefulness of the proposed system through 2 real-world AR applications on Magic Leap 2, spatial search with natural language, and intelligent object inventory. The multimodal 3D fusion starts with scanning a physical space with an AR headset or smartphone to capture registered RGB images and depth maps. The proposed pipeline
Well, this we wanna
reconstructs
have
the 3D
real-time,
environment
obviously,
model and fuses
eventually.
clip vision language features into the segmented individual object models.
In
After just
research,
2
it can
minutes
be
of
done real
processing,
time, right?
users
Just
can review the
not at the same
reconstruction in
time as
various ways.
working on the
A
other
volume
stuff.
grid, a mesh model, 3D segmentation, and our favorite form of interaction, directly highlighting and selecting physical objects like magic. Spatial
Because they were
search with
automatically
natural language.
segmented.
Have you ever imagined being able to search a physical space as easily as using the Control F on your computer? With 3D Vision Language Fusion, you can perform a spatial search describing the object or even use abstract natural language queries. For example, show me things that might be dangerous to babies. The AR application will display a 3D heat map that highlights potential hazards, such as the skateboard, the basketball, and the rolling chair that could trip the baby or objects on the shelf that might fall.
All right, so I'm going to stop that here. So I think this is really interesting, an interesting application, right? And so if we buy into the notion that we might have always on glasses, then things like that could be really, really useful. It would automatically recognize and model an environment that you're in. Of course, that's also scary, right, from privacy perspective and from computational load perspective, but maybe on demand. And then you could query this environment for like any advice that you want. What is dangerous for babies? Where in my backyard could I best hang a hammock? Stuff like that, right? And so all of these things that make this possible, the real-time detection, semantic indexing, and then AR representation are things of interest to us. So all of these, the challenges that I listed, like obviously have to happen with real-time performance if you buy into, again, this notion of always on augmented reality. And there is a big question if we will ever convince a large swath of people to wear glasses that might be more clunky than normal vision correction eyewear. But they may not have to be more clunky, right? So extrapolating from developments that we already have seen. So we have now glasses with Meta Orion that look bulky, but are maybe socially acceptable. I'm not quite sure yet. But I'm a skeptic as well as a technology optimist. So, all right. So tracking solved. So answer, I would say, is clearly no, right? So the next question then is, to what extent does that matter to users of extended reality? So here's an example of recent work that we did, that gets to that question. So if we walk around here on another one of our treasure hunts, this one indoors, so lots of augmentations around, and now notice I call this milestone stability, and I will tell you why. So it was much, much milder before, but we wanted to test with users at what point they actually don't use the arrows anymore and switch over to something like the radar that you saw before. And at least for this artificial environment where a task is short and they're not wearing it all the time, users put up with a lot of tracking error. So you can see that, I mean, this is like what would happen in the worst case if you are maybe in an environment like this, where AR might be like really important, and you don't have any models to track against because you're just in a natural disaster. And that is actually one driving question of this, right? So back to our example, users did see the value of the radar, like having an overview of where all the search targets were in the environment. But they still, even though they had complete control over what they would turn off and on, they would still leave these in-world arrows on, even if they are like wildly unstable. And so that's interesting, right? Now, would that still be true if you really wear your glasses and actually like are not that reliant on this information for your task at hand? Probably not, definitely not, right? I mean, who wants to have like nausea-inducing movement in their periphery or in front of them all the time? So I would say, to what extent does it matter to XR users? Well, so the answer to that is probably likely highly application dependent, right? In specialized use cases, you can get benefit from AR overlays, even if there are large instabilities, as shown by the example that I just gave you. But for always on use, you likely want to be as perfect as possible. And that makes your task working on visual odometry and tracking and registration, like obviously more and more important, and the performance requirements more stringent. Okay. So with that, the conclusions from what I've talked about today. From an augmented reality application perspective, which is what I gave you today, this is not the only thing that my lab is interested in, but that was the hook for today. Tracking, visual odometry, and scene reconstruction are far from solved. Even though there is great advancements in that field, in all those fields, we have need for much higher accuracy and for like really fast algorithms on all that. My second takeaway point is that augmented reality actually plays really well with other HCI technologies, especially AI. And I still think, even though like as I told you, I used this slide of paradigms in computer adoption in my HCI class, I think since 2002, and have since then predicted at some point we will get to like personalized mobile augmented reality. It currently still has lots of problems, right? And it is not clear that this will happen in the next 2 years, 5 years even. But with the investment that is going on right now in the field, I still keep it on the top of my list, because what else is there? I mean, what will make you like give up on your smartphone, or even maybe complement your smartphone even, right? For something to be a replacement for your smartphone. It has to be an order of magnitude better in some human-computer interaction dimension. And you can't do that without another widening display of some kind. And AR, which lives in the visual space in front of you, into 3D space, is obviously very well suited for that. All right, and then the last point, AI, which we are currently in the paradigm shift of, is being deployed all around us. Yeah, we better take charge of the AI and don't get ruled by the AI. And in order to keep it under human control, we need a constant interface with it and to it as well. And also for that, I think AR is really well suited. AI can definitely itself help in even like bringing about this this paradigm shift, but only if the human component isn't lost. Okay, so I think that's all I have, and these are the funding agencies that supported our work. The members and collaborators of the 4S laboratory over the years did all this work. And with that, I have a few minutes for questions.
Any questions? Yes, please.
Hello. I was hoping talking to you here in person. So I'm Frederick from Graz in Austria. You work with Dieter Schmalzstieg.
Absolutely.
Okay, so I have a question. So you mentioned all these programs for tracking, and my question would be: do you think that event cameras will play a role in advancing tracking? You know, these neuromorphic event cameras to detect changes.
Right.
Would it be for headsets or something like this? Is there talk about this?
Well, I don't think it's on the very near horizon, right? I think it's a research topic. I think it's very interesting for that. Let me first also say that I would have loved to be at CVPR this year. Your opportunity is to catch my student Noah Steer, who will be presenting this Sunday. So talk to him. So he has more central computer vision like focus and not the applied AR focus as much, because our lab is broadly interested. Back to the event cameras, I think it's really interesting technology. It's not currently, apart from like some research projects that are now being actually used even in ISMA-like research. So I think if you're working with it, that's a great opportunity.
Okay, wonderful. Thank you. I will check out the post also.
Okay.
Perfect.
I want to read another question. And for indoor and outdoor augmented reality, and do you see a big differences right now in your research?
Well, I see a big research challenge in bridging the two. If you want to do always on AR, it needs to actually work in either place and then in transition. And I think there is no two fields at the moment right now, right? There's a field of mobile augmented reality, and I think the challenges there live in both indoor and outdoor environments. But yeah, so I think we need to bridge them.
Okay, and another question is, currently there are quite a lot using large language models, and we can see you are also using the language as well. And have you explicitly used the large language model in your research to navigate the AR augmented reality applications in navigation?
So for navigation, we haven't used it yet. No. So I think that would be interesting too. And in fact, I mean, you can then do navigation even without visual overlays, right? And so it's a great additional modality to compare against. I mean, with something like the Ray-Ban Meta glasses, you could do this really well in a deployed application right now.
Okay. Any other questions from the audience? Okay. If no further questions, thank you very much, Dr. Tobias.
Thank you.
Yeah.
Thank you so much. It's great to see Ming there on the podium. Hi, Ming. Great to see you. I wish I could be there as well. Yeah, I look forward to your talk.
Thank you. I'm trying to find the
USB.
Yeah, I'm not finding it.
If that doesn't look, we can try that one. Let's just see.
I don't see it.
C drive. Is it the one? This one? USB. There is a USB drive recognized.
Oh, right there. Yes, that's it. Okay, that's it. Should have downloaded to local. It's taking forever to open it.
This one is slower than this one. And if that is too slow, we can switch to this one.
Okay. It's taking forever.
Then we can just try the same thing. Both are mounting.
All right, there we go.
Sorry, let me share screen already. Let's say screen is shared. Let's see. Sure. Let me introduce Dr. Ming Lin. Dr. Ming Lin is currently a professor at University of Maryland, and she is very well known in her research in robotics and computer vision. And actually, she's also an Amazon Scholar at the moment, I believe so, right? You are also Amazon Scholar, okay? She has been distinguished professor in University of North Carolina, Chapel Hill, and she obtained degrees and from bachelor, master, PhD from University of California, Berkeley, and she received quite a lot of awards, including NSF Career Award, the UNC Title Award for Scholarly Achievement, and the IEEE GTC Virtual Reality Technical Achievement, and yeah, quite a lot. And she is currently a fellow from of National Academy of Inventors, fellow of ACM, fellow of IEEE, and Eurographics, and ACM CGraph Academy, and IEEE VR Academy. She has already won quite a lot of awards, and she has been serving in the community, in CGraph community, as well as in the robotics community, in quite a lot of different venues. And she was editor-in-chief of IEEE Transitions on visualization and computer graphics, and the former chair of IEEE CS Transition Operation Committee, and a member of quite a lot of editorial boards. And let's welcome Dr. Ming for her research talk.
Thank you for the introduction. Okay, so it's a pleasure for me to be here and to kind of share with you some of the work that we have done, which really kind of bridging the gap between VR and physics-based simulations and robotics. And I hope it will become very clear as I kind of walk you through some of the work that we do. And obviously, as we threaded through all this, vision is part of, integral part of all these work. Okay, so the application domain that I'm going to focus on is not what I do at Amazon. I was actually at Amazon Retail, the fashion. We launched its first 3D virtual try-on application. And most recently, I have moved to Amazon Robotics. And we are actually trying to support all kinds of operations, including learning for generalist robots at Amazon. And just my few months at Amazon Robotics, I would say, for those of you who are working in vision and robotics, Amazon arguably might just be the largest robotics researcher employer in the US can come in across the world, but there's so much going on and there's a lot of excitement there. But to kind of kick off the work of the talk, I do want to kind of share with some really interesting statistic, which I came through. This was the top 10 US industry by revenue in 2024. And right there on the very first one, it's banking. Hopefully that should be no surprise. And then a whole bunch underneath of that is like hospital, healthcare, basically, goods for keeping you healthy and looking great. And then somewhere in there is public school. For those of us who are in education, we are number 8. That's not even including the private universities. But what was really interesting was the new car dealer, the sales was number 5. It means transportation is critical. And why? Because everything we produce need to go from point A to point B. It needs to be transported. People don't think about it. That is how critical it is. And number 10 is petroleum. That is energy and gas, fuel, the transportation, and everything else. Okay, so that kind of, put a real numbers on why I'm excited about doing what I'm doing as a robotics researcher. I also believe autonomous driving is a lot closer than anything else in robotics. In terms of sort of this grand vision of generalist robotics, because the price tag is going to be affordable and is already affordable. And that's what you pay, very close to what you pay for a car. But also there is an increasing trend of growth in mobility. And this is the cost of mobility. It kind of flattened a little bit in 2016, but it is still growing, continuing to grow. Okay. So I'm going to chat just about a few projects that we do. I won't go into all the detail, but hopefully it will give you some idea where visual informations are critical. So the first one is about city scale traffic animation and reconstruction using statistical learning and meta-based optimization. And so the key idea here was the very fact that we recognize the importance of urbanizations. The world population is already over 8 billion, and overwhelming majority of them live in the city. And there's another interesting statistic: 2.5 billion of the 8 billion lives in Asia. And so share rides, no matter where you are, no matter what continent you are, is increasingly popular everywhere. But we think share ride is going to reduce the traffic. No, it doesn't. And in fact, that it increase, there are more cars on the road because all these share rides. So traffic is a major issue. It has always been a major issue and continue to be a major issue. So what we're interested in doing is to reconstruct city scale traffic. And the reason is multiple fold. We can build a virtual vehicle simulator. We can use the traffic information that we reconstructed from real world data to interface it with autonomous vehicle simulations and for designs and how to cope with various traffic jams. So traffic simulation has been around for decades, and traffic animation has also been, pretty popular across different domains, even including animations and cartoons and VR, and also the related work will be on reconstructions. Given the traffic data, can we reconstruct what's going on and why? Well, the part of the reason is we have tons of traffic data. They are everywhere. They are in road. It's sensing how fast you're driving, and they are on the overhead. For example, the camera. I have gotten ticket for just driving a little bit over 25 miles. The camera is everywhere. In the city, it doesn't take that much. Even if you just want to pass the driver, you can't see 25 miles in the city. So those are real cameras are everywhere, right? So we got tons of traffic data. And they are everywhere. This is a city scale in San Francisco. You can see where they are all different kind of sensors. And we have been looking at how can we use these sensor information. They are not always camera data. They could be just a car passing by, and they're different kind of data. But what was really interesting was the very fact, one of the most popular coverage of data that we can get is actually GPS data. Because wherever we are, all of us have a cell phone. I'm not sure who goes around today don't have a cell phone. If you're driving, you have a cell phone. And if you have an autonomous vehicle, there is some sort of Wi-Fi coverage as well. So GPS coverage is becoming very, very general and very broad. And on top of that, all these autonomous vehicle and all the car have some sort of mobility information that is being transmitted and being tracked. All these data are rich information. A lot of it is actually privacy protected. It just simply indicate what car is where, not necessarily the driver's information. Particularly for GPS data, mostly you don't have an identifier. But I'm not arguing privacy and security information should not be a concern. It should be. We should continue to protect our privacy, even when these data is being collected. However, there are some issues, and one of them is the low sampling of GPS data. They are not transmitted every second, like the in-road sensor data. It just, whenever there's a car passing by, there are data being captured. And then there, not to mention they have different modality. GPS data are different in camera data. This is important. I'm gonna, toward the end, I'm gonna say a few words about collaborative perception and multimodality sensing. So the solution that has been looked at is, given all these data, we need some sort of map matching. What does that mean? And travel time estimation. And this is important for reconstructing traffic. So what's map matching? Well, you have the street. So you have the GIS data, you have the road network, and the GPS will give you the information regarding when the car passed by a certain location. But you don't know where the car actually drive in between. So you need to reconstruct that information. This very simple example, 2 different GPS location and points, you can actually get 2 different paths. And I would argue much more if you are in a connected city road. And so which path? That can actually alter a lot of decision you make. And generally speaking, the current map matching algorithm is trying to map the correct information that you get from the GPS to the correct path. And a lot of time by default, people use shortest distance. And what we did is we did some minor difference. We're saying, no, it's not true that you should always use the shortest distance. You should look at what's the time estimation. And so we've been also looking at using the time as a constraint to actually help better select. So we now do also estimate travel time to incorporate that information to figure out how the driver actually drive. It turned out it's a far better estimation. And the other issue is that traffic is dynamic, it's not static. There may be a traffic jam right now, but by the time you get there, they may not be. Or the road is clear, but by the time you get there, there may be a traffic jam. And so the sparsity of the information means that it leaves gap in terms of how you can actually interpolate and reconstruct traffic flow. And that is a dynamically evolving phenomenon over time. And so what we did here is we actually incorporate all these information, whether it's GPS tracer, whether it's in-road sensors, or some sort of trip informations. We use that to do this initial traffic reconstruction. And so zooming is that we have these sample data, and we come up with some sort of meta model to fit those sample data to figure out what that might be. And that it would include things like map matching, including travel time estimation. But we also have a traffic flow simulation model that we use So basically what we did is we have combined all these information. It's not just statistical fitting. It's actually a very intelligent statistical fitting, taking into account of travel information, and the traffic flow model, and then make a decision. Also, you have a lot of junction and different road network may have different kind of intersection. So you need to take all that into account to reconstruct this whole entire pipeline. So the idea here is you need to do more than just regression or a prediction, a simple statistical prediction. Now, by taking this kind of approach, that is taking the actual physical phenomenon of the traffic flow into account, we found out that we can reduce the relative errors in terms of accuracy by 97%. But in addition to that, we also found out that by using this dynamic data completion, what I mean by dynamic data completion is incorporating the traffic model into statistical learning. We found we can get 35 about 35 times faster, and the biggest speed up we have seen was 90%. Now, I want to mention, as somebody who does a lot of physics simulation, and one other paradigm which I've been trying to push is, I know GPU is lovely and it's really, really fast, but there's no reason why we need to learn everything from scratch, and there are a lot of information. So the dynamic data completion is a perfect example where when we incorporate the basic law of traffic flow, the physical law of the traffic flow, we can easily get speed up to 100 times. And we have seen the same kind of approach in using differentiable physics incorporated with learning. It can speed up as much as 1,000 times. And what it says is basically, don't throw away everything we already know. If you have a model, it doesn't matter if it's physics, doesn't matter if it's traffic, it doesn't matter if it's geometry, use it to help you do the learning faster. And these are sort of different plots that we have to show the analysis that we have done. And we have also used it to visualize the traffic flow at different time throughout the day in San Francisco. And this is a very large scale, city scale traffic flow visualization. Now, what was really interesting was being able to reconstruct the traffic also allow us to take a look at how can we even improve the traffic simulation model. So all the numbers and all the data that we have, we can in fact incorporate it with machine learning technology to also build better traffic simulation model. One of the things that it does help us is to determine what are the parameters in your traffic equations. So I'll go through all the details. I just want to show you the simulation. All right, so that traffic simulator was important as we move forward toward building better and safer autonomous vehicles. Because if we are going to deploy large number of autonomous vehicle out there, some of these traffic information can help inform the vehicle how to drive more efficiently, how to get there safer, and also save more energies in terms of reducing the gas consumption. So one of the things that we have been looking at, the basic motivation, is that most of the data that are collected by the human drivers are safe data, meaning just normal driving. And those are not the cases that we need gazillions of data on. And we can spend lots of time training and processing those data. It does not improve autonomous driving. Autonomous driving need to know how to handle accident-prone scenarios, and those are rare for a reason. That's why they are called rare events. And human is almost guaranteed to be an integral part of these rare events. And if you expect a human to help you label the data, that's pretty difficult and very time consuming, not to mention collection is difficult and challenging. So this is one of the places where we actually develop our simulator, trying to incorporate the traffic simulation and vehicle simulation and put real human drivers in there. And you wonder, how is that possible? It's called virtual reality. So we actually create scenarios of such a simulator embedded in a traffic simulation. We create these scenarios. So we literally script these accident prompt scenarios based on whatever that has been studied in traffic engineering. And we basically are doing is creating a multi-agent systems. The benefit of such is not just creating a simulation with cars, but you can also create a simulation with pedestrians and crowds. And I know earlier there was a talk by another speaker, Paul Torrance, who talked a bit about the crowd simulation. So all these are important, but increasingly, my group is actually looking at another thing which has been largely ignored, but it's becoming a real problem. At least if you are in a city with a university, and that's called the micromobility system. The scooters, the one wheel, the two wheel, the four wheel, the three wheel, they are everywhere. And they actually are posing as one of the biggest safety threat for not just autonomous vehicle, but also vehicle driven by normal human drivers, but not to mention the pedestrian who's walking on the sidewalk. And so how can we model and capture those? And this is where, I think vision can help, but we are also trying to figure out a simulation model to capture some of the dynamics of these micromobility systems. Now, if we simulate an accident in a VR environment, we can put driver of all different type in a VR environment and then trying to capture those data. And once we have those accident data, you can in fact use it to analyze what is going on automatically because it's all done in a simulator, it's captured in a simulated environment. But the person who's driving the car is a real human driver. And my argument is autonomous vehicles know how to drive. It's the human drivers who make errors. And how to anticipate and how to drive side by side with real human drivers is critical. And that's where we're trying to capture the data, is trying to capture these data taken from the real human driver when they have to deal with unexpected scenarios. It's not necessarily an autonomous car. It's the human driver who did not expect unexpected rare events. And that human driver can affect the safety of the autonomous vehicle and all the car nearby. And that is one of the reasons that we are focusing on the interaction between these autonomous vehicle and also human driver. And we are trying to capture these accident scenario, accident prone scenario, or rare events systematically and capturing them in the VR environment. And the hope there is with these data, we can improve transfer learning. And in fact, that we did some study. Again, these scenarios, the pre-crash scenarios that we try to model and simulate, they were predefined by the National Highway Transportation Systems safety agencies in the US. And I'm sure a similar kind of agency exists around the world. So there's actually a catalog of scenario. We did not create them. Okay, so here are just a few cases. You can take a look. Running a red light, running a stop light or stop sign, turning and driving the same directions, and changing lane in the same direction, and so on. And my joke is, the deers, the squirrels, all those unexpected, or the pedestrians, and throw it onto that list, the scooters that you did not expect that was driving from the sidewalk onto the highway, or the roads. And so all these scenarios that you just saw, we try to model them and create them in the VR environment. And so we can simulate them. And here, just sort of one of them. It goes on. I won't go into all the detail, but I just want to say that we have found in our study, we have actually 3 different models. One of them is we just train a learning-based model with a simulation. One of them we trained it with only real-world data, and one of them we trained with both the real-world data and the simulated accidents. Number 3 did the best across all of them, and we also compare against the baseline in terms of convergence, and ours certainly do a lot better than the existing simulation. I don't think I have time to show you another video. I'm gonna just skip that and just simply say that by simulating these accidental scenario and collect real human data how they drive, and use that information to train the autonomous vehicle turn out to be a really huge bonuses and a plus to make driving safer. We are still trying to also incorporate other things like formal methods to assure safety guarantee. Personally, I believed I am not going to go into that autonomous vehicle unless I can feel safe. And I think safety is going to be a real issue. If it's not a real issue to the rider and the human drivers, other human drivers, it will become a legal issue. So it will become a real issue. Now, there are other issues that it can impact safety, and that is robustness in autonomous system in general. And that's another area where we have been looking at using adversarial training. And so we have developed an adversarial differentiable data augmentation for autonomous systems. Now, all the existing autonomous driving systems are vision-based. I don't know anyone that's not vision-based. And so as you know, and most of them have an RGB camera. These images, they can get corrupted. They are not perfect. They could be sensor errors. And these are standard, neural network performance on just sort of typical vision recognition tasks. And you can see just simple corruption of images can lead to all kind of errors. So this is not anything new. And you can see 5 different cases, 3 of them did just fine, 2 of them fail miserably. Now, that is image corruption is not only one. The other one, and I know a lot of people who was working autonomous driving industry, and including some of my former students, many of my former students. One of the issues they are still struggling with is with weather. Snow, frost, fog, lens distortion, all kind of blurring. All these are just perfect examples. Same view, how they actually getting corrupted due to weather or sensor errors. And so how do you deal with it? What we have proposed is an adversarial training approach where we actually take whatever clean images you have, we corrupt them on purpose. And we corrupt those images by altering all different image attribute channels from color to intensity value to hues and noises and so on. And then we train them. And what was really interesting is that the train systems was able to handle this amazingly well, even including weather, which we did not expect. So even simulated scenarios, and we believe is because some of these weather effects can be a linear combination of degradation in different color channels and brightness and hues. So, and again, these are data. I encourage you to check it out. We actually have different approach, both gradient based as well as gradient free. The result I was showing earlier was gradient based. We also have done this for gradient free approach that you actually don't have to compute gradients. And very small amount. I don't think I have time. Let's skip this. And I encourage you to check out our papers that was published in Europe a couple of years ago. We also have another one that's coming out of ICML, where we actually did look at how can you actually compute these augmentation much more efficiently. And the way that we did it is based on sensitivity analysis. And sensitivity analysis can be very expensive. So we now propose a new methods which can adaptively compute sensitivity for any input-output systems. This means any black box, any neural network. We show it on segmentation, but it can be generalized to control and other vision systems. And I want to say that the future that we're going to be going toward is that as we increasingly have more and more autonomous vehicle on the road, we might want to also start thinking about collaborative perceptions and cross-view and cross-modality perceptions. And these are important because as, once we have more car, why don't we leverage some of those information? So one of the things that we've been looking at is, can we actually use cross-modality and also cross-view perception to actually help improving the safety? So one of the really good example is when you're driving on the road, you have a really big truck in front of you. And then you are at the red line. And suddenly the light got changed. And the car in front of you moved, but you were right behind. But there was a traffic jam. And so you don't get to see everything. If you have cross view and you have other information regarding other incoming car, say a drunken driver, that will save life. So having that kind of cross view scenario to warn you and to help and assist autonomous systems to warn the driver of a potential incoming dangers will be something you kind of consider. What we did is we actually propose a new novel representation that will consistently represent an observation as a semantic graph. So it doesn't matter which view you have, there's a correlation between different view and based on distance field information. And this can be really useful for collaborative perception, but also multi-agent, multi-robot team perception. So I just want to kind of introduce the idea. We have applied this to place recognition, and it turned out to be a huge helpful. So even if you don't have all the perfect perception, you just have a couple view. With this approach, you could actually do the place recognition very efficiently. And this was actually presented at IRAS 2023, and it won one of the best paper awards. And we have extended this to also perform collaborative decision making using this idea of spatial temporal graph. So it's beyond what I just mentioned. It also taking into account of time in connected autonomy. So as we move forward to the future, when we will have more and more autonomous vehicle, we also can leverage that collaborative informations across the systems. Okay, and I won't, like I say, I won't have time to talk about this, but this was in ICRA just this past years, for those of you who are interested, and check it out. And so I just want to say that, with a right representation, so it's not just the right approach, like I mentioned, incorporation of model with learning, but also use and develop the right representation and data structure. We found that we can reduce in terms of the data size by 100 times. So by developing the right data structure, you can also reduce the amount of data that you need to store and that you need to share across the bandwidth. And that matters when you are right here in a convention center and you complain, why is the Wi-Fi so slow? That was one of the contributors. All right. And I just want to say that by using the same kind of idea, you can also use different modality. You can use it during training, but during influence, you only use one. So we have proposed this idea, and in fact, some of these concepts are not new, but we have formalized it. And we call it auxiliary modality learning, AML. This paper was presented at ICML last year, and I encourage you to check it out because we literally guarantee you will do better if you use this kind of approach. And we have also analyzed why it actually works from a data perspective, from the optimization perspective, from the policy perspective. I won't go into all the detail, because the goal here is to encourage all of us who are here in a computer vision conference to think about how can we think about cross modality, even different visual modality, and use that to create safer AI and autonomous systems. And so that is sort of my personal, advocacy right now, is as we move to a more autonomous system, as we design more and more efficient and optimized and effective AI system, safety has to be considered. And I hope we will all work toward that direction. Okay. All right. I'm going to just end right here. I think I'm at my 30%. And of course, I have to thank all the sponsors who supported the work.
Any questions? Questions from the audience?
Okay.
Actually, I do have a question. So you mentioned about the speed up can be something like 35 times, even 90 times, and somehow I always feel there is no free lunch, and once you accelerate something, you lose something.
It's actually not true. Okay. And the reason is that, generally speaking, yes, there is no free lunch. And in the case of learning, I would just simply say that the reason that we are able to accelerate is same thing, the principle based on what everybody already know in optimization. If you're doing optimization and you sample every single data and trying to optimize and pick the maximum and the most optimal solution, it's going to cost you. It's brute force. And that's what we do in learning right now. If you don't take into account of all these other information, like better data structure, cross correlations of data. And that's basically what we do, is we are taking the existing model as approximation, just like gradients. Which one of us would do optimization without some sort of gradient descent or leverage the gradient today? Most of us do, right? So what would you do that with learning? So model, in a way, is approximate solution. It's like a gradient. So we are actually not losing anything. We're just going from a brute force way to what we already know how to do. We just did not know better when we got into learning and not realize there is the counterpart of what we already know how to do. Learning is about reconstruction. It's about optimization. It's about prediction. Do we already know, which is what we do in optimization? Take advantage of the information and gradients and proximity informations, and it's clustering, so you don't actually lose anything. The only pitfall is if you do that, you need to be careful of not getting yourself trapped in a local minima. And all the things that we already know in optimizations will also apply there. How to address, how do you ensure you don't have a local minima, and you take into account uncertainties. And so those kind of approach will also work there. Okay. All right. Thanks.
Well, maybe another question. So you mentioned about collaborative sensing, and in another concept, in verticals, and are somehow also connecting different robots to make a decision. Do you see? Can you explain what is the difference between connected wearables concept together with the collaborative sensing?
So they actually are very similar in concept because, as I already mentioned, that autonomous vehicles are just robots. They are, and I am very optimistic about robotics being pervasive. We're going to see them on the road because they cost the same as the car you pay, almost the same, just a little bit more, and for that reason, when the price is right, people will pay for them. Then you will get an autonomous vehicle because you can drive safer and you don't have to put as much energy. And even if the night before you didn't sleep or you had too much to drink, too much to party, the car is going to help you, right? So though I do believe autonomous vehicle will become one of the most popular robots out there. And so the collaborative sensing for multi-agent system, multi-robot system, it's very similar to connected autonomous vehicle because you're basically sharing the information. So there's a lot of very similar paradigm.
Okay, thank you very much.
Thank you.
Okay, that goes to the last talk for today, and the speakers meeting is a joint talk given by who is the first? Samuel, you are the first. Okay, given by Samuel Wong and Xipeng Wang, both Wang. Okay, Wang. Okay, let me introduce the first. Samuel Wang is a senior autonomy engineering at Schedule, and where he leads the branch of night sensing system and enabling
Okay, I'm unmuted now. Cool. About Skydio. So we were founded in 2014. We're the leading US drone maker, specializing in autonomous flight. We are headquartered in San Mateo, California. We have around like 700 employees across the globe, 3,000 customers, and we have shipped 50,000, more than 55,000 drones. As of today, we have 2.3 million customer flight flown. Okay. And we developed both our hardware and software in-house for full stack control. And we believe that drones with camera and sensors can really enable safer, faster, and more productive operations. So here are some examples, that these are the industry that they can use drones to, as a tool for their day-to-day activities and to help them collect data and then make useful decisions on that. And here are our product offerings from the past that, we've launched our first product in R1 back in 2018, and the S2, which as far as we know is the first deep learning-based obstacle avoidance system that was deployed as a product. And then we later have X2, which is the enterprise version, and we have the dock for both S2 and X2. And like we mentioned earlier, we not only develop hardware, we also have software offerings. So we have house scan and 3D scan that you can specify a volume. The drone will autonomously collect data for you according to the volume that you specify. And for our latest product offerings, we launched X10 2 years ago, and we also have the dock for it. And as a software side with the dock, you can think about it as the robot vacuum that you had at home. You can basically, remotely operate them through a web browser. And specifically, we found that, for firefighters or police officers, they can actually use this as use drone as the first responder. So that, traditionally this has to be carried out through a helicopter, which is, a lot of risk and a lot of money that involved, but drones are now mature enough that you can actually use it frequently to get really quick information, and so that they can deploy faster and do their job more efficiently. So yeah, we're gonna share a little bit about our latest platform and with a demo. So if you can, please connect your phone to the Wi-Fi. I know it's not very fast, or any kind of reliable internet. So for Skydio X10, it's our enterprise version. It's a very modular platform that you can have attachment to extend its capability. So we have night sense to allow nighttime operation. I will talk more about it later. You can put RTK, speaker, spotlight, and parachute for safety. And we also allow third-party integration. It has NVIDIA Jetson Orin and Qualcomm Snapdragon on it. So you have powerful CPU and GPU to work with. And on this platform, we have 6 fisheye navigation cameras, GPS, IMU, barometer, and magnetometer. And we have a swappable gimbal that you can see here that has 2 high-resolution cameras and 1 radiometric thermal camera. So specifically because this is a computer vision conference, so specifically on our navigation cameras, it has more than 200-degree field of view. It has better sharpness than what we had previously, higher dynamic range, and it can work with both visible and infrared light. And on the right here is the camera lens. At the bottom here is just trying to give you a sense of the camera rig that we have. So we have 6 camera, 2 rigs. So each rig has 3 cameras in a triangle configuration. So that's how we use spatial stereos to perceive their environment. So 1 on top, 1 at the bottom, and there's attachment port that's in the middle of the rig where you can put stuff on it. For example, Night Sense. So Night Sense is a LED attachment that you can put on both top and the bottom rig so that it can enable operations in no light environment. So on the right here, you can see this is the visible attachment that we can basically illuminate the scene, right? So that we can navigate visually. And then at the left here is a log playback. So on the left here is the mesh that we created, post-process and created from our logs. And on the top, and on the right here, top right here is the equirectangular view of our stitched navcam images that's in IR spectrum. And then at the bottom right is the subject camera. So you can see the subject camera can't see anything because there's no light, but there's only IR light. And but the drone can navigate in this kind of environment using our navigation camera and infrared light. And we bet very early and big on computer vision. our drones need to see this environment with this 6 fisheye cameras, and we need to handle like very extreme visual conditions, like many other speakers have mentioned. So for example, we need to handle not only sun glare, but also night bloom, if you fly under a light pole, and all the particles in the air will create backscatter once you have your own self-illumination. We have thin branches or electrical wires. A lot of our enterprise customers fly in this kind of industrial settings, and we have like reflective water or like reflective glasses or anything that's reflective that could confuse the drone in terms of from the algorithm perspective. We also have textureless walls, or like with the limited lights, sometimes the ground could look very textureless at night as well. And we also need to handle like extreme weather as well, like snow, water on the lens. And here's just a glimpse of how we how our obstacle avoidance system can see the environment. This is flying in a substation. On the left here is the raw footage. On the right is our deep learning based obstacle avoidance system. We use the stereo camera to perceive the environment. And specifically, you can see that the wires are actually very thin and very hard to see from human eye, but our system can actually capture them, even the ones that's even higher behind these 3 wires in the middle. So we're going to do a quick demo. This is, am I sharing?
Yeah, hello everyone. Yeah, before diving into the technical details, I will be giving a demo today. And, for safety reasons, unfortunately, we cannot really fly a drone inside this room, right? So also it's not practical to move everyone to the street and to see a drone fly. So what can we do? We like doing live demos. So today I will be demoing one of our products, which is called Dog Remote Operations. So it allows you to fly a drone thousands of miles away and using this computer. Let's try this out. Okay, so let me fly. So there's so many features I want to show here, but before we dive into those features, so I want to first introduce the interface. So what you are currently seeing. So on the left is the drone's first-person view, and you can see from the first-person view what is outside. But very interestingly, we also have another camera here. So we call this inspection camera. So I think probably the Wi-Fi is not quite good here. So basically, this inspection camera allows us to look at the thing outside surrounding the drone, so to ensure it's safe to fly. But I guess probably because the Wi-Fi is not quite, it doesn't work quite well. So on the right side is a map view, and if I zoom out, as you can see, the vehicle is actually located at the California, which is 2,000 miles away from here. And we can, so space is too small to use the mouse. Anyway, I'll just use. If we switch to the 3D mode, we can zoom in back to the location, which in the Summit Hill. And you can see some, green and orange bounding boxes. So those are the geo fences. So we make sure that the vehicle cannot fly outside the green fences. And also we make sure the vehicle cannot fly into the orange boxes. So basically the vehicle will fly just, you can fly freely around within these green fences, or maybe on top of the orange boxes. And another thing, since this is a kind of computer vision, conference, and if you look at here, we have 2 signal bars here. We have 2 state estimation system running simultaneously on the background. So one is a VIO system, which we will get into details later today, and another is the GNSS system. And before we fly, one feature I want to show you is this QR code. which is called this feature is called Ready Link. Basically, if you use your phone to scan this QR code, you can stream the drone's video feed on your device. And I will just do this here maybe for 10 seconds to allow people to scan this to try this out. It's this one. Maybe I can zoom in a little bit. Okay, cool. Let's try this out. Let's fly. And so if I hit launch here, you will see the vehicle will. So first of all, the vehicle is inside this dock, and so the vehicle will take off and do some 360 spin to look at the surrounding things. And now, so we are up, and so it's actually quite easy to fly. So because we have this satellite map, and if you want to fly to a location, you can just right click and click fly here. And then the vehicle will fly autonomously to the location you specify. And if I move a little bit, you will see this. Once the vehicle reaches to the location, and as you can see, we put just one waypoint, it will just fly to the location you specified. And once the drone reaches the location, you can take over the control. There's many features, but basically it's like if you play video game and we have basic keyboard control, you can move forward, backward, left or right, and go up and go down. So as you can see, if now I can move backward and go up, pitch down. One feature I'm very excited to show is called Street AR. So, and if you look at the video, we can just now look at the video feed here. You can see we overlay the street names and also some other information on the video feed. So this is very useful, very helpful for pilot for the situation awareness. You don't need to go back to the satellite view to look at where the vehicle it is and where you want to fly. And so because to make sure this work well, you have to have a very high accurate, very reliable global positioning system to know where the drone with respect to the Earth. But now let's just turn this off. And another feature I want to show is, so the kind of last demo I want to show is try to fly into a tree. Let's see what will happen. Oh, I'm not showing. So, okay, sorry about it. How do I? Maybe. Yeah. Okay, cool. Let me just maybe fly back a little bit. And so this is our schedule HQ headquarters, and I can fly down a little bit, and just the demo is basically we're trying to fly into this tree and see what will happen.
You always do the same tree?
You can pick a tree.
You can pick one.
You can pick one. So
as long as it's not moving.
So yeah, so basically, I can just fly down a little bit, and then the vehicle, okay, fly around all those trees. So we're not just flying this tree, so we can fly anywhere, and yeah. So basically, this kind of showcase for our obstacle avoidance, and I believe the Skydio is the first company to really deploy a deep learning based model on the vehicle, to do the obstacle avoidance. And finally, okay, now let's get back to the base. I need to. I don't know why the screen zoom in. I cannot see the.
Yeah. Do you want to maybe
refresh?
You want to refresh?
I don't know. I don't see the. It seems the video is zoom in.
Because we're sharing.
I'm not sure. Maybe we'll just refresh the page. So I'm trying to look for a button, but somehow the button is not inside this page. Anyway, it's trying the ready link. I see the video feed. I thought if I go, and you can switch between different camera views. You can switch to the thermal view, and also you can switch to the map view. Cool. Yeah.
How about on like.
Can I just stop sharing for a second?
Yeah.
So this is the hard part for doing the live demo. It's always the demo effect always.
You want to exit full screen?
Yeah, maybe X.
No.
So I still cannot see the. Oh, okay. Now it works. I think that.
Share the screen.
Zoom. Share. Okay, cool. Yeah, so somehow I don't know why the screen can zoom in. So yeah, the last feature I want to show is the return to the dock. So so basically now the vehicle, this is quite simple. You can just hit this return button and the vehicle will return to its base autonomously and then land into the dock. And we can look at the 3D view again to see the trajectory. So we start from here and go into this around this building, and now the vehicle is flying back to find this space. And once the vehicle is get close to the dock, we have a model try to detect our the dock location. So as getting closer, you can see we have this the blue circle around the dock. And another thing feature, as you can see, once we get closer and closer, the video, the zoom changes. And also we have the tag, April tag on the dock. So it helps us to estimate the relative pose between the dock and the vehicle. So the vehicle can land into the dock precisely and also begin charging. So great. I hope you like it.
Yeah, sweet demo. And now the landing. So how do I share the different screen? Can I share this? Okay. Cool. So okay, so we're going to talk about our VIO system just to give a really quick overview. So as you know, we have 6 images. We use cemented masks to like help us, pick the features to track, and we also have IMU, and these are put into a feature tracker or a flow estimation. We use rolling shutter, so we need to correct for it. We use IMU pre-integration. We also have optional GPS with relative heading, so that put into some frame transformation. And we also use barometer and sensor temperature because, we learn from, our data, like our intrinsic actually changes with the temperature. So we also need to correct for that. And all these data are feed into our VIO system, which has initializer, PNP solver, sparse map. We use a fixed flex smoother, and we also have health manager to like monitor the health. And at the end of it, we get a 6-DOF pose, IMU biases, camera intrinsics, relative heading, and also potentially time offset between the camera and IMU, sometimes it's useful to, even though we have it synchronized, but sometimes could still be some small error. So we want to share like a lot of the challenges that we ran into. So for for example, the first one is high altitude. As you know, high altitude reduce the parallax, and also when you're higher up in the air, the visual texture is a lot lower, and also your scale might drift. The IMU bias might not be easily observable, as drone missions usually carry out at a constant velocity. So here's just a quick log playback that you can see what the images look like. The second thing is that the research community put a lot of effort, which is initialization. So every time you see our drone take off, it do a 360 spin. It's not showing off, it's actually doing it for a VIO system. So it needs to observe the IMU biases. And also at high altitude, we usually require long baseline, so you have parallax, but then it also introduced a problem where as you integrate IMU for a long time, you kind of reduce the observability of the scale. And hardware is hard, like literally. So as we mentioned earlier, like if you stare at this bottom left animation here, like the camera lens actually moves with the temperature. And also in the middle here, the plot here is showing the IMU gyro reading. So sometimes the sensor quality might fall out of spec. So in this case, when the IMU is actually stationary, it actually has 5 degrees per second of gyro bias, which is really high. And then bottom right here, if you stare at it again, you will see image jello, which comes from mechanical flex or just vehicle vibration. And also at night, we have limited visibility because we use LED to illuminate scene. And also we mentioned like the dust or moisture in the air with self-illumination will cause backscatter. So this is kind of the images that we're working with, and our VIO system need to work. So it's very challenging. And also, everyone knows that VIO drift, like it's a commonly known problem, but we want to share a perspective where for drone use cases are actually less studied. We usually fly kilometer-long trajectory. It has much longer duration. It's higher in altitude. The scene range is very dynamic. You go from all the way from the ground all the way to 300 meters, and it's maneuvering at full 6 stop, right? So here's 64S screen recording where we travel for 5 kilometers at a 200 to 300 meter altitude. GPS is not used. This is purely on VIO, but GPS only used to like show you where the drone is in the map. And the second thing, Xipeng is going to share about our visual positioning system.
Yeah, so the visual positioning system is a little bit different from the VIO. So the VIO give you kind of a local smooth trajectory, and it runs a little bit higher frequency. But for visual positioning system, it works by building a kind of prime map, and which will be used for localization. And so some motivations. So for some for some drone related inspection work, and we need the drone to fly to a location repeatedly. So we need to very precise localization for the drone. And here is one example. And we basically set up a mission. The vehicle will inspect these shelves, and it will fly to a location and take a picture. And on the right side, as you can see, if we don't have this visual positioning system, basically dealing with a different time of day, and you can see that the picture is kind of varies a lot, right? And but with this visual positioning system, and it's quite stable. That's what we want. And another thing is, so we by building a prime map, it allows us to do the planning as well. So in this example, we do this inventory check, and there's a warehouse. We can build a 3D kind of, we call this now we call this digital twin, right? You can build this 3D map, 3D meshes, and then you can plan a mission. For this one is quite simple. You just fly shelf by shelf and hour by hour, and then you take a picture for each location, so you can do this inventory check. And here is a diagram how the the VPS works. And as I mentioned, it works by first building a prime map. The input is just the top and bottom camera images, and we have the VLO system output as the input for the VPS system. And it goes through very standard like keyframe selection, feature extraction, stereo matching, and then we have a factor graph to optimize things. And the output for the mapping system is the poses and also the feature map, which will be used for localization, and also the mesh map you already see. And then, so for the localization part, which it will take in the again the images and also the VLO output, and also the prime map we have, we have built. So this goes through this keyframe selection again, and then we have this small PNP factor graph. And once we get the output from the factor graph, which is kind of localize the pose, we still have a system to perform this consistency check validation to make sure we have a good solution. And the final output is just to localize the poses inside this prime map. Yeah, I mean, it's a very quite standard system, but our goal is really building a product to be very reliable and to work well in different scenarios. Here, just I want to share some challenges for the system. Of course, when we build this, like a vision system, we often talk about front end and back end, right? So for the front end, which is used for feature detection or matching, and some challenges here for warehouse inspection. There's repetitive textures. It's very common in the warehouse, right? As you can see, it's quite similar from different frames. And another challenge is the scene changes. Of course, in the previous one, it's like it doesn't change a lot frame by frame, right? And then here is another scenario is it changes a lot by kind of at different time of day or maybe different location at the same location. So here is at a substation, and on the left and right is the two images taken at a similar location but at a different time of day. I can guarantee you that the traditional system match won't work well, especially with all those shadows, right? Like the gradient of the histogram or gradient won't distinguish between shadows or those corners, right? So we do leverage some learning based methods to feature detection and matching to leverage the semantic informations and the global context to perform better matches. So even you have, of course, we cannot guarantee how 100% totally correct matches. Even you have a majority matches are correct, there's still other challenges for the back end. So for example, in this case, and for the top camera, we get lots of matches, also correct matches between two camera images. But the challenge here is that all those features is so far away, and essentially those features can only constrain your orientation, but cannot constrain your translation position quite very well. So that's kind of a very challenging scenario for far away things. And I mean, another really challenge part for building this product is really how can we really scale up scale up for to build a very large map, right? And of course for drone, it have very limited flying time, and for a very large location, how can we really map the whole area and how to more efficiently? How can we leverage multi-drone to do this? And even even though like we built the map on the cloud and then download the map to the edge device to the drone perform localization, you still need to think about like what to upload and what to download, right? Because we have the limited time and also limited bandwidth to perform our missions. So we try our best to really reduce the memory usage and also the optimization time to on the cloud to so we can build a map as quickly as possible to avoid delays formations. Okay, now I'll hand over to Sam. We'll talk about the infrastructure.
Yeah, so to scale autonomy, you definitely need good tools, and not just software, but also hardware. So, you know, we don't need to talk about the common error metrics, but one thing to share here that's unique to us is, you know, Doc is not only a product, but the fiducials on it also provide kind of pseudo ground truth that at the end of the trajectory that you can use to evaluate your VIO system, which is very valuable, you know, as ground truth is often lacking in real world scenarios. And then we, you know, with user consent, we kind of compress this error metrics into analytics so that we can use to monitor system performance and drive future development. And of course, we definitely, you know, want to test this in scales. So we have like curated log sets that spans, you know, different altitudes, flight profiles, scene textures, lighting conditions across like the globe. And, you know, we can run this regression test on cloud station, you know, clusters and with really fast turnaround time. And so that we can make sure, you know, with these metrics and these testing suite, we can really ensure consistent performance across software updates. And, you know, drone is both a product, but also a valuable internal testing tool, right? We can basically run this like 24/7, and testing suites that we develop like over time can run daily and nightly on different branches. It's very useful. And, you know, we also have simulation for rapid control, repeatable development. And we're really good at, you know, killing two birds with one stone. So this is also a very valuable interactive training tool and demo platform for external customers too. So it's not only used internally, but also used for externally. Yeah, so we're here for questions. And, you know, this is a teamwork. Shibon and I are here. Aaron is also here. Also Max that joined us. And yeah, we're hiring. Paul over there is our lead recruiter. You know, we not only work on VIO and VPS, we also work on, you know, many computer vision related projects. So we're hiring. So maybe join us and let me know if you have any questions.
Any questions? Yes, go ahead.
So I was wondering, in theory, you could only do with VPS, right? You wouldn't need VIO. So is the frequency of the VPS sufficient enough that that will be possible?
So the VIO, sorry, can you clarify a little bit the first part of your question? You said VPS cannot run all the time and VIO is running all the time?
No, so I would think that you would need VIO if your VPS is fast enough.
Yes. But, you know, for drone, for obstacle avoidance, for just any kind of, you know, normal navigation, you need good enough state estimate. So we need VIO to be running like at a centimeter level so that you can avoid obstacles. And VPS, yes, you don't have to run it all the time. You just need to like correct your drift with respect to the map, or if you want to localize it in, you know, in a different location. Yes.
So it cannot run on board at a high enough frequency.
It is running on board. Yeah.
But not at 100 hertz.
Yeah, not, and it doesn't need to, right? Most of the time it just needs VIO, and then only when you're performing a mission, once you reach the spot that you're interested, you run the localization, make sure you're at the consistent location that you care about. Yes, please.
Hi, I have another question. So it's about the demo. You showed this point and click navigation. So you control your drone to a specific point and you plot it a straight line there. So what happens when there's an obstacle here, like a power pile and something like that? Is your drone making a detour? Is this planned into?
Yes, we actually have a new, like most recent feature that we released. We call it Pathfinder. So you can load a map like, you know, from Google Earth or something like that. It knows the geometry. It can actually plan it around. And that's for the global perspective. But for local perspective, it'll always, you know, move away from any obstacle that's not in a map. So yes, it does. So imagine if you're flying in an urban environment with buildings, it will plan around it.
So in your scenario, when you click, basically you show the straight line, but the drone actually will sort of avoid obstacles and nevertheless come to the end?
It shows the straight line because there's no actually things in the map, but if there is any buildings, it will actually not show the straight line. It will show you like the path that it planned around it.
Very nice. Thank you.
Thank you.
Any other questions?
Thanks for the presentation. So what were some of the motivations behind not using like a LiDAR as part of the sensor fusion here to help with, you know, some of the textureless environments? And I guess maybe to follow up question to that, how do you deal with textureless environments?
Yeah. To answer the second question, how do you deal with it? Deep learning is very powerful. So you can actually train a model to recognize the scene in a global scale so that it can actually, you know, understand it. So the first part is why not use a LiDAR? So I think LiDAR is like the point cloud is actually quite sparse. So images actually give you very, very dense information, and not just, you know, with stereo camera, not only can you perceive the depth, right? You can also have semantic information and everything else. So that's the bet that we made very early on, and it turns out it's very useful. Of course, I understand there's always a debate, you know, Tesla versus Waymo, like, you know, LiDAR versus camera. So yeah.
And the second question I have is, how do you deal with motion blur in like low light scenarios? And has that been a challenge for you guys?
Yeah, motion blur is definitely there, especially at low time, in low light at nighttime. So you know, we have IMU, so we can actually predict how much motion blur that we're expecting, so that we can do something clever about it.
Thank you.
Thank you. There's one question at the back.
I would say you come in the front because there are
I can repeat. Okay.
So the question is like, how do you handle the calibration of all the sensors on board? Because like you operate in like very harsh environment, right? So there's going to be thermal expansion and all. So the intrinsics as well as extrinsics are going to change.
Yes. Yeah. So we have different system that runs it, but our VIO system that we mentioned, it's actually using both vision and IMU information to correct for the extrinsic, and also do a joint optimization. So you estimate both in real time.
Okay, so you
Yes. So we have factory calibration that will, you know, reach to a ballpark, like a, you know, but then, you know, as you deploy, the vehicle is flying, wear and tear will definitely change it a little bit. So we always run online calibration.
Thank you.
Yes, please.
Wondering if you run Jetson or
Jetson. Yeah.
So if that's the case, can you share what frequency the update is?
Maybe not. Yeah. It's nothing, you know, nothing fancy. It just, you know, it's some internal number that maybe it's not appropriate to share here. Yeah.
Right. And it's down 7 or 6 cameras in same.
Yes. It's actually more than 6 cameras. So on the gimbal, there's 3 other cameras.
Oh.
We don't use it for VIO, but like they're also running something for other applications, like, you know, like scanning and stuff. There's also something running there.
What about the flying time? And when you run multiple cameras, and what is the normal time of flying?
For X10, the flying time, I might be slightly off, but like it's close to 40 minutes, 35.
When you operate all the cameras.
Yeah.
Okay.
It's all, yeah, all the cameras are running all the time. Yeah. But you're right, it does take a lot of power. So, you know, we have tested with, if you only fly with GPS and not use any vision, you can definitely get more juice out of it. Yeah. Yes.
You mentioned trade-offs between cloud and edge computing. Like, how much of this runs on the actual drone versus like in the cloud? Like, does the visual processing system run on the device as well, or?
Yeah, so that's referring to the mapping part. So once we collect, you know, if you want to do a repetitive mission that you want to localize with respect to like the previous flight, yeah, then there is a trade-off there, and we can run both, you know, locally versus and also like in the cloud. It just depends on like the use case. For example, if it's in its environment where like you don't have good enough internet, kind of like here, right? You don't have enough bandwidth to upload all the data, then you can run locally. But then if you have a really big map and with good internet connection, you can always upload it and then optimize in the cloud and then download it back. Thank you.
Question. Thank you very much. And it's really, I'm really appreciate at the end of the day until now, it's already 6 p.m. almost. So it's still quite a lot of people here and to listen. Also, we have quite around more than 10 people on Zoom and YouTube. And so we have good turnout. Okay. If you don't mind, and every time when we finish this Zoom, this workshop, and we want to take a group picture, and so as a memory, and so maybe later we can post on the website of our workshop. So if you don't mind, come to the front and come to the stage, and we will take a picture, group picture together. Yeah, sure.
We take the picture. Oh yeah. Yeah, like if you have bad access, you know, then you can't control it.
I'll come to the front piece, something like blocking the view.
It's better to stay in front.
Yeah, I think so.
In front of the podium. So maybe you come a little.
The Wi-Fi.
Thank you.
What about dynamic option cost for you guys?
Yeah.
Does that could be a problem?
Yeah, if it's actually moving really fast, yeah, they will become a problem. But if it's like slowly moving, we can kind of treat it as a static. Yeah, so there's a limit. Yeah.
Yeah, you fly very fast, everything else is, it's
Luckily, we're in the air, so.
Sure. Let me stop recording.
In the airspace.
Second floor.
还适应吗？
挺适应的，
还行。昨天还看到的，
So it will broadcast where you are in the GPS and where you're going in velocity, so that you can use that.
刘老师我也看到，今天这个在上午。
That's what I heard.
Yeah.
That's what I heard. I'm sure you guys.
And you know, in the jet, like on the right side of the map, like it should also show you like where the other vehicles are flying at the same airspace, so that you can also avoid it.
That's also the wider field fence feature. Please make sure that the drone will not fly out and buy something in the areas.
其实室内比室外难一点点，现在在室外的环境更
rig and everything else. Just the drone by itself.
就是更多样的，就是在里面的
like the dock and the cloud software and everything. I think that comes like 50 a year. But 50.
50,000.
The dock, the drone, the annual software.
Okay, let's try.
We created your.
First did this guy?
Yeah, I think we have a group called SLED, State Local Education Group, so they
We do schedule for good. We work with schools like high school. We give.
Usually the problem we always get is, can we have low level controls to the drone, and then the answer is no. But if you want to use it and you just want to like for your traffic analysis and collecting data and stuff like that, that wouldn't be a problem.
Collaborative perception.
Yeah, there you go.
Air and
That could-
ground, right, yeah.
So
when a customer does like an inspection site, do they kind of get like a?
Thank you so much.
Thank you for organizing it. Yeah, it's a pleasure.
Yeah, we really have done quite.
Depends, like,
Or is it all fully post-processed?
there's both. There's on the yeah.
Yeah.
We have on
Yeah, I mean,
it's all part of one estimation.
Okay.
If you just kind of want to.
well, I manage.
Yeah, okay. So you do like a quick.
The-
like,
Yeah, just to make sure you capture the whole process.
Some of them are
Yeah,
post
some
doc and
customers,
some
they
are
have their
not
own
students, so
sign up as well. So we
the
can-
one that you saw probably.
But then you need to like work on like with a little bit of what you're saying, right? Clean the reference.
Yeah.
It's really depends on application, you know, some customers, they just
Maybe
want to.
less than
have
10.
coverage to make sure they.
Wow.
Yeah, less than 10 over the years, because some of the students just keep working on the project, keep extending, right? Yeah, less than 10.
I got a quick question earlier about like the LiDAR and the camera. Yeah. What did you want to use some of that, like for redundancy?
He speaks
Like in
about the
cases where, you
students,
know,
that's
like
why they
camera,
loved it.
but it's also.
They all come to great places, so, yeah.
Sensor fuse that with LiDAR.
You use
Yeah, but you get trade-offs, I mean, the weight, the size, the cost, the power, all those things.
I always do
So
robotics,
it's a design
even when I'm
Yeah.
publishing graphics.
You
I
cannot
always do
really
simulation.
put a line.
So the whole idea here was we
And
can
you
run
want to
simulation models
and
into all of these applications.
And which you can use for training.
Yeah, use it for training, use it for accelerating learning systems. Like I said,
Well,
if you have the.
For background,
equation,
like we
you
work
can-
at Deep
you can
Structure,
solve
we make
it
like underwater robotics.
thousand times.
And we're kind of getting into
And
similar
the same
realms,
thing
but
for
like
some
we
of
got
the things that we were doing.
Do you know
in
this?
traffic reconstruction.
Do you know the company of this?
And I just don't understand why people don't, I mean, I think most of people don't understand simulation, they don't understand.
Section map, and they were doing already.
Right now.
No, we don't use.
Right, there is a huge,
Like,
I mean, it's a really
also
useful
like
thing,
3D
so I'm seeing
sensor.
simulation is being used
Yeah, it's,
everywhere, I mean.
Playing around with
and
some slam systems
part
like
of
that,
AR
as well as
and
like
some
spirit
robotics is
cameras
that
and stuff.
interesting
You're
simulation.
trying to fuse some
You
of
know,
that
so
together. But
there's
it's more challenging underwater,
media
because lack of
invested in a
visual
lot of
features,
simulation,
lack of light,
because people are
and then
recognizing
all gets very kind of
simulation
weird
data
too.
to fill in the gap.
Yeah.
Interesting.
Actually, I found, I myself found quite a lot of agricultural robotics, and I'm trying to build something like simulated. Field that we can grow, we can have different kind of crowd or whatever. You see situations, whatever, and sometimes my students don't want to do that kind of things, and
you would
Simulation
localize
is not
against those.
Yeah, I don't.
Like cell
I don't
image
always have a
mapping,
huge
we
number of
have done
students,
like
but
experimental
whenever
projects for
I try to,
that, but we don't currently have
you
a
know,
product.
get them to do multiple
And I
projects
think
and
it's because
collaborate.
we have a
and
startup in
multiply,
Finland called
you know,
Spectacular AI,
it's
and
a
we
lot
are
of
doing
work,
that
so
stuff.
it's
So
just
if
a
you want
matter
to
of
check
sort
out.
of getting the right students. But
I
my
mean, we
job
have
is,
some public
it's
demos
self-select,
that we
anybody can do
write
simulation these days.
I
You
will
can
be
do
the
machine
type of
learning also.
organizer.
Why would they not want to do machine
No,
learning? But I
just
think these
experimental
are the
drones.
best
Like, we are not
is
manufacturing
willing
drones,
to
but we are
integrate
doing software,
simulation
so
into
we
machine learning, because you
Odometry
actually
and
know,
visual
need to
positioning.
know different kind of math.
Currently,
Apply
I'm
without
trying
the
to
satellite
ask, whether it is possible to use something
Mhm.
like Bridge or whatever other things.
That's pretty cool. I think the
something
stack
like
like
using
this.
3D calibration for
useful, like,
the
even how to.
and so later on we just run simulation for robotics and for those kind of tasks. But have you done those kind of things?
We use simulation, we use large language model.
Seems like you know
because
about what you're doing.
language
And,
is not
question,
precise.
you mentioned that
So
you're
unless
doing
you're gonna
work
use language to specify your mathematics
your own
equations
functions
and
as well.
quantitative, right, yeah, exactly.
We didn't mention the
And
details, but
that's
like
the
we have a
quantitative.
low level MCU that's
And that
running
means that if you
for
have that
low
much
level
information,
control and
you
also
need
the
simulation.
GPS estimation stack runs on that. So we have redundancy.
Actually, it's already a form of pipeline and that we
Yes.
robotics.
That's for multiple reasons. You have real time.
Automatically or something is doing or part of engineering.
No, we did all of that.
So like the.
Because the company was
still
founded
require
around the
math.
time when
So
Articulate and,
we do
you know,
like some of these scenarios.
Yeah,
with the
exactly.
author.
When
And so that means that students have to
2014?
create these scenarios.
Like kind of in
And then
parallel.
once it's run, once you create a scenario
Yes,
of assets, then you can run. So automatically creating scenario is still hard.
Good job.
And then that does
How big
take
is your guys'
time.
engineering?
And but once you create a scenario. it's
again,
really
How big is
hard.
your guys' engineering?
Yeah, actually, we
Like,
also
what we're doing
do
is just
how to do better simulation for the and maybe they have
Hardware, software, autonomy.
the guidance.
Sure, happy to chat. No, we met. How are you doing?
Actually, I met with you just on Anchor, but I didn't never had a chance to talk to you.
Yeah,
We
we
always
met.
have students.
I mean, we had a really big show at the
Headquarters is engineering.
which is great.
Yes, 20-something paper, I remember. This year.
I actually have a.
I mean, our group has 10, but Maryland is.
Yeah, I've seen this before.
Yeah, Maryland has 70 faculty in robotics.
Okay.
70.
70.
So we had a Maryland Robotics Center and Maryland 70 faculty. So
Maryland also gets like a very big donation, something like 100 million, something like that. And
So
I don't know, AI.
No.
Depending on
No, they did not get a donation for that. They claim they want to hire 30 faculty or 100 faculty, all these stuff, fictitious number that doesn't exist. There's no.
But I mean, you sometimes say myself, yeah, right now you're at Amazon.
Yeah, I'm an Amazon scholar. Yeah. Yeah. So I'm with Amazon Robotics.
So I mean, you work on transportation, but Amazon is doing a lot of logistics. So what you said, what type of robotics? What do you think? You said all of it, right?
All kinds of yeah. All kinds. It would actually be very interesting, some of the autonomous vehicle stuff that we do, because that just. They also have those robots driving in their warehouse.
Integrating everything, so
those
like
are
a system
just-
level
those are
challenge, you can have a state of the art.
So they have their logistic, but right now it's more like all general simulation scenarios.
Because what I'm aware of is sort of the picking robots, of picking was a big topic for Amazon, and also the warehouse robots.
Yeah, they picking in the warehouse, but they're still not in production. Because they really want to digitalize everything. And there are stuff that still get jobs, things they. So they also like picking, how do you bing and how do you pack and all that. So a lot of Amazon, it's have a lot of robotics technology. That's why I say I was like, wow, this is like amazing. This is like robotics employer in the US. You have all these operations everywhere in the warehouse, including the warehouses. So just getting things to go, it's all automated and it's not all automated. It's highly automated.
About trucking, automated trucking.
Yeah, they are definitely, yeah. So those are. They are not.
So you said that autonomous driving might be coming quicker than we think. So this was surprising because way back actually it was predicted that we will have this within 5 years, which is now 10 years in the past. Yes, but it doesn't seem to like get too common or available to customers. So I have the feeling at some point we might see this autonomous trucking earlier than actually.
Autonomous trucking is already ongoing. Yeah, so because what they're doing is they're doing it in using all that. It's easy because that's the easiest. The hard autonomous driving is the one that drivers dealing with the pedestrian, and that's like the high risk scenarios, right? And you don't have to have 100% autonomous vehicle driving around. Like, there's different level 1, level 2, all the way to level 5. Okay, so you have different level of autonomy. And we are already enjoying it. That's the way I'm looking at it. And you did not even know you're paying for all those features.
Okay.
Yeah, actually, I see. I always work. I used to work before, and I always work at project for the GM, and they recently hiring for it, but they indeed open another department for GM that for the robotics. They just open a new department for the robotics. They not for autonomous driving, but like you mentioned, for the replacing the factory actually.
Right. So yeah, there is a lot of possibilities. Yeah, so I mean, I think that's the one place that robotics will make a difference. Actually, it already is.
It seems like you are switching the focus from Maryland to right now to Amazon right now.
Just want to say thank you.
Okay, sure, absolutely, yeah, later, yeah.
Thank you.
Yeah, I mean, I've been always doing robotics for years. It's just that some of these basic things go away. So, yeah.
I know quite a lot of people That's true. Actually,
So I want to know if I can test your device because I will have a workshop to organize.
Sure.
Okay, so how to test it?
Yeah, just plug it in here. Learning. I hope, you know, probably you
No. I mean, I can't.
You have download for your.
You got it, not here. And then I would need a special permission. None of this is like. I'd be very high level description. And they have a booth here, but for me to give a talk here, it's all work and it's not information. Yeah, so you have, yeah, you didn't hear anything, you only hear it very high level. I would say, I have not.
Oh, you build it out of a head for the arms on the body.
I helped you, right? I'm gonna be out. Yeah, I'm gonna be out of booth, so, yeah.
You are hiring, actually, you are hiring a team.
No, I'm not hiring, I'm not going full time, just part time.
Okay.
Yeah, but I would be out of booth just photo.
No.
Photo op.
You're supposed to provide, but we're not providing.
I
actually need to leave.
Yeah, sure.
So we have, I'm still.
This is going with the UNC event.
No,
I will be there as well.
Yeah.
So I
but-
was
but
supposed to get you.
Otherwise.
Yeah,
You just drop on my back.
But
Yeah, you just drop on my back, so
Yeah.
I will see you there.
I also have.
So if you have Zoom,
I forgot which one.
have in your
What's the name?
presentation, then you can log into the Wi-Fi here.
So
CVPR special.
No, I forgot which day. I also has something like invite a team.
outside.
I forgot which one.
Participants, we are
But I
also
forgot.
So what I mentioned is
Also-
the University of North Carolina. So we plug the union.
So you were there, okay.
Yes.
You worked in UNC before?
Yes, only for a short time with Mark.
Okay.
So basically, where Mark was moving.
Mark qualified.
Exactly.
Okay. Yeah. I saw Mark qualified. I should see him in the next time. Hopefully I can show.
I think he was busy with his own workshop and giving talks around. So he's always very busy, but you're right. This would be a good person.
Okay, cool. Yeah. I will still see you around.
Yes,
Yeah,
absolutely.
Yeah. Cool. Yeah.
I'm here. So it was very nice.
Yeah, finally.
You
This is
feel
really
actually you
the
have a
high
very nice
one.
lineup of all the presenters.
This is really, this time is really time.
So now
I have never had such a long workshop day from something like 8:30 to something like 6, and then even there's no lunch time.
You're right.
Okay, cool. Yeah, so see you around. Yeah. 对，那个你们那个谁，他叫那个孔老师还跟我谈了一下，他还想做一些 embodiment。最近就是感觉他感觉计算机视觉做不太动了，有点。他还跟我说了一下，他想做一些机器人的东西，我俩谈了一下。他是让你去做吗？现在？
对，我这个其实一个